Hi, welcome to YourPedia. My name is Gurumurthy. I will teach the subject is nothing but electronic devices and circuits. So what I can able to taught here means, so electronic devices related concepts like what means semiconductors, characteristics of semiconductors, current mechanisms in semiconductors, right, drift to diffusion mechanisms, basic PN junction theory, and special diodes like Zener diodes, tunnel diode, Varactor diode, and what their characteristics, and as well as BJT concepts, and next FET and MOSFET, and somewhat VLSI concept I discuss. Okay, so this topics 100% helpful to you for all your GATE as well as any PSU sectors or any other competitive exams, as well as for interviews conditions, any corresponding to electronics related concepts of electronics related concepts of what means exams. These concepts are very useful to you. Okay, so now you can able to start what this electronic devices and circuits. Now you can able to examine the theory of semiconductors, the type of questions he asked in this. So the first question I go, why protons do not contribute to conductivity? And so now the question he asked is why protons do not contribute to conductivity. So come back here somewhat to the atomic structure. You know that in the case of atom, three fundamental particles are there. Those are electrons, protons and neutrons. Confirm now? In a given atom, you know that three fundamental particles are there. Those are electrons, protons and neutrons. Right? Electrons have the fundamental property of what means the condition of movable you can call. Confirm now this. The carriers we find out here. So the carriers are electrons. Okay, one more is proton, other one is neutron. Confirm? These are the three fundamental particles you can call. He asked that why the proton do not contribute to the conductivity. Suppose if I go for charge for electron, the charge on electron is 1.6 into 10 power minus 19 coulombs. 1.6 into 10 power minus 19 coulombs. Right? So proton also have the same charge. 1.6 into 10 power minus 19 coulombs. So both electrons and protons have the same charge. 1.6 into 10 power minus 19 coulombs. What are the neutron? Neutron is a neutral particle, has no charge. Neutron is a neutral person that has no charge you can call. And what is the polarity of this charge carriers? You go. Polarity is the electron is a negative charged particle. Proton is a positive charged particle. Neutron has no charge, no polarity you can call. No charge as well as no polarity you can call. Confirm now? Now, if I come back to their property, what are the property of these carriers means? Electrons have a fundamental ability to move. It have a mobility. Means in a given crystal lattice, electrons should be movable. Confirm? But what are that your proton you ask? That is a stationary person. That is not movable you can call. So proton is a stationary. Neutron is also stationary you can call. Confirm now? So proton have a charge same as to the electron, but it is unable to move in a given crystal body. So proton should be at the center of an atom you can call. That should be called as a nucleus. There it should be fixed. It is unable to move in a given crystal lattice, so that the current is not be caused by the proton, even it have a charge same as to electron. The main reason is it is a stationary, fixed in position, which is unable to move. Even it is a charged particle, because it is fixed in the position, it is unable to cause the conductivity of current. Whereas the electron in a given crystal lattice, it can able to move, and due to its movement, it can cause the current conductivity. So you may find that the current conductivity among these three particles only by electrons, which should be movable. And so now whatever that protons are stationary persons, right? They are fixed in a given atom at the center part of an atom. That's to be called nucleus, you say. They are unable to move, you can call, such that no current conductivity caused by protons. So protons do not cause the conductivity because of their position is fixed. That should be the answer for that question. And so now check out the next question now. So next question is nothing but what is meant by energy gap? What is meant by energy gap, you can call. So next question I can go, what is meant by energy gap? So now let us see this one now. In the case of an atom, all electrons do not have the same number of, all electrons do not have the same amount of energy. And so now in a given atom, all the electrons do not have the same energy. They have different values of energy, you can call. They have different values of energy. So some of the electrons have high energy, some of the electrons have lower energy, like this. So they have simply said that random values of energy. So because of their random energies, how do you know the probability of energy of an electron in a given atom means that known by the energy band diagram. Confirm my option. So in a given atom, all the electrons not have the same energy call. They have different values of energy, I told. Confirm now. So in a given atom, what is the probability of energy by an electron in a given atom known by the energy band diagram? Energy band diagram. This energy band diagram have three partitions, I think that you know. Those three partitions are, one is valence band, confirm. Another one is conduction band, right? These together separated by a gap, that is called forbidden energy gap, or simply called energy gap. So now the question he asked is what is meant by this energy gap. And now let us see this one now. According to the energy band diagram, the energy of the carrier is ranging from minus infinity to plus infinity call. Considering the lowest energy of the carrier in conduction band is EC, highest energy of the carrier in valence band considered as a EV. And thereby this energy gap is the energy difference, you can call, that is EC minus EV. And this energy gap commonly measured in terms of the unit is electron volts. It is commonly measured in terms of the unit is what? Electron volts, you can call. What is this valence band? Valence band is the range of energy considered by valence electrons. Valence band is the range of energy considered by valence electrons. Conduction band is the range of energy considered by conduction electrons, nothing but free electrons. It is the range of energy considered by the free electrons. Valence band is the range of energy considered by the binded electrons. Got it now? And what is the energy difference between the valence and the conduction bands is called energy gap. And what is the importance of this energy gap? This energy gap represents the minimum energy required by an electron to move from valence to the conduction band. So this energy gap indicate the minimum energy required by an electron to move from valence band to the conduction band. If the applied energy is less than energy gap, nobody can jump into the conduction band. So energy gap represent the minimum energy required by an electron to move from valence band to the conduction band. Right? If the applied energy is less than energy gap, no carrier can jump into the conduction band. Confirm now? So energy gap always represent the energy needed by an electron to become as a free. Confirm? That's the energy gap you can call. And this energy gap is different for different materials. Suppose if you go for conductors, this energy gap is almost zero. So that in the case of conductors, you know that valence and conduction bands are superimposed, you can call. If I go for insulators, energy gap is very high, indicating that there the electrons are very tightly bound, you can call. If you go for semiconductors, the energy gap is moderate, it should be around 1 electron volt, you can call. Confirm my option, sir? So energy gap is represent the energy need by an electron to become as a free. Right? So if the gap is more energy required. If the gap is less energy required. Lower the energy gap, less the energy required. Higher the energy gap, higher energy required. So indirectly, energy gap represent the bondage of valence electrons in a given atom. Energy gap simply indicate the bondage of valence electrons in a given atom. Understand this? What I told you? It represents the minimum energy. It represents the minimum energy, right? It represents the minimum energy required by electron to move from valence band to conduction band to become free. Confirm? So this energy gap is expressed as EC minus EV, I call, where EC is the lowest energy of electron in conduction band, EV is the highest energy of carrier in valence band, I call, and measured in terms of the unit is electron volt, you can call. So one more thing I told you, the energy gap indirectly define the bondage of valence electron. So one more way if you want to define, it also represent, confirm, it also represent the bondage of valence electrons, bondage of valence electrons. So using which you can identify the electrons should either tightly bound or loosely bound. I think that you know, so conductors, insulators and semiconductors are mainly distinguished by the size of energy gap. If you go for conductors, the energy gap is almost zero. If you go for insulators, this energy gap is very high. If you go for semiconductor, this energy gap is moderate. And so now, what that is the meaning for energy gap. Now I can able to check out the next one of this. Check out the next question. Why don't you find holes in conductors? He asked that, so the current carriers are not the holes in the case of conductors. Why you don't find the holes in the case of conductors, he asked. Now come back here, if you go for conductor, conductor is a good metal, you know. Sir, all metals are good conductors, you can call. A conductor is a body that can allow the electrons to pass through it freely. That is called conductor, you can call. A conductor is a body that can allow the electrons to pass through it very freely. And so now, so all metals are good conductors like copper, silver, gold, like this. All are good metallic bodies, you can say. And according to the condition of conductors, the energy band diagram is such that in the case of conductors, the valence and the conduction bands are superimposed. Just I indicate that one now. So in the case of conductors, the valence and the conduction bands are superimposed, you can say. So yes, now. Now I can able to go for the energy band diagram for conductors. In the case of conductors, the valence and the conduction bands are superimposed, I can call. So this is the valence band, right? And this will be the conduction band, I call. Both are superimposed, I say, indicating that in the case of conductors, the energy gap is almost to zero, you call. So this is the superposition place, you say. Both are superimposed there, confirm, indicating that the energy gap in a conductor is almost to zero. The meaning of that, what sir means, the conductor body do not require any external energy to make electron free. All electrons are free. They do not ask any external energy to make an electron as a free. Because the energy gap is zero, none of the external energy are required to make an electron as a free. Because of that free condition, they can move anywhere in that crystal very freely without applied source. So these electrons can easily move from valence to the conduction band, right? So they can easily move from valence to conduction band, at the same time conduction to valency band without asking any extra energy. And they are move around valence and conduction bands, so that in the case of conductors, you say that valence and conduction bands are partially filled. So electrons are not static in one area. They continuously move around valence to conduction band and conduction to valence band, so that both bands are partially filled. Confirm now? And commonly you know that the hole is a carrier that can be defined due to the loss of electron in valency band. That you can expect commonly in the case of semiconductors. So even electron in the valence, even the electron is jumping from valence to conduction band, I don't find any loss, because your valence and conduction bands are superimposed. So there is no separation. Wherever it is, it belongs to the same place. So commonly the hole is considered due to the loss of electron. But I am saying in the case of conductor, even the electron jump into the conduction band, I don't find any loss of electron in valence band. Why you say like that means, because both bands are superimposed wherever the electron that belongs to the same place. So you don't find the loss of electron, even the electron jump from valence to the conduction band. In that manner, in the case of conductors, you do not find the holes as the current carriers. Only the current carriers are purely electrons. Only the current carriers are what, sir? Purely electrons. So no hole is found out in the case of conductors. Why you say like that means, because the reason is the valence and conduction bands are superimposed, energy gap is 0, the electrons can able to move from valence to conduction band at the same time conduction to valence band without asking any extra energy. So both are partially filled, I told. Confirm? Both are what? Partially filled. Making that, so the electron wherever it belongs to the same place, such that in the case of conductors, the current carriers are only electrons. Conductors are, in the case of conductor, the current carriers are what, sir? Only electrons. Confirm on this one. So why don't you find the holes in conductors means? Hole is due to what, sir? Loss of electron I call. Hole is due to loss of electron. But even the electron jump from valence to the conduction band, I don't find any loss. Confirm my option. In conductor, energy gap is 0, right? So that electrons move around valence band and conduction band without additional energy, without extra energy, right? Without additional energy you can call. And even the electron jump to the conduction band, it belongs to the same place, right? And electron even goes to conduction band, right? There is no loss of electron in valence band. Commonly hole is created due to the removal of electron from valence to the conduction band I call. But here valence and the conduction bands are superimposed, both look like the same band, such that you don't expect any hole in the case of conductors, right, sir? Check out the next question now. Why silicon is preferred over germanium? Right? The question he asked is, why silicon is preferred over germanium? So you know that there are two fundamental particles of semiconductors that are most popular in semiconductor devices is germanium and silicon. These are well popular semiconductor devices in our PN diodes, right, BZT, all these things, FET to MOSFET. So commonly these are the semiconductor devices, they are preferred to be made by either germanium or silicon. Particularly if I compare silicon and germanium, which should be preferred over the other, which is most popular over the other means that you commonly say that silicon, right? But originally if I compare silicon and germanium, sir, as compared to silicon, germanium conductivity is more. Germanium conductivity is more as compared to silicon. If you apply the same energy to both silicon and germanium, suppose this is a X material, this is Y material, it is made by germanium, it is made by silicon, right, sir? I apply the same energy to both X and Y, and both materials have same dimensions. So what are the X dimensions? Y dimensions are same and are driven with the same energy. Just only they made by the metal here, X is by germanium, Y is by silicon. If I compare the conductivity of X and Y, what I told means the conductivity of X is greater than conductivity of Y. X is a germanium body, Y is a silicon body. But you say that who is mostly preferred than other? Silicon is mostly preferred than germanium. Even the conductivity of germanium is greater than silicon. What the reason means? The thing is, as compared to germanium, silicon is abundant, easily available in the nature. Confirm, sir? So, silicon is easily available in the nature, you can call. So, as compared to germanium, silicon is abundant, you can call. Easily available in the nature as compared to germanium, first one. Next one is what, sir? Silicon have less minority carrier effect as compared to germanium. So in the case of silicon material, the minority carrier effect is very important in semiconductor devices. That minority carrier effect is less in the case of silicon as compared to germanium, you say. So one more is the minority carrier effect is less. The minority carrier effect is less in silicon, and it is fundamentally stable, you call. It is more stable. This is most required condition in the case of amplifier circuits, all this. So silicon is quite stable because of the minority carrier effect is less. And one more is silicon should operate even at high temperature as compared to germanium. So germanium can able to maintain its characteristics or properties up to 85 degrees centigrade according to the condition. Whereas silicon can maintain its properties or applications up to 200 degrees centigrade. So who should be preferable at high temperature means silicon as compared to germanium. Confirm? So silicon is preferred to use at high temperature. So it can operate even at high temperature. Silicon preferred, sir, silicon should be operate at high temperature as compared to what, sir, means germanium you can call. And so now, 1 minute. So silicon can be used at a high temperature. Silicon can be used at high temperature than germanium. So that is known by some critical temperature. How much it is means, so this is critical temperature is up to 85 degrees centigrade for germanium. And it is up to 200 degrees centigrade for silicon. So up to 200 degrees centigrade for what, sir? Silicon. Sir, the germanium body have more conductivity than compared to silicon. But you say that silicon should be preferred because of this. Why the silicon body have less conductivity than compared to germanium? Why the silicon body have less conductivity than compared to germanium means, the main reason for that one is the resistivity of silicon is very high than compared to germanium. So why the body of silicon have lower, why the silicon body have lower conductivity than compared to germanium means, the reason for that is silicon body have high resistivity than compared to germanium. By that, the silicon material look like we have less conductivity than compared to germanium. Even the silicon have a less conductivity, most popular to use in applications as compared to germanium. The reasons are easy to be available in the nature, that is abundant you can call. Minority carrier effect is less you can call, quite a stable element. And as well as what you can call, sir, it can operate easily even at high temperature. It can operate easily even at a high temperature, that is up to what, sir? 200 degrees centigrade for silicon. If it is a germanium, sir, it is up to only 85 degrees centigrade. So that is commonly called as a critical temperature. Commonly called as what? Critical temperature. So because of these reasons, the silicon should be preferred than compared to what? Germanium in semiconductor applications. Confirm? Check out the next question. What is meant by hole you call? Right? So now you can able to examine where do you find the holes. Just now you discuss. So among the three particles of conductors, insulators and semiconductors, holes can be identified in semiconductors. Holes can be identified in what? Semiconductors. Holes do not considered in conductors as well as in insulators. Hole is a current carrier that we find out in the case of semiconductors. In the case of what, sir? Semiconductors. Now check up now what is that hole. Suppose now I take the energy band diagram for semiconductor. This is the energy band diagram for semiconductors. So this is some valence band I call. this is some conduction band, right? So now this is the highest energy, you say EV. So this is the highest energy called EV for valency band. Lowest energy here it is EC for conduction band. So according to this one here, the energy gap is moderate, confirm. The energy gap is nearly around 1 electron volt. It is not much high like insulators, not zero like conductors. It is a small, around 1 electron volt, confirm. Energy gap is not zero, it's small. It should be around 1 electron volt for semiconductors, you say. So because of the energy gap, there is a bondage of electron in the semiconductors. So whenever you want to make the electron to become free, you make that electron to jump to the conduction band. How to jump the electron to the conduction band means by applying the required energy, you call. On applying the required energy, what is the electron who got the required energy can jump into the conduction band like this. So this is the way. So on jumping into the conduction band, it is a free person. The electron can be considered as a free there. So on getting a required energy, right, the electron can jump into the conduction band. So that look like as a free electron. So here, as compared to the conductors, valence and the conduction bands are not superimposed. They are separated, you can call. We have some separation is there, some distance is there. So based on that, you find the loss of electron in valency band. So that loss of electron in the valency band creating a empty place, that empty place is called as a hole. Confirm? So hole is a vacancy that is considered due to the removal of electron from valence band to the conduction band. Hole is a vacancy that is experienced there due to removal of electron from valence band to the conduction band. And because it is considered due to the removal of electron, and according to the law of conservation of charge, it must be a positive charge because it is due to the loss of a negative charge such that it can gain positive charge. Confirm? And this hole is considered in valency band, and this hole can travel very freely in the valency band without any restrictions. The hole can able to move freely in valency band, right? Sir, why that one you can call means here in the case of valency band, the binding conditions, bonding restrictions is only for electrons, not for hole. Even the hole in valency band, it look like a free carrier. Based on that, in semiconductors, you find out the current carriers are electrons in conduction band and holes in valency band, you can call. Got it now? So you don't expect the holes in conduction band. You can expect the holes only in valency band on removal or on loss of electrons from valence to the conduction band. Confirm my option? So these holes even in the valency band, there is no bonding conditions for that. It is completely free and you can travel anywhere in that concerned valency band, you can call. Sir, whenever the electron is returned from conduction to valency band, it can able to collide with a hole, that is called as a recombination. Got it now? What is the electron who entered the conduction band can spend some time called a lifetime, you say. After that, that electron may return to the valency band to collide with the hole. That collision is called as a recombination. And due to that recombination process, it can again regenerate the valence electron there. So whenever the electron can return from conduction to the valency band, you don't expect the hole in conduction band. Holes are always considered by the removal of electron from valence to the conduction band, never from conduction to valency band. Because electrons are originally in valency band, they can move from their original place to the new place. Based on that, you can create the holes. But don't consider that holes in conduction band on jumping of electrons from conduction to valency band. Holes are only caused in valency band on jumping from valency band to conduction band, and you don't expect the holes in conduction band. Confirm now? So hole is a positive carrier of a charge same as 2. What sir means electron like what sir 1.6 into 10 power minus 19 coulombs. And in the case of semiconductor, the current carriers are electrons in conduction band and holes in valency band. Confirm now, students? What I call hole is a vacancy due to removal of electron from valence band to the conduction band. Simple statement. Hole is a vacancy due to removal of electron from valence band to conduction band. And what I say, hole is a positive carrier. It is a positive carrier according to law of conservation of charge. Positive carrier of a charge 1.6 into 10 power minus 19 coulombs. Got it now? So, holes is nothing but purely due to the vacancy considered by the electron, right, in valence band. What is the electron? After spending some time in conduction band, it should return. That is depend on lifetime I call. So, on returning to the valence band, it can collide with the hole and regenerate the valence electron in that area. So, whenever the electron can return from conduction band, at that time you don't expect any hole in conduction band because it is nothing but not a original place. Original place of electron is here. So, it is jumping to the new place. On that removal, it can create the hole. But you don't expect the hole whenever the electron is returning from conduction to the valence band. Got it now? Check out the next one. Distinguish between crystalline and amorphous materials. Distinguish between crystalline and amorphous materials we call. Says for now, so based on the atomic structure, the materials are mainly classified into solids, liquids and gases. Based on the atomic structure, the materials should be classified into what you know, solids, liquids and what you can call gas particles. So what is a solid you know? A solid is a rigid body in which the atoms are kept very close to each other. A solid is a rigid body in which the atoms are kept very close to each other you call. And it's not possible to separate one atom from another atom. A solid is a rigid body in which the atoms are kept very close to each other. And based on the atomic structure of solid, you can find out there are two types of solids. One is a crystalline solid, other one is amorphous solid. Confirm my option. A solid is a rigid body in which the atoms are kept very close to each other. And based on the atomic structure of solid, you find out one is crystalline, other one is amorphous. So solid element can be classified into two things. Crystalline solid, alright. Other one is amorphous. So what is a crystalline solid we call? A crystalline solid is one in which the atoms are kept to what means in a symmetric pattern. So in the case of crystalline solid, the atoms are kept in a symmetric pattern, not in a zigzag manner. So that is called as a crystalline solid. So what is this crystalline solid, sir? It has some symmetric structure I call. So it have a symmetric structure. So the arrangement of atoms not in zigzag manner. The arrangement of atoms must be in a symmetric manner like this. So this is one atom, this is another atom like this. Every atom with respect to the other one is in symmetric position, not in a zigzag manner. That should be called as a symmetric. All atoms are arranged in symmetric condition. Best example of this one you call, that is called conductors. Best example is what, sir? Conductors you call. In the case of conductors, all atoms are maintaining a symmetric structure. By that they have surface charges. That is symmetric. So if I go for amorphous, in the case of amorphous, the corresponding atoms are arranged in unsymmetric pattern. So atomic structure is unsymmetric. Unsymmetric means zigzag. The atoms are arranged in a zigzag manner. Look like a group of cattle in the road. Look like a group of cattle on the road. So the atomic structure is unsymmetric you can call. That is unsymmetric, sir. This is unsymmetric structure you say. Look like a zigzag. The atoms are not in a symmetric pattern, they are should be in zigzag like this. Look like a group of cattle I call. This is the case. Atoms are not in a symmetric manner, they are in a zigzag manner you can call. So best example of this one is insulators. Insulators are amorphous bodies. You call insulators right? So insulators you may find out there. So understand now what are the crystalline and amorphous? So amorphous is unsymmetric structure, crystalline is symmetric structure. So based on the atomic structure, a solid body can further classify into crystalline and amorphous I call. Crystalline solid have symmetric structure, atomic arrangement is in symmetric order, right? Each and every atom in symmetric position with respect to the other. So based on this only, in the case of semiconductors, you can use covalent bond. Covalent bond is only a person that can maintain a symmetric structure in semiconductors. Confirm? So one more is amorphous I call, that is having unsymmetric structure where the atoms are kept in a zigzag manner. Confirm? So in the case of insulators, the structure is amorphous. In the case of conductors, the structure is crystalline. Check out the next question. What is meant by covalent bond? Let us see this one now. What is the bond? Bond is the meaning of transfer of electrons from one atom to another atom to make that atom as a stable. So you know that, right? In order to make an atom to be as a stable, we can carry the electrons from one atom to another atom. Confirm? So there are different type of bondings are there. Suppose if you go for conductors, right? What means metallic bond you can use. If I go for insulators, ionic bond you can use. If I go for semiconductors, you can prefer covalent bond, right? So bonding is the meaning of transfer of electrons from one atom to another atom. So there are different type of bondings based on the different materials. So conductors prefer metallic bond, insulators prefer ionic bond, particularly semiconductors if you go covalent bond. You asked that what is the covalent bond? So covalent bond is what? Covalent bond is one obtained by sharing one electron from a neighbor atom. Covalent bond is one that can be obtained by sharing one electron from a neighbor atom. So conditions are here that neighbor atom may be same or a different type, no restriction for that. So neighbor atom may be any type, no restrictions. But what are the thing you require, sir? Neighbor atoms must be in symmetric position. Neighbor atom not be in random position. Neighbor atom must be in symmetric position and making the bond look like a crystalline structure. And making the bonding look like a what? Crystalline structure. So you can able to share an electron from a neighbor atom of any type we call, but which must be in symmetric position only, not random position. Every neighbor atom can contribute only one electron, not more than one electron. That's the condition of covalent bond. A covalent bond is obtained by sharing one electron from a neighbor atom, right, which is any type you say, but neighbor atom should be in symmetric position. And one more thing, remember now, this covalent bond is nothing but cumulative pattern. Cumulative means it is a continuous structure. You don't find any end in the covalent bond. Covalent bond is a cumulative structure and you don't expect any end in this one. Suppose now I can able to go for some silicon crystal, right? All semiconductors uses covalent bond pattern I call. So now I can able to go for particularly one of that one now, that is now what I say means some silicon crystal. So this is some silicon atom I call, right? And you know somewhat silicon is a tetravalent one. Tetravalent means 4 valence electrons in its outermost shell, right? A silicon atom is nothing but a tetravalent that is having 4 valence electrons you can call, right? And according to the Bohr atomic model, to make an atom stable, each atom should have a minimum of 8 electrons in its outermost shell, minimum of 8 electrons required in the outermost shell, but every silicon atom already having 4 valence electrons in their outermost shell, and each atom require 4 more electrons to make them as a stable. And so now occur the Bohr condition. So an atom to be stable, if it have a minimum of 8 electrons in the outermost, but here silicon are tetravalent I told, everyone is having 4 valence electrons in the outermost already. So each atom need 4 more electrons to become as a stable. So how many each have? 4 valence electrons. So this is one of the silicon atom, like this I call. So all these are the silicon atoms. Suppose I call pure silicon crystal structure, right? So all are tetravalent you can call. Tetravalent means 4 valence electrons. So this is the meaning that that electron belongs to the valence band. It is bonded with the concerned parent atom. So this is the bond structure commonly are indicating. And so now, so each atom 4 valence electrons are indicated there. So how do you get the bonding, sir? Bonding is obtained by sharing of one electron from a neighbor atom, which must be in what? Symmetric position to that. Right? So all these are the covalent, all these are the silicon atoms with respect to their valence electrons are indicated. I want to keep that bonding now. So bonding is obtained by sharing of one electron from a neighbor atom, I call. That neighbor atom must be in symmetric position, I told you. Now I can do one of that. Now I can make that bonding now. Sorry. Now I can make the bonding now. So this is bonding thing and I can do. So now I can make it one of the bond. So I can share one electron from this. Can I get one more electron from the same? Means not possible, call. So you can share one other electron from another atom. Can I get the electron from this one? Means it do not do that because it is not in symmetric position. It's a random position, not possible to contribute. Now I can get here. This is possible. Now I can get this. It is possible. Now I can get this. It is also possible. So this fellow becomes stable. So this process you can continue for the remaining atoms. Like that, you can get the bonding to be this. This is the way of generating the covalent bond. Say so now it is a pure silicon crystal structure. Suppose I can call. Right? And so now. So among this, it is only the person to be stable. Center one is a stable, getting the required 4 more electrons from the neighbor atoms. But the surrounding silicon atoms still they don't stable. They need some more electrons to become as a stable. It requires 2 more. It requires 1 more. It requires 2 more. 1 more. 2 more. Like this. So it is a cumulative structure you can call. It is a continuous process. So that's covalent bond. And on applying energy that is commonly called thermal energy you can call. On applying the thermal energy, the energy given to the covalent bonds goes to be increases. On applying the thermal energy, the energy given to the covalent bonds increases you can call. And when do you find the covalent bonds are broken, sir? The covalent bonds can able to break up whenever it can get a required energy. Whenever it can get a required energy, at that time the covalent bonds can get break up. So whenever the covalent bonds got a required energy, at that time only it can get break up. What is the required energy to break any covalent bond means? That equal to energy gap. That equal to what? Energy gap. So any covalent bond may be able to go into be break up on getting a required energy. That energy must be what, sir, means equal to energy gap. So until that none of the covalent bond can get break up. Confirm now. At room temperature, what is the energy gap for silicon means? It should be 1.12 electron volt. If it is a germanium, it should be around 0.72 electron volt. So it is a silicon crystal. At room temperature, any covalent bond of the silicon should break up if it get a required energy of 1.12 electron volt. That's the case. Confirm on this. So what is the covalent bond I call? See so now. Covalent bond is obtained by sharing one electron from a neighbor atom. So now sharing one electron from a neighbor atom I call, which must be in symmetric position. Which must be in symmetric position I call. which must be in what, sir, means symmetric position. And covalent must be what means crystalline structure and as well as cumulative, I told. It is a crystalline structure, you call. It is a crystalline structure. Confirm? And is cumulative, you say. Cumulative means no end, you find out. The bond is continuous one without end. Right? And what is the minimum energy required to break a covalent bond means that equal to energy gap. Minimum energy required to break any covalent bond equal to energy gap, you call. Minimum energy required to break covalent bond is its energy gap. Right? Understand this? So that is about covalent bond equal. Now check out the next one. What is meant by valence electron equal? Now I can able to go for next of that. What is meant by valence electrons? So this is commonly used word in the case of atomic structure equal. So valence electrons are those in the outermost shell of an incomplete atom. So when according to the Bohr atomic model, how many electrons are there in the outermost shell of an incomplete? Those are called as a valence electrons. I think that you know, based on the number of valence electrons, the materials are mainly classified into three types. Primary classification: trivalent, tetravalent, pentavalent. A trivalent atom in its outermost shell of incomplete have 3 valence electrons. A tetravalent atom in its outermost shell of incomplete have 4 valence electrons. A pentavalent atom in its outermost shell of incomplete have 5 valence electrons. Understand now? What is the valence electrons? It is the number of electrons in the outermost shell of an incomplete atom. Suppose if the outermost shell is complete, then the valence is 0. If the outermost shell is complete, then the valence is 0. So who is that one means? That is inert gas particles like helium, neon, xenon, argon. All these are the inert gas particles. In that the outermost shell is complete and for which the valence number is 0. Right? For other atoms, their valence is non-zero. And how they become stable means by means of the bonding. By means of what? Bonding. And so now, so what is the valence electrons means? It is the number of electrons in the outermost shell of an incomplete atom. If the outermost shell is complete, valence is 0. Example is what I call inert gas elements. Other than this, all remaining are what sir means outermost shell is not complete, they are unstable, you can call, and there the corresponding electrons you may get back by means of the bonding. Confirm? What are the valence electrons? It is the number of electrons in outermost shell of an incomplete atom. Outermost shell of what, sir? An incomplete atom we call. Incomplete atom. That should be called valence electrons. Right? Suppose if the outermost shell is complete, the valence is 0. Example I call inert gas particles. So whenever the valence electrons are there, how to make the atom to be stable means by means of bonding. Based on the number of valence electrons, the materials are mainly classified into what you know, trivalent, tetravalent and pentavalent. Trivalent atom, tetravalent atom, pentavalent atom. A trivalent atom have 3 valence electrons. A tetravalent atom have 4 valence electrons. A pentavalent atom have 5 valence electrons. And so now these things, okay. Check out Next one. What is the effect of temperature on conductors, insulators and semiconductors we call? What is the effect of temperature on conductors, insulators and semiconductors we call? So now you can able to examine that. First of all, conductors. Conductor is a good metal, I told, in which the electrons are the free carriers, right? All electrons are free and they can able to move anywhere in the crystal lattice, I told. But according to the condition, conductors have positive temperature coefficient of resistance. Conductors have positive temperature coefficient of resistance. What is the meaning of positive temperature coefficient of resistance? Means as the temperature increases, the resistance of conductors goes to be increases. As the temperature increases, the resistance of conductor going to be increases. How do you say it is? Suppose in the case of conductors, all are free electrons. Originally they can move randomly in a given body. How do you make all the electrons to move in one direction? Means that is called drifting all electrons in one direction. How do you drift all the electrons in one direction? Means by the applied source. With application of some source of energy, same. The electric field is acting there, thereby electric force is acting, and thereby all electrons are moving in one direction. But even all electrons are moving in one direction, but they don't have the same velocity. See this one now. Suppose this is a conductor I call. Confirm. So this is the terminals of conductor. You apply some source of energy. That is some battery of V volt we call. So this is a positive charge surface. This will be a negative charge surface. So electrons are repelled by negative charge surface and attracted to be like this. So electrons are moving like this. This is the direction electric field is acting. This is the direction force is acting on that. So electrons are moving like this. All electrons are moving in only one direction. So without applied source, they can move randomly. But on applying the source, all of them moving in one direction. But he said that even all electrons are moving in the same direction, they don't have the same velocity. They have different values of velocity. That velocity is commonly called as a drift velocity, you can call, and that is always be uniform velocity. Why you say that electrons are moving with different velocities? Means because force is not be same on all of them. Force direction is same, but amount of force is not be same on all electrons, because field is not be distributed equally on all carriers. Electric field may not be distributed equal on all carriers. Based on that, force is not be same on all carriers. Even all are moving in one direction, they can move with different velocities. So once they can move with different velocities, commonly there is a chance of collision. Whenever there is a collision is there, their velocity drops. Because of that collision process, their velocity fall down. And due to collision process, the collision process can able to increase the temperature, heating effect cost. Temperature increases. So in the case of conductor, temperature increasing means there is an increased condition of collision effect between the electrons. So based on that, their velocity drops. Velocity drops means they need more time to reach the other end. Time required more. Time increases means automatically the current comes to reduces. In a given time, the conductivity reduces. According to the Ohm's law, current decreases means resistance increases. R equal to V by I. R equal to what, sir? V by I. That's a condition for it. So in the case of conductors, as the temperature increasing means there is an increased collision effect between the electrons, because all electrons not be moving with the same velocity. So due to this increased collision effect, the body temperature increases. Automatically that collision effect makes that velocity drops, time is more, transit time is more, current decreases, resistance increases. So first one of that, conductors have what, sir? Positive temperature coefficient of resistance. Conductors have positive temperature coefficient of resistance. Confirm? That is what you say, R proportional to T. This is for conductors. Come back. Now I can able to go for insulators. How the effect of temperature in insulators? Insulator is originally what, sir, means non-conductor you can call. In the case of insulators, the energy gap is very high. In the case of insulators, the energy gap is very high. Under normal condition, in the case of insulator, no electron can move from valence to the conduction band. So this is an insulator body. Suppose I call, this is the band diagram for insulator, valence band. This is the conduction band. Energy gap is very high, I call. This is for what? Insulators. Band diagram for insulators. Insulator band diagram I call. Confirm. So based on that, under normal condition, no electron can become free. So conduction band is empty. So in the case of insulators, ideally the current is 0 means resistance tends to infinity, can call. Resistance tends to infinite. Commonly it is called a non-conductor. Suppose if you are a person, you are applying this much high energy. If you apply this much high energy, very few of the electrons may jump into the conduction band. Very of the few electrons may jump into the conduction band and causing a very small conductivity of current. Under normal condition, no electron can jump into the conduction band. Conduction band is empty, so current is 0, so that resistance is infinite for insulator. If I go for higher application of energy, this much energy if I apply, so very few electrons may goes to the conduction band. Very few electrons may goes to the conduction band and look like act as a free. Very small number of electrons may goes to the conduction band and look like become as a free, can call. Got it now? Very few number of electrons can go into the conduction band and become as a free. By that, I get a very small current. That current is of no use originally. So on applying a high energy like this, suppose if you go for a diamond, energy gap is 6 electron volt. If I apply this much high energy, I find out very few number of electrons can become free and causing a small current. With that current, I write resistance somewhat decreasing from infinite to somewhat high value. So instead of infinity, you may say that it is now become high. So on applying high energy, few electrons can become free, causing small current, making to decrease the resistance from infinite to high value. But you see this one now, applied energy is more, conductivity is less. Means most of your applied energy is wasted as a heat. Now, so you don't get a proportional conductivity for applied energy. Among your applied energy, most of energy is wasted, right? Because the amount of conductivity is very poor here. So on applying a high my energy, I got very less conductivity, means most of my energy is wasted. Waste of energy applied as a heat, nothing but temperature. So on increase of more temperature, there is a little bit fall in resistance, such that the insulators have negative temperature coefficient of resistance. Confirm now? Insulators have negative temperature coefficient of resistance. Confirm? That is R proportional to 1 by T call. Ideally the resistance of insulator is infinite. On applying a high energy I call, very few carriers become free, causing a small conductivity, making to decrease the resistance from infinite to high value. But most of your applied energy is wasted. Waste of energy is heat, nothing but temperature. So temperature increases, right? There is a more increase in temperature, there is a little bit fall in resistance. The fall in resistance is very less. Anyhow, it have a negative temperature coefficient of resistance. Now I can able to examine the person of what, sir? Semiconductors now. So how the effect of temperature on semiconductors now I can able to examine? Check up the next one of that, semiconductors I can go. If I go for semiconductors, so the semiconductors also have negative temperature coefficient of resistance. How it is means, in the case of semiconductors, the energy gap is depend on temperatures, right? In the case of semiconductor, the energy gap depend on temperature, you say. So what is the meaning of it, you say now? If I go for semiconductor, in semiconductor, energy gap decreases as temperature increases. This is the case. Suppose if you go for the formula of this, Ez equal to Ez naught So this one now, for semiconductor, the formula for energy gap at a given temperature is this one. Eg equal to Eg0 minus beta T call. Where, right, in a case of semiconductor, the main person is energy gap that is decreasing as temperature increasing. What is this, sir? Where Eg equal to energy gap at 0 degree Kelvin, that is original energy gap I call, Eg0 I call. Eg0 stands for energy gap at 0 degree Kelvin, means without applied energy. And Eg equal to what I call? Energy gap at applied energy source of T degree Kelvin. Eg0 is the energy gap of the body at a temperature of 0 degree Kelvin. Eg is the energy gap in the same body at a applied source of T degree Kelvin. Beta equal to constant, you say. Depending on the type of material, you can say. Suppose if I go for germanium, it is 2.2 into 10 power minus 4. It is how much means 2.2 into 10 power minus 4 for germanium. 2.2 into 10 power minus 4 for germanium. If I go for silicon, it is around 3.6 into 10 power minus 4. Confirm? So what is the interrelation with the energy gap means? Now I can able to show that. So as the temperature increases, right, energy gap of a semiconductor come to decreasing, you can call. Suppose if I go for germanium and silicon, particularly this is one now. This is at 0 degree Kelvin. This is at room temperature of 300 degree Kelvin I call. What is the energy gap? Here the energy gap I call Eg0. So for germanium, original is 0.785 electron volt. Original energy gap of germanium is 0.785 electron volt, and at room temperature it come to be 0.72 electron volt. If I go for silicon, original energy gap, right, is 1.21 electron volt. For silicon, same silicon at room temperature become 1.12 electron volt. What is the meaning of this one, you can call? So as the temperature increases, you find out that, so energy gap of a semiconductor reducing. As the temperature increases, you say that the energy gap of semiconductor comes to what, sir? Decreasing, you can call. So temperature increases, energy gap decreases means what the condition of it? So the required energy for making the electron to jump into the conduction band decreases. Confirm my option? So as the temperature increases, the energy gap decreases, you call. What is the meaning of that one, sir? It indicates that with increase of temperature, so the energy gap decreases means the required energy for the electron to move into the conduction band decreases. Already just now you learn. Energy gap indicates the energy required by electron to become as a free. So the required energy reduces. Required energy reduces means then for a given energy, more number of electrons can become free. More number of electrons can become free means current conductivity is more. That's the case. Current conductivity more means resistance decreasing. Confirm now? So because of that required energy gap decreasing, required energy decreases. So for a given energy, you can expect more number of electrons can become free. So that current is more. So that resistance is decreasing rapidly. So according to the practical condition, the resistance of a semiconductor decreases exponentially with the temperature. Resistance of a semiconductor decreases exponentially with the temperature, and it have a negative temperature coefficient of resistance. Confirm? So resistance of semiconductor decreases exponentially, rapidly, you can call, with the temperature. So semiconductor have a negative temperature coefficient of resistance. Semiconductor have what? Negative temperature coefficient of resistance. So this is the formula, one of the formula for semiconductor, R equal to X into e power of minus y by t. Sir, where X and Y are constants. Where X and Y, you are called what, sir? Means constant, you say. So X and Y are constant, so resistance minus stands for decreasing exponentially with increase in temperature. The resistance of a semiconductor decreasing rapidly with increase of temperature, you can call resistance of a semiconductor decreasing rapidly with increase of temperature, you can call. Understand these things? So that is the resistance condition for what means conductors, right, insulators and semiconductors that have what type of temperature coefficient. Means for conductors it is positive temperature coefficient, for insulators and semiconductors it is of what? Negative temperature coefficient, you can call. Confirm now? Check out the next one. Which is the most popular trivalent and pentavalent impurity used in IC technology, integrated chip technology? So already you know just now, depending on the number of valence electrons, the materials are classified into trivalent, tetravalent and pentavalent. Trivalent means number of valence electrons is 3. Tetravalent means number of valence electrons is 4. Pentavalent means number of valence electrons is 5. Suppose if I go for trivalent atom, right, that can have 3 valence electrons in the outermost cell, and what are the examples of trivalent atoms? Means this one using a trivalent atom have 3 valence electrons using, right? Examples of this, you go gallium, indium, boron, all this. Confirm? Gallium, indium, boron, all these are the trivalent impurities. They have 3 valence electrons, you call. If you go for pentavalent, you call a pentavalent impurity have 5 valence electrons. In its outermost cell, the number of electrons is 5. What are the examples of this one? Means, you know, arsenic, antimony, bismuth, phosphorus, all this. Okay. So gallium, indium, boron are trivalent impurities. Arsenic, antimony, bismuth, phosphorus, all are the pentavalent. We asked the question is, which type of trivalent and pentavalent impurities are used in IC technology? While you come back to the integrated chip technology, the most popular trivalent impurity for the fabrication of P-type is what, sir? Means that is boron. Sir, trivalent impurities used in the fabrication of P-type material, you know. Pentavalent impurity is used in the fabrication of N-type material. So N-type semiconductor is obtained by adding a pentavalent impurity to pure semiconductor. A P-type semiconductor is obtained by adding a trivalent impurity to a pure semiconductor, you can call. And who is the most popular trivalent impurity used in the fabrication of P-type semiconductor in IC technology? Means boron. Like that, who is the most popular pentavalent impurity used in what, sir? Means fabrication of N-type in IC technology? Means phosphorus. This one is most popular. This one is most popular. So the most commonly used trivalent is boron. The most commonly used pentavalent is phosphorus. What is the reason? Sir, why don't you prefer the other impurities? Why do you prefer only these two? For trivalent boron, for pentavalent phosphorus? Means among all the other impurities, their energy gap comparatively less. In all trivalent atoms, the boron energy gap is less as compared to remaining. In all pentavalent atoms, as compared to the remaining phosphorus, the energy gap is less. Because of their less energy gap, they need less energy to make the carriers as a free. So already you know that energy gap indirectly indicate the external energy required to make the electrons as a free. So among all the trivalent atoms, the boron energy gap is less, so that they require less energy to make the carriers as a free. In the case of pentavalent, as compared to all other pentavalent impurities, the phosphorus energy gap is less. So less energy gap means, so the required energy is less to generate the carriers as a free. So the most popularly used trivalent impurity for fabrication of P-type in IC technology is boron. Right? In all, as compared to all other pentavalent impurities, the most popular is phosphorus. for the fabrication of n-type. The main reason is their energy gap as compared to the other impurities should be less. So that is the case for that. Okay, so the most commonly popular pentavalent and trivalent impurities, you know. So what sir means? Trivalent impurity is boron, pentavalent impurity is phosphorus. Trivalent impurity is used in the fabrication of what sir means p-type, and a pentavalent impurity is used in the fabrication of what? N-type you can call. The main reason is as compared to other impurities, their energy gap is less you can call. And so now these things. Hi, you discuss the next question now. Why intrinsic semiconductor has poor conductivity call? Let us see this one now. Why the intrinsic semiconductor like germanium or silicon, whatever it may be, how the poor conductivity. So fundamentally, you know that without any applied energy source, in the case of intrinsic semiconductor, none of the covalent bonds are broken, right? No covalent bond is broken without any applied energy. On applying some source of energy, the covalent bonds able to break up, you know, on getting the required energy. What is the required energy to break any covalent bond means that required energy to break any covalent bond is equal to the energy gap. Whenever a covalent bond broken, according to the condition, what you say means electron hole pairs are generated, right? For each covalent bond breakage, you are getting one electron hole pair. So depending on the number of covalent bonds are broken, that number of electron hole pairs are generated. So in the case of intrinsic semiconductor with applied energy at a given instant, how many covalent bonds are broken, that number of electron hole pairs are generated. So always number of electrons should be equal to number of holes. So you are getting the current by electrons and current by holes. And in the case of intrinsic, number of electrons equal to number of holes. Their charge is the same, number is the same, and both generated at the same time. So that the current by electron and hole should be equal, but opposite in polarity, the total current becomes zero. The total current become what? Zero. Suppose this is the pure semiconductor of silicon you call. Now I take some bond, covalent bond, you know somewhat. This is the silicon crystal. Already know that semiconductor uses covalent bond structure, you know. Semiconductor uses what, sir? Covalent bond structure, you know, right? So this is the covalent bond pattern of silicon crystal, you know. This is the covalent bond structure for silicon crystal, right? So whenever a covalent bond broken, what I told means the electron hole pairs are generated. This is called as a thermal generation of electron hole pairs also you can call. It is also called as a thermal generation of electron hole pairs. What is the required energy to break any covalent bond means? I told that required energy equal to the what sir means energy gap. Suppose for silicon crystal, you know, at room temperature, the energy gap is around 1.12 electron volt. So with applied energy source, any of the covalent bond got required energy of 1.12 electron volt, it can able to break up. So like this. Suppose now I can apply the energy. On applying the energy, like that is called thermal energy, called KT. Unit for that one is electron volt you can call. Whenever any of the covalent bond broken, among this electron pair, only one of the electron can come out as a free. Don't say both electrons come out as a free. Why you say only one of the electron can come out as a free means, so if both electrons come out as a free, none of the electron is there, indicating that no bonding. So the bonding is maintained as long as the electrons should be there. If I say that both electrons should come out, under that condition you don't expect any bonding there. So bonding is not possible means the structure is not possible, crystal get collapsed. So according to the condition, whenever a bond broken among the electron pair of covalent bond, either of the electron can come out as a free. Don't say both. Either one may come out as a free. Suppose I say that this is the electron that come out as a free. This is called a free electron, which is outside the bond, that belong to the conduction band, right? So what is the electron which is lost inside the bond, represented by what sir means empty place. That empty place is nothing but what you can call hole. Hole is a vacancy that is due to the removal of electron, you know, that should be called as a hole. So this is the hole. So the breakage of every covalent bond give up one electron and one hole as a free. So in the case of intrinsic semiconductor, how many electrons are generated as a free? The same number of holes also be generated, such that electron current should be equal to the hole current but polarity opposite, so that the total current become 0, such that intrinsic semiconductor has poor conductivity can call. How do you improve the conductivity? Means that can be made by making either electron or hole to be excess. How do you make electron or hole to be excess? Means that to be done by adding of some impurity. The process of adding impurity is called as a doping, you say. The process of adding impurity is doping. Confirm now? Think, understood now? In intrinsic, number of electrons is equal to number of holes. So both can participate in current you call, but both the number is equal, so that total current by both electrons and holes you can call, total current is 0. So intrinsic semiconductor has a poor conductivity can call. How do you improve the conductivity of semiconductor? Means adding some impurity. The process of adding impurity is called what you can call doping. Understand on this? Check out the next question now. What is meant by direct band gap and indirect band gap semiconductors? What is meant by direct band gap and indirect band gap semiconductors you can call? So based on the energy gap condition, you may find out two type of semiconductors. One is a direct band gap, other one is a indirect band gap semiconductor. First come to the direct band gap semiconductor. If I go for direct band gap semiconductor, the maximum energy level of valency band and the minimum energy level of conduction band should be aligned. So both should be in the same position. So the carrier can able to move from one band to the another band without changing any K factor, nothing but momentum factor. Without changing any momentum, the carrier can easy to carry from one band to the another band. So that is type of semiconductor is a direct band gap semiconductor you can call. And in the case of direct band gap semiconductor, the radiation come out in the form of a light, right? Best example, you know, LEDs, laser beams, all these things. And so now in the case of direct band gap semiconductor, this is the case I say. This is the valence band you can call, whose maximum energy it is. Confirm? And this is the conduction band you call. This is the conduction band I say. So this will be the conduction band you can call. This is the minimum energy level of the conduction band you can call. You observe now the maximum energy level of valency band and the minimum energy level of conduction band should be aligned. So should be in the same position you can call. So what he says, what are the carrier? Suppose here electron you can call. So that can able to move from valency band to the conduction band without any changing momentum. Without any changing momentum you can call. The electron can able to move from valence band to the conduction band without any changing momentum you say. And in the case of a direct band gap semiconductor, the radiation should be come out in the form of what sir means light energy. It can radiate the energy as a light. And as compared to the indirect band gap semiconductor, in the case of direct band gap semiconductor, the carrier lifetime is less. So in the case of direct band gap semiconductor, the carriers have a very less lifetime. What is the lifetime means? I think that you know, lifetime indicate the time for which the carrier can stay before recombination. So that lifetime is less in the case of what? Direct band gap semiconductors. So this is the direct band gap semiconductor you call. Confirm? Best example of the direct band gap semiconductors, you know, gallium arsenide, gallium phosphide, gallium nitride, all these are the examples of the direct band gap semiconductors. They are very good for light conductivity and they are very poor for current conductivity. They do not prefer for current conductivity you can call. Here the radiation comes in the form of what? Light energy you can call, right? So examples is gallium arsenide, gallium phosphide, gallium nitride, all these are the direct band gap semiconductors. One more is indirect band gap semiconductor. As compared to the direct band gap semiconductor, in the case of indirect band gap semiconductor, the maximum energy level of valency band, the maximum energy level of valency band and minimum energy level of conduction band should not aligned. This is this. So this is the maximum energy level of valence band you can call. Confirm. This is the minimum energy level of conduction band you say. The maximum energy level of valence band and minimum energy level of conduction band both do not be aligned. Both are not be same position. So indicating that a carrier can able to move from one band to the another band with changing momentum. With what? Changing momentum we can call. That is called as a what sir means indirect band gap semiconductor you can call. In the case of indirect band gap semiconductor, the charge carrier can able to move from one band to the other band with what sir? Changing momentum you say. So as it is without changing momentum, it's not possible to jump. So must and should you can able to make the carrier to move from one band to the another band with the changing momentum you say. And here the radiation of the energy should be comes out in the form of a heat, that is nothing but gives current. So they are very good for current conductivity, not good for light conductivity can call. Best example, you know, direct band gap, indirect band gap semiconductors are what sir means germanium and silicon. All these are the indirect band gap semiconductors. So this is a indirect band gap semiconductor. Confirm. Indirect band gap semiconductor you can call. This will be the direct band gap semiconductor you say. Observe now what the thing you discussed. So in the case of direct band gap semiconductor, the minimum energy level of conduction band and maximum energy level of valence band should be aligned, so that you can able to make the carrier to move from one to the other band without changing momentum, without changing k vector. K vector means momentum vector recall. So there the radiation gives what sir means light energy. Examples I told gallium arsenide, gallium phosphide, all this. But as compared to the indirect band gap semiconductors, in the case of direct band gap semiconductors, what the thing I am saying now here, so the lifetime should be less. So as compared to the direct band gap, indirect band gap semiconductors should have some more lifetime you say, where the carriers must also travel with the changing momentum from one band to the other band, and the radiation gives some heat energy like current conductivity call. Here the examples of this one is what sir? Germanium, silicon, all these are indirect band gap semiconductors. Understood now? So now what is this? In direct band gap semiconductor, confirm, the maximum energy level of valence band should be aligned with minimum energy should be aligned with what sir? Minimum energy level of conduction band, so that a carrier can move from one band to the other band without changing momentum. Without changing momentum. That is called direct band gap semiconductor. And its radiation gives what I told you, light energy it gives. Example is nothing but gallium arsenide, gallium phosphide, all this. Example, you know, gallium arsenide, gallium phosphide, all these are the cases. Right? Here the radiation comes as a light energy. Suppose if you go for indirect band gap semiconductor, right? This is a direct band gap you say. In indirect band gap semiconductor, okay, if I go for an indirect band gap semiconductor, what the thing you can call, there these two are not aligned. Confirm now? The maximum energy level of valence band do not align with minimum energy level of what? Conduction band. So the carrier can able to move from one band to the other band with the changing momentum. So that a carrier can move what, sir? With changing momentum. And the radiation gives us a heat energy call, like current conductivity may get. Example is nothing but what you can call germanium, silicon, all these are the indirect band gap semiconductors you can call. And if I compare the lifetime of direct and indirect band gap semiconductors as compared to the direct band gap semiconductor, in the case of indirect band gap semiconductor, right? In the case of indirect band gap semiconductor, the lifetime somewhat more you say. So this is the direct band gap semiconductor, right? This is the indirect band gap semiconductor. Can one of these things? Check out the next question. What is the net charge on a semiconductor? You are asking that what is the total charge on a given semiconductor? According to the fundamental condition, any semiconductor, that may be either intrinsic or extrinsic of N type or P type, anything you take, any semiconductor is electrically neutral. Any semiconductor is electrically neutral means the total charge on any semiconductor should be 0. The total charge on any semiconductor is 0. Suppose now I can take some N type semiconductor. Now I take some N type semiconductor. Suppose for N type semiconductor I take, how to get N type semiconductor, you know, right? N type semiconductor is obtained by adding a pentavalent impurity to a pure semiconductor, you know. N type semiconductor is obtained by what? Adding a pentavalent impurity to a pure semiconductor, you call. Sir, the addition of every pentavalent atom make one electron to be excess. The addition of every pentavalent atom make one electron to be excess. So that excess electrons should be donated by the pentavalent atom. By that pentavalent atom is also called as a donor impurity. So the addition of every pentavalent atom make that one electron to be excess and which should be donated. So a pentavalent impurity atom is added to donate an electron so that it can gain a positive ion or it can gain a positive charge. Right? So in the case of N type semiconductor, what you can call, sir? For every excess electron, there is an associated positive donor ion is there. Suppose, depending on the number of pentavalent atoms you are adding, that number of electrons are excess. That number of electrons are excess. This is one like this. All these are the excess electrons I call. So how many excess electrons means that depending on the amount of impurity added. Right? So for every excess electron, what I told means there is an associated, what sir means, donor, or there is associated positive ion you call. There is an associated positive ion, right? For every excess electron, there should be an associated positive ion you call. So there should be associated positive donor ion. Because this is the atom made to donate an electron. According to the law of conservation of charge, charge can either be created nor be destroyed, you can call. So because this is an electron to be donated, so for which there is an associated positive ion is there. So this positive ion I indicated within a circle because its position must be fixed. And it is most important person in the case of a PN junction that look like act as a barrier. So this is the positive donor ion you say. Confirm? So for every excess electron, there is an associated positive ion is there. And now suppose if I apply thermal energy, how many covalent bonds are broken? That number of electron hole pairs are generated. So how many electrons are additionally generated? That same number of holes are also be created. So that can also be balanced. So that any semiconductor is totally electrically neutral. Confirm my option. So by the addition of impurity, how many excess electrons are there? That number of positive ions are there. They are balanced. With the applied energy, how many covalent bonds are broken? That number of electrons become additional as a free, and same number of holes are also be get as a free. That can also get balanced. So any semiconductor that may be either N type or P type or intrinsic semiconductor is totally electrically neutral. Means net charge on any semiconductor is 0. Confirm now? So no net charge on any semiconductor of intrinsic and extrinsic semiconductor. Confirm now? So Excess electrons are balanced by positive donor ions, we call. How many additional electrons by the breakage of covalent bonds? That number of additional holes are there, so that the total charge on any semiconductor is 0, such that any semiconductor is electrically neutral. Convana? The total charge on any semiconductor is 0 and is totally electrically neutral, we call. Right? And that semiconductor is totally electrically neutral, such that the total charge or net charge on any semiconductor is 0. Same thing you also consider for p-type. In the case of p-type semiconductor, the addition of every trivalent atom make one holes to be excess. So for every excess hole, there is an associated negative acceptor ion is there, that is balanced. And due to breakage of covalent bonds in a p-type semiconductor, how many electrons are free? That number of holes are generated, so that again that additional electrons are balanced by additional holes. So there also the total charge is 0. So any semiconductor of n-type or p-type or intrinsic semiconductor is totally electrically neutral. So you call the net charge on any semiconductor is 0, right? Next question I go. What is the effect of temperature on extrinsic semiconductor? This is somewhat useful question. So what is the effect of temperature on extrinsic semiconductor, you call? See this one now. As the temperature increasing, what you can call means additional electron hole pairs are generated with the breakage of covalent bonds. Now temperature increasing means there is a continuous application of energy source. With that, what you find out, sir? So what are the covalent bonds who got energy by the applied source? They can able to break up. So by that you find out additional carriers are generated, you can call. Sir, by that additional carriers, the what he said means not only the strength of the majority, but also strength of the minority carriers increases. Strength of both majority as well as minority carriers is increasing, you call. But whenever you can compare the percent change, nothing but percent increase of both majority and minority, if you compare, which one is more here means the percent increase in minority carriers is more than compared to majority carriers. Thereby, majority to minority carrier ratio should be decreasing with the increase of temperature. At a particular temperature, this ratio should be almost equal to 1, not 100% equal to 1. Almost it look like be 1. Wherever this ratio is almost 1, where the extrinsic semiconductor can become as an intrinsic. So there is a great effect of temperature on conductivity of extrinsic semiconductor. And so now what I told, with applied energy source, as the temperature increasing, additional electron hole pairs are generated by the breakage of covalent bonds. By that, what I told you, for a given extrinsic of n-type or p-type, not only the strength of the majority, strength of minority also increases. But what I told you, the percent increase of minority carriers is more than compared to majority carriers. Thereby, the ratio of majority to minority gradually decreasing. And at a particular temperature, this ratio is almost equal to 1, where the extrinsic semiconductor becomes an intrinsic. So that you can call what, sir, means critical temperature you can call. That temperature is what you can call, sir, critical temperature. Check up this. Suppose now I can able to take n-type semiconductor. Now I take the case of n-type semiconductor. Now I consider the first doping conditions, right? Now I can consider that added impurity now. That is donor impurity there added. Added impurity I go, okay, excess electrons and excess holes. Suppose I am adding one impurity. The addition of one impurity of pentavalent make one electron to be excess. How many holes to be there? 0, nothing. As long as you are adding the impurity, only majority strength increasing, no minority carrier increase, right? Minority carriers not be defined by doping profile. Sir, I can go for 100 pentavalent impurities, indicating that 100 electrons are free, no hole. Now I can able to go for 1000 impurities now. Now 1000 electrons become free, no hole. So as long as you are adding the impurity, that number of electrons are become free, none of the hole is created in the case of n-type semiconductor. So remember now, in any n-type or p-type, so majority carrier density purely depending on the amount of doping you can call. Higher the doping, more will be the number of excess carriers. Lower the doping, less will be the number of excess carriers. Confirm? So now I stop the addition of impurity now. I am stopping the addition of impurity. Now I can able to go for the application of thermal energy now. Now I can apply the thermal energy KT. Now I can apply thermal energy. Now I can call KT use. With that applied thermal energy KT electron volt at a temperature T1, I assume that 100 covalent bonds are broken. So up to now, no covalent bond is broken, just we are adding the impurity. Now I start to apply the thermal energy. With applied energy source at a temperature T1, I assume that 100 covalent bonds of the n-type crystal got required energy to break up. So with that one, how many covalent bonds are broken? You call 100. So how many electron hole pairs are created? Additional means 100 electron hole pairs are created. So already in our hand 1000 electrons are there. Now it becomes 100 additional means total become 1100. Previously 0 number of holes is there, now that number become 100. Got it? So you confirm now in this way, n-type semiconductor, the minority number is holes that are generated by the breakage of covalent bonds with applied source as a function of temperature. Such that somewhat in our diodes BJT, that minority carrier current strongly depend on temperature called as a reverse saturation current. So in n-type or p-type, the source for the generation of minority carriers is the breakage of covalent bonds, and minority carrier number strongly depend on temperature. Confirm? So up to now you don't say that any holes, now you can say that 100 holes, that is due to covalent bonds with applied source as a function of temperature. Now I can go for at another temperature T2, again 100 covalent bonds are broken, I call. Then this number become 1200, this number become 200. Sir, with the breakage of covalent bonds, not only majority strength increasing, minority strength also increases. Majority strength as well as minority strength both is increasing. But which percent increase is more you call means the percent increase in minority is more than compared to majority. Check up now. With applied energy, confirm? With applied energy at a temperature T1 I call. With applied energy at T1, okay, at a temperature T1 degree Kelvin you say, T1 degree Kelvin, percent increase in majority electron is, so I can able to calculate percent increase, changed value by original value into 100, that is 1200 minus 1100 by 1100, right, divided by 1100 into 100. Confirm? So now I can able to calculate the percent increase there. So how much percent in this is 100 by 1100 means 1 by 11 into 100, nearly it is nothing but 9%, around 9% you call. Like that now I can able to go, what is the percent change or percent increase in what sir means? Minority carrier density, now I can able to go, percent increase in minority hole density I go, percent increase in minority hole density now I am saying is, check up now this. So 200 minus 100, that is changed value, 200 minus 100 by 100 initial value into 100%. That equal to 100% you say. Confirm? So majority carrier density changed by 9%, but minority carrier density with the temperature changed by 100%. With this condition, what ESSR means, because as compared to the percent increase of majority, percent increase in minority is more equal, thereby majority to minority ratio reduces. Now, the thereby majority to minority ratio goes to be what? Reducing equal. So as temperature increases, okay, ratio of majority to minority carriers is decreasing equal. Ratio of majority to minority carriers is nothing but what, sir? Decreasing, because percent increase of minority carriers is more than compared to majority carriers, right? And at a particular temperature, that is called critical temperature, and at critical temperature, this ratio, what do you call, is almost unity, you say. This ratio is almost unity. So there, what are the doping is no use, because the extrinsic semiconductor now becomes as intrinsic. So ratio is almost unity means, so what you can call majority carrier number is almost equal to minority carrier number, such that extrinsic semiconductor becomes as an intrinsic semiconductor you can call. So that is the greatest effect of temperature on extrinsic semiconductor. And extrinsic semiconductor can become as, come on now, extrinsic semiconductor can become as what, sir? Intrinsic semiconductor we call. Can become as intrinsic. Understood now this? Sir, how much this one means? Tc equal to 85 degrees centigrade for germanium, sir. The critical temperature Tc equal to around 200 degrees centigrade for silicon. So by this you can confirm who is preferable to use at high temperature, means silicon should be preferable to use at high temperature than compared to germanium. You say. Got it now? Check out the next question. What is effective mass of charge carrier? Check up now. So virtually you know that mass of electron is 9.1 into 10 power minus 31 kg. That is the mass of electron, you know. That's called true mass, right? Rest mass or a true mass you can call. But in the case of a material, what you can call, sir, with applied source of energy, there should be some interaction should be done between the atoms. There is some collisions or interactions should be done between the atoms. So due to the successive interaction between the atoms, the mass of a charge carrier can able to vary. There is a slight changes in the mass of carrier. That variations in the mass of charge carrier is called effective mass, you say. Now, due to interaction between the atoms, there is a deviation in the mass of a charge carrier. So based on that, you may find out the effective mass for a carrier, right? So understand now? So the rest mass of electron, you know that 9.1 into 10 power minus 31 kg. But this mass of the carrier should be varying by the interaction between the atoms. So that resultant is be called as what, sir? Effective mass. What I told you? Due to interactions between atoms, there is a deviation in the mass of carrier. Deviation in the mass of a carrier you can call. Right, called as effective mass. Denoted by Me. Right. Suppose now I can able to go for silicon. See this one now. For silicon, How the effective mass of electron, that is nothing but now I can able to go for effective mass of electron and hole you can call. So effective mass of electron is how much, sir? Means this one you can call 1.08 mn. Effective mass of electron equal to what, sir? Means 1.08 mn you can call. Check up this, just 1 minute. So 1.08 m you say, where m is the original mass of electron, where m is the original mass of electron you can call. So this is the effective mass you say, silicon effective mass. Okay, where m is the original mass of electron, that is nothing but already you know 9.1 into 10 power minus 31 kg. So effective mass of electron for the silicon at room temperature may become like this, 1.08 m. This is defined at room temperature at 300 degree Kelvin. So for the effective mass of hole means that equal to 0.56 m. So in the case of silicon at room temperature of 300 degree Kelvin, the effective mass to be like this. For electron it is 1.08 m. For silicon hole it is 0.56 m you can call. M represents the true mass of electrons. True mass of electron is nothing but equal to 9.1 into 10 power minus 31 kg. At room temperature, due to interaction between the atoms, the effective mass of electron become as 1.08 times the true mass of it you can call. What is the true mass of electron means? 9.1 into 10 power minus 31 kg. So same thing you can also go for germanium also. There where the effective mass of electron equal to around 0.55 m and effective mass of hole is around 0.37 m you can say. And so now, so due to interaction between the atoms, there should be some deviation in the mass of a carrier, that to be called as a effective mass. Next one I go. What is meant by mass action law? So according to the mass action law, this is very useful for semiconductor devices you say. So according to the mass action law, he say that the product of electron and hole densities at a given temperature is constant. Originally, the electron and hole density product mainly depend on temperature you call, and at a given temperature, this product look like to be constant. So according to the mass action law, the product of electron and hole densities at a given temperature is constant you can say. Can you now? So the product of electron and hole densities is mainly depend on temperature. At a given temperature is constant. Confirm? Suppose electron density you can call n, hole density you can call p. Electron density is n, hole density is equal to p you can call, right? And each equal to ni you say, intrinsic carrier density, each equal to ni. Then n into p equal to ni you can call, that is ni square. That equal to constant you call at a given temperature. So this is the most useful formula from mass action law, using which you can define the minority carrier density once you know the majority carrier density. So according to the mass action law, you say that the product of electron and hole densities originally depend on temperature, and at a given temperature this product must be constant you can call. Commonly you say that each of electron and hole density is equal to original density without doping is nothing but intrinsic carrier density you can call, that you say ni. Ni stands for intrinsic carrier density, that should be constant at a given temperature, that should be constant at a given temperature. It is purely dependent on temperature you can call, and each equal to ni means n into p equal to ni square you can call. What is ni there I told? Where ni is the original carrier density without doping you say, intrinsic carrier density, that is equilibrium density you say, mainly depend on temperature. Mainly depend on what? Temperature you say. So suppose for silicon it is around 1.5 into 10 power 10 per centimeter cube. Per unit volume of centimeter cube, the electron intrinsic carrier density of silicon is 1.5 into 10 power 10, sir. This is for silicon. If I go for germanium, that is 2.5 into 10 power 13 per centimeter cube per germanium. So this is the depend on temperature you say, this to be defined at room temperature of 300 degree Kelvin. Confirm? Now I say that this is the relation should be hold very useful. What for means minority carrier density. Suppose if you go for what sir means n-type semiconductor, if you go for n-type semiconductor, there you are adding donor impurity sir. There you are adding what? Donor impurity you call. So in the case of n-type semiconductor, you are adding what means donor impurity. So with the addition of donor impurity, number of electrons should be excess you can call. So see this one now, for n-type you say net electron density n equal to original density before doping is Ni, and with the added donor impurity become Nd. This is the net electron density sir, where Ni is the intrinsic carrier density, Nd is nothing but donor density you can call. But according to the doping profile, he say that Nd must be greater than Ni. This is the condition of doping sir. Nd must be greater than Ni. Nd stands for how many number of donor atoms added per unit volume. As compared to the intrinsic carrier density, Nd must be greater than Ni you can call. Then what you can say means N is close to Nd. So in the case of n-type semiconductor, the majority carrier density directly depend on the amount of impurity you can add. That is N proportional to Nd. Got it? Who is the minority carrier there? Holes. And minority hole density to be defined by mass action law. Like this. Minority hole density defined by mass action law, that is P equal to Ni square by N. What is that N? N is nothing but equal to Nd equal. So Ni square by N means Nd. So he say that P proportional to 1 by Nd. So remember now, by what value the electron density excess, the same value the hole density become in excess. By what value the electron density become excess, the same value by which the hole density become in excess, such that according to the mass action law, so what you say sir means by what value one of the carrier density increasing by doping, the other carrier density decreasing by the same value, to keep that the total product remains constant. Suppose if you go for intrinsic semiconductor, electron and hole densities are equal and each equal to 50%. Suppose if I add some pentavalent impurity of n-type, so electron density is excess by 20%, become as a 70% I call. Then the hole density become in excess by 20%, look like a 30% you say. So total product must be same. That's the indication of this mass action law, so that in any semiconductor, the total probability of both electrons and holes must be always 1. 1 stands for 100% you say. So the total probability of both electrons and holes in any semiconductor should be equal to 1. So that is about the mass action law. Confirm? Next one I go. The thermal equilibrium concentration of electrons and holes are N0 and P0 respectively. So that is the original electron and hole densities without adding any impurity, all that. So electron density is N0, hole density is P0 equal. If after doping they are N and P respectively, they are after doping N and P respectively, what is the relation between them you call? What is the relation between them you can call? What is the original electron and hole density here? N0 and P0 means, this is that one means, electron and hole density is nothing but N0 and P0 sir. This is their product. After doping, it become as what sir means? N into P equal. That product is N into P. Just now you discussed that according to the mass action law, the product of electron and hole densities always be constant you can call. So what is the product of electron and hole densities before doping? N0 P0, and is equal to their product after doping. So N0 P0 is always equal to N into P. Confirm now? By doping one to be excess, other one to be in excess you can call, but product remains the same. That's a condition. So what is the relation between them means N0 into P0 equal to N into P you can call. Confirm now? That's just the mass action law. So what are the conditions sir? The product remain constant before and after doping. What is the product before doping? N0 into P0. After doping it becomes N into P. That should be changing. According to the mass action law, product remains unchanged. This is the case. So the relation for this one is N0 P0 equal to N into P you call. Understood now? Check out next. How the Fermi energy in intrinsic and extrinsic semiconductor. So this is one of the critical thing. So Fermi energy is commonly called as a characteristic energy, you can call. So using the position of Fermi level, one can define which carrier have more probability in a semiconductor. So Fermi energy is commonly called as a characteristic energy, you can call, that indicate the probability of occupancy of charge carrier. That indicate the probability of occupancy of charge carrier, you say. So Fermi energy is a characteristic energy that indicate the probability of occupancy of charge carrier. Suppose now this is the band diagram, energy band diagram of a semiconductor. I go confirm. This is the valence band, you know. This will be the conduction band. And so now this would be the conduction band. So what is the highest energy of the conduction band? Means plus infinite. Here it is minus infinity call. Highest energy here you call EV. Here lowest energy is called what? EC. So this is the forbidden energy gap, you say. So now let us see this one. Now suppose if the Fermi energies are the center, both electrons and holes have equal probability. Holes are in valence band, you know. Holes are the carriers in valence band. Electrons are the carriers in conduction band, you know. If the Fermi energy is near to the conduction band, electron probability is more. If the Fermi energy is near to the valence band, hole probability is more. So using that you can identify what type of semiconductor it is. Understand my option? So Fermi energy is always it is a characteristic energy that represent what? The probability of occupancy of a carrier. Confirm? It is a characteristic energy. Confirm? That represent the probability of occupancy of a charge carrier, you say. So that always represent the probability of occupancy of a charge carrier. Suppose for intrinsic you go, where electron and hole almost have equal probability, you know. So for intrinsic you write like this. For intrinsic semiconductor, what is the Fermi level you can call? EFI I say. So Fermi level I can call EFI, sir. Fermi level of intrinsic semiconductor I call EFI I say. EFI equal to EC plus EV by 2, EC plus EV by 2 minus 3 by 4 KT ln of ME by MH electron volt. What is that ME? Already know. ME and MH defines the effective mass of electron and holes. Suppose if we consider that ME equal to MH, then ln of this factor becomes 0, such that EF equal to EC plus EV by 2, indicating that the Fermi level lies at the center of energy gap. Correct now? So that equal to what you say? EC plus EV by 2 if ME equal to MH. So indicated that for the intrinsic semiconductor, the Fermi level lies almost at the center of energy gap, indicating that the electron and holes have equal probability. Electrons and holes have what, sir? Equal probability, you can call. So Fermi level lies quite at the center of energy gap. Confirm? This is EFI, you say. So this is the case of intrinsic. So if suppose if I go for N type, so depending on the amount of pentavalent impurity you are adding, so the Fermi level lies near to the conduction band, because whole electron probability is more for N type semiconductor. So for N type semiconductor, the Fermi level lies near the bottom of conduction band. This one. This is for N type. So this is the Fermi level for n-type semiconductor. So one can define the occupancy of carrier in a given semiconductor by the position of Fermi level you say. If you go for p-type semiconductor, there whole probability is more depending on the amount of acceptor impurity you are adding. By that, the Fermi level lies near the valency band. This one. This is for p-type semiconductor. Confirm? This is for p-type semiconductor Fermi level. So originally it is here, on adding a donor impurity is shifting towards conduction band. Depending on the amount of donor impurity you are adding, that much Fermi level moves towards conduction band. So in the case of n-type semiconductor, on the adding of donor impurity more, the Fermi level moves very close to the conduction band. In the case of p-type semiconductor, depending on the amount of trivalent impurity or acceptor impurity you are adding, based on that the Fermi level moves towards valency band. So in the case of extrinsic semiconductor, the position of the Fermi level depend on the doping of their impurities. And not only that, Fermi level also depend on temperature. In n-type and p-type semiconductors, so at the temperature increasing, the Fermi level comes towards the center of energy gap. Confirm now? So either in n-type or p-type, depending on the temperature, the Fermi level comes towards the center of the energy gap. And when almost at center of energy gap means that is just you discussed, that is called critical temperature. So increasing of temperature make that concerned Fermi level moves towards center of energy gap. Confirm? And depending on the added impurity, the Fermi level moves towards the corresponding band. If it is donor impurity is more, thereby the Fermi level shift towards conduction band. Acceptor impurity is more, then Fermi level shift towards valency band you can call. So in the case of n-type and p-type semiconductors, the position of the Fermi level is depending on the type of impurity, amount of impurity you are adding, and as well as temperature. As well as what? Temperature. Check up this. So now I can able to indicate for n-type. So for n-type Fermi level below, what sir means conduction band you can call. See so now for n-type. So Fermi level below conduction band sir, that is EC minus EF, that indicate Fermi level below conduction band. Derivative value it is KT ln of NC by ND electron volts, where NC stands for density of the energy states in conduction band, energy density states in conduction band. So the Fermi level depend on both the temperature and the donor density. As the temperature increasing, the Fermi level moves towards center of energy gap. Whereas donor impurity density increasing, the Fermi level moves towards conduction band you call. Suppose if you go for p-type, the Fermi level lies above the valency band you can call, above the valency band. That is you call EF minus EV, that represent Fermi level above valency band. What is the formula for this? KT ln of NV by NA, where NV stands for energy density states in valency band, NA stands for acceptor density, KT is the nothing but thermal energy, T stands for temperature, you know. So here also temperature increasing, the Fermi level moves towards center of energy gap. And as NA increasing, the Fermi level moves towards valency band. And so now these things. So this is the Fermi level that it always indicate the probability of occupancy of the carrier in a given semiconductor, right? Check out the next one. What is a degenerative semiconductor you call? So degenerative semiconductor is what means if the doping is very high, means nothing but added impurity is very high, then the Fermi level of the corresponding semiconductor comes into either conduction band or valency band you can call. If it is a degenerative n-type semiconductor, doping is too high, indicating that the Fermi level lies into the conduction band, not at the bottom of conduction band, it comes into the conduction band you say. If you go for p-type semiconductor of degenerative, where the Fermi level lies into the valency band you can call, and a degenerative semiconductor look like as a metal, act as a metal, where the Einstein relation should not be applicable. One of the Einstein relation is there, d by mu equal to Vt, that is called thermal voltage you say. That Einstein relation is invalid to use in what sir means in this degenerative semiconductors. And so now degenerative indicating what? So here the doping is too high, and there Fermi level moves either into the conduction band or into the valence band, moves into the conduction band of n-type of degenerative, moves into the valence band of degenerative p-type. And this degenerative semiconductor look like as a metal, where the Einstein relation is invalid to use. Confirm now? That is called degenerative semiconductor use. So what I told? In this, doping is too high. Confirm? Doping is too high and it look like a metal, I say. And it look like what? Metal. Confirm? Where the Fermi energy EF, right, is in conduction band, that is a degenerative field. N-type, sir. Degenerative N-type we call, or is in valence band, that is degenerative P-type. Confirm? So it look like act as a metal. You say. That is called as a degenerative semiconductor. Check up now this. What is the drift velocity? On which factors the drift current can depend, you call. What is a drift velocity? On which factors the drift current can depend is asking the next question. Check up now. What is that drift velocity? So you know that either in conductor or semiconductor, the current is caused by the flow of carriers in a given direction. Either in conductor body or semiconductor body, the current is caused by the flow of carriers in a given direction. Suppose even the carriers are free, if they don't move in a single direction, you don't expect the current by all the carriers. Why means, so if they don't move in a single direction means they can move in a zigzag direction, indicating that some of them move up, down, left, right like this. So the current by upward carrier cancelled by downward carrier. The current by left going carrier is cancelled by right going. So cancellation is more, the overall current becomes zero. So even have a plenty of free electrons or anyone, so the current not be possible. Why means, because of they are free, they can move in random direction. So current conductivity considered by all carriers if and only if they move in a single direction. How do you make them in single direction, sir? That to be done by the drifting of the carriers with applied source. Suppose now I take some conducting element of N-type, or suppose conductor body. This is some conductor body I taken. So in which the current carriers are electrons I call, whose length is L meters I say. This body I can apply it to what's some source of energy like this. Confirm? So because of this, what you find out here, with the applied source of energy in the body, what are the current carriers? Suppose I call electrons. So this is a positive potential. So the electrons are attracted by this positive potential and they come like this. So the surface from this electrons are come out. So this look like a positive charge. The removal of electrons make it as a positive charge. So what are the electrons who are attracted by this positive potential? Same time they are repelled by negative potential and go in this side. Means this is the surface become negative charge. Got it? So this surface positive charge, this surface is negative charge. So whenever opposite charges separated over a given length, I think that electric field is very strong. Electric field is caused by the separation of charges over a given length. Electric field is a vector signal. It is always be directed from positive charge surface to the negative charge surface. Got it? Electric field directed from positive to negative charge surface you can call. So with that electric field, the force would be acting on the carriers. What is the force would be acting on the carriers means? That is called electric force. That's be called electric force, you can say. Electric force defined as F equal to QE. That is also called as electrostatic force. So the force is also a vector signal. The direction of the force may be same to the field or opposite to the field. The direction of the force may be same to the field or opposite to the field you call like this. So where it is same to the field means for positive carrier, suppose for a holes, Where it is opposite means for negative carrier, suppose for electrons. So I assume that here the current carriers are electrons. The force must be in a direction opposite means like this. So with the applied source, electric field is acting, by that electric force is acting. By that what he says, sir, instead of making the carriers to move in random direction, the carriers are moving in a single direction like this. Now the carriers are moving in a single direction. So this is called drifting. Now the carriers are moving in one direction, sir. That is nothing but called as a drifting, you call. Drifting means making them to move in only one direction, you can call. Sir, all carriers are drifting in a single direction. All carriers are drifting in a single direction and having a velocity called drift velocity. But according to the practical condition, this drift velocity never be the uniform velocity. Drift velocity commonly considers an average velocity. How do you say average velocity? Why don't you say uniform velocity? Means even all are moving in one direction with effect of force, the force may not be same on all carriers. Why the force is not same on all carriers means the field is not be equal on all carriers. At a given time, one carrier may get more field energy than other. What are the carrier who got more field energy that can express more force and move faster? At that time, what are the other carrier who got less field energy can express less force and move slowly in the same direction? So all are moving in the same direction but with different velocities because the force may not be same on all carriers, because the field may not be distributed equally. Such that drift velocity is always be a uniform velocity. It's never be average velocity, you can call. And so now, so drift velocity is always what? Uniform, always be average velocity only. Never be the uniform velocity you call. And so now, so drift velocity is the average velocity I call. Confirm? Average velocity and is due to the effect of electric force you call. Electric force, carriers can drift in a single direction instead of moving in random directions. So it can drift in a single direction, you say. Understood now this? So this drift velocity mainly depend on the applied electric field. So this is the condition, sir. Drift velocity mainly depend on the applied electric field. Vd proportional to E. The drift velocity mainly depend on what? Applied electric field, where Vd the drift velocity stands for electric field you call. And remove this proportionality by means of a constant. That constant is called mobility. So mobility is a key person, you say that mobility indicate how much is the velocity gained by the carrier with the applied electric field. How much is the velocity gained by the carrier with the applied electric field. Confirm? So drift velocity depend on the applied electric field you can call, and it is interrelated to mobility. Mobility is a person that define the velocity gained by the carrier with the applied electric field. Confirm? And if you compare electron and a hole, which should carrier have more mobility than other, means electron mobility is more than compared to hole. That is a property of electron. Such that if you apply same field energy to both electrons and holes, who can travel faster than other, means electrons can move faster in a given body than compared to holes. Such that electron can cause the conductivity faster than holes. Based on that, wherever the electrons is the carriers, that is mostly preferred than compared to holes, like BJT, NPN transistor, FET and MOSFET, N-channel FET, right? That is the case. Anyhow, you say that the carriers are drifting in a single direction, they define the current, that current is called as a drift current. So, drift current is considered by the rate of flow of charge in a given direction. Drift current is considered by what, sir? Rate of flow of charge carriers in a given direction. And this drift current is a function of applied electric field. Got it now? So, drift current is the rate of flow of charge carriers in a given direction we call. Drift current is the rate of flow of charge in a given direction, right? So I equal to Q by T, say, and it is mainly depending on applied electric field recall. See, so now one of the formula derived one I written now, I equal to NCQ A VD means mu E. This is the formula derived for drift current in the case of semiconductors here, where NC stands for carrier density, Q stands for charge, A stands for area, mu stands for mobility, E stands for electric field, right? So NC stands for carrier density, Q stands for charge, A stands for area, mu stands for mobility, E stands for electric field. So drift current is mainly depend on the applied electric field. Drift current mainly depend on applied electric field, you can call, and this drift current is caused to flow both in conductors and semiconductors. Drift current is caused to flow both in conductors and semiconductors, you can call. Got it now? Check out the next one. What is mobility? On which factor it can depend? So the continuation of the previous one, we asked the question is what is mobility and on which factor it is depend. Just now I told you the mobility of a carrier represent the velocity gained by it with the applied electric field. So velocity gained by it with the applied electric field, that should be called as a mobility I told. Just now I told that Vd equal to mu E, confirm, where Vd is the velocity, mu stands for mobility, E stands for electric field. Sir, mobility of a carrier indicate how much the velocity gained by the carrier with the applied electric field. How much the velocity gained by the carrier with the electric field you call. And whose practical unit is meter square per volt second. So this mobility mainly depend on two factors, depend on electric field and temperature. So electric field and temperature, confirm now, mu depend on mobility, mu depend on what, sir, means electric field and temperature, you say. Electric field and temperature, confirm. Suppose with respect to electric field I am showing like this. With respect to electric field I am showing this, how it is. So this is the mobility of a carrier with respect to the electric field. This is the mobility. Sir, for low field energy, the mobility varies linearly with the field energy. For low field condition, the mobility of a carrier varies linearly with the field energy, you can call. So whenever the field get critical, like this is the critical field, this is the critical field you can call, that is the critical field where you can expect, able to expect what, sir, means maximum velocity, you can call, where you can able to expect the maximum velocity. So thereafter, what you can call, sir, means, this one I call velocity. Drift velocity I can call. So this is the critical field you can call. For lower values of that one now, you say that the velocity is changing linearly with the electric field, you can call. So this is the drift velocity that become max. Once this drift velocity become max, that become as a saturated one, thereafter even the field changing, no change in the velocity you can call. So this is the one of the condition of the mobility, you say. So mobility depend on the electric field, you can call under low field condition. So it can make that the velocity to vary linearly with the field energy. Once the field become critical, thereafter the same that, so velocity remains same or unchanged one, even the field energy changing. So the variation of the velocity with respect to the electric field for mobility conditions I am showing here. And other than this, the mobility of a carrier can also depend on temperature. Mobility of a carrier can also depend on temperature. What is that temperature means? The mobility of a carrier varies inversely with the temperature, you say. The mobility of a carrier varies inversely with the temperature. As the temperature increasing, the mobility of carrier goes to be decreases. Y means temperature indicating that, so collision effect. So all carriers are moving in one direction. Why the temperature increasing means that collision effect you can call. Whenever the carriers are get collide, their velocity drops. Whenever the carriers are collide, their velocity drops. Velocity drops means the mobility come to decreasing. The mobility come to decreasing you call. So temperature increases, the mobility of a carrier goes to be decreasing you say. Understand this? So mobility of a carrier represent the velocity gained by the carrier with the applied field energy. How much the velocity charge carrier can gain with the applied field energy, that should be called as a mobility. That should be called what? Mobility. Confirm now? So this mobility mainly depend on the electric field and as well as what? Temperature you say. So how it depend on the electric field means I told that for low field energy, the velocity can vary with respect to the field as a proportional. Once the field become critical, where the velocity become maximum, thereafter no further change in the velocity. That look like a saturated. And with respect to temperature, you can find out as the temperature increases, the mobility of a carrier goes to be decreases you can call. The mobility of a carrier comes to decreasing with the temperature. And I just now told you, if I compare the mobility of electrons and holes, which carrier have more mobility than other means electrons have more mobility than compared to holes. And which should be mainly preferred as current carriers than others means electrons should be preferred as holes. So electrons are preferred as current carriers than holes. Which one is mostly preferred as current carriers you call? Electrons should be preferred as current carriers than holes. Electrons are preferred as current carriers than holes. The main reason is the mobility of electrons should be greater than mobility of hole. Confirm now? So like that in the case of BJT, NPN transistor is preferred than PNP. In the case of FET and MOSFET, N channel body is preferred over P channel body. The main reason is mobility of electrons should be greater than mobility of hole. Got it now? Check out the next one. If electric field is directed towards right, then how electrons and holes can move? Just now I told that one to you, simple one. See this one now. So due to electric field, electric force is acting I call. Due to electric field, electric force is acting I call. That electric force is F equal to QE I call. And the direction of the force is the same as to the field for holes. Both should be in the same direction. For electrons, it should be in opposite direction I call. So force should be in opposite direction for field, like this. So it indicates that in any body, the electric force is acting in opposite direction to both electrons and holes. Means in any semiconductor, electrons and holes can always drift in opposite directions. What he say means electric field is directed towards right, you can call. Right, he given electric field is towards right or left. As electric field is towards right. Right means like this. Electric field is towards right means then force is like this for holes and like this for electrons. Confirm? So what is the direction of the field? That should be same for hole, opposite for electron. Electric field direction is towards right, you can call. Towards right means force are moving towards right, electrons are moving towards left. That's the meaning. So holes move towards right, and electrons move towards left. So always electrons and holes to be move in opposite directions. This is the case. Holes move towards right and electrons move towards left, you can call. Got it now? Check out the next question now. What is the energy band diagram for the biased N-type semiconductor given below? So this is some N-type semiconductor which is applied with some source of energy. What is the energy band diagram for this? Okay, so Fermi condition for that one you call. See this one now, without any applied condition, what is the energy band diagram of N-type semiconductor like this? For unbiased N-type semiconductor, right? What is the band diagram means? This is the case. This is the valency band. This is the conduction band, you know. And in the case of n-type semiconductor, Fermi level lies near the bottom of conduction band. You know, Fermi level lies near the bottom of conduction band like this. Fermi level lies near the bottom of conduction band, you say. This is the Fermi level. Confirm? This is for unbiased semiconductor. So with the applied source like this become positive charge condition. This become like this. So that in this n-type semiconductor, the electrons are moving towards right. Electrons are moving towards right. So with this applied source, electrons are moving towards right means holes are moving towards left. The Fermi level come like this, right? With applied bias, right? Electrons move towards right there, and holes move towards left. Then what is the band diagram, sir? The band diagram come like this. See this one now? So the band diagram come for this one like this. This is the way. This is EC. This is EV. Right? The resultant Fermi level for that one to be like this. This is the Fermi level. So electrons are moving like this. This is the flow of electrons. This is the holes. Holes are moving like this. Electrons are moving like this. Here electrons are the carriers that are moving like this. Holes are moving like this. Fermi level comes like this for this biased n-type semiconductor. In the case of unbiased semiconductor, this is the band diagram. In the case of biasing of this one, the band diagram come like this. The band diagram come like that. And so know that. So what is the band diagram for that one means that should be like this. So this is the band diagram for biased n-type semiconductor. Confirm? So depending on this, electrons are moving like this option, holes are moving like this. Got it now? Check out the next question now. What is meant by diffusion current you call? Good. So what is meant by diffusion current you can call? You can able to examine what is the diffusion current. So in the case of semiconductor or conductor, current is considered by the flow of free carriers. Anywhere the current is caused by the flow of free carriers. That may be a conductor or semiconductor. Okay. So but drift current you discussed by the free carriers, that to be find out in both conductors and semiconductors. And that drift current always function of applied electric field you call. But other than this, you can also expect one more current. That one more current is what called means diffusion current you can call. That one more current you may call what's a diffusion current. But this diffusion current identified to be flow only in semiconductors. This diffusion current is identified to flow only in semiconductors. You do not find out in conductors. Confirm? The diffusion current never find out to flow in conductors. It always find out in semiconductors. How this diffusion current means? Again you see this one now. This diffusion current can flow even if the applied electric field is not present. Even the applied electric field is absent you call. So even the electric field is not present, so this diffusion current can able to flow you can call. So diffusion current can flow in a semiconductor as independent of applied electric field. As independent of what? Applied electric field. Diffusion current can flow in a semiconductor as independent of applied electric field you say. And this diffusion current mainly depend on concentration gradient. That is what? Non-uniform concentration of carriers. Means the density of carriers is changing from one area to the another area, that to be called as a concentration gradient. So diffusion current is appeared as independent of electric field, and it can flows only in semiconductor, confirm now, and it can present in the semiconductor that has concentration gradient. That is what you can call non-uniform density of carriers. Suppose now I take some p-type sample. This is some p-type sample I taken, whose length is along x-axis. Confirm? On one side of this one I can take higher density, So I can separate this one, some imaginary axis I taken. One side have more density I say. So one side of that one have more number of holes. Doping is more, right? Look like some P plus I call. On the other side, I say that low doping I call. This is high density area. This is a less density I call, like this. Ordinary doping. So completely it is a p-type, but do not have the same amount of doping in all areas. Area to area, point to point, the doping is changing. Point to pointing, the doping is changing. So because of this, the concentration gradient is exist. What is that concentration gradient means? Change in the hole density with respect to length. So concentration gradient exists means the carrots are always move from higher to lower density side without any applied source, like this. The carrots can easy to move from higher to lower density side, look like a waterfall. Water should easy to flow from higher density side to the lower density side, even the applied source is not be present. So this phenomenon is called as a diffusion. This is called diffusion, you say. So diffusion is caused by what, sir? Means the concentration gradient of semiconductor, you say. Concentration gradient of what? Semiconductor. Whenever concentration gradient is present, the carrots can able to move from higher to lower density side. That is called diffusion. So all carrots are moving in only one direction and producing the current called diffusion current. I think that you find out this diffusion current in PN diodes, like P plus N diode or PN plus diodes. And once again, the main important person BJT. In BJT, the main current flow is emitter current flow. That is only due to diffusion principle. Because in a BJT, emitter is a strongly doped, base is a lightly doped, you know. So carriers have a tendency to move from emitter to base, not from base to emitter. So in the case of BJT, the emitter current flow is mainly due to diffusion phenomenon. And why don't you find this diffusion current in the case of conductors? Means in the case of conductors, there you don't have any doping profiles. There the current carriers are electrons, and in the case of conductor, the concentration gradient of electron is 0. Means anywhere the concentration of electrons should be uniform. The concentration gradient of electron is 0 in the case of conductor, such that no chance for a diffusion current in the case of conductor. This current can flow in a semiconductor that to have concentration gradient. It is independent of electric field call. Confirm now? Understand now this? It flow as independent of electric field, you can call. It can flow as, understand now, independent of electric field. Independent of electric field. Got it now? Next, what you say? It is depend on concentration gradient. Concentration gradient means non-uniform concentration of carriers. Concentration gradient. So what are the semiconductor who do have this property? In that only it can flow, not in all semiconductors, sir. So it never appeared in conductors. It appears in semiconductors that do have this type of property. Suppose for holes, this is the formula for diffusion current, sir. I proportional to dP by dx per holes, where dP by dx is what? Concentration gradient I call. So this is the diffusion current, you say. Diffusion current is dependent on concentration gradient. Suppose for holes, dP by dx, where dP stands for change in hole density, dx stands for length. So if you written this one complete formula, means like this, you may get minus QA dP into dP by dx ampere for holes. Confirm? What is this minus? Why do you take minus here? Means minus is not the negative current. Minus indicate that the hole density decreasing as length x is increases. As length x is increasing, the hole density decreases. That's a sign for negative. Negative sign indicate that as length x is increasing, the hole density decreases. That's the meaning of negative sign. So the diffusion current mainly depend on the concentration gradient of the carrier. And what is this dP means? dP stands for a diffusion constant, where dp is what means diffusion constant for hole you can call. dp stands for diffusion coefficient or diffusion constant for hole. Confirm now. Q stands for charge, A stands for area, dp by dx, that is called as a concentration gradient for hole. Like that you can also write for the diffusion current for electron. And you remember again, in the case of semiconductor, electrons and holes always be diffuse in opposite directions. They never diffuse in the same direction. They never diffuse in the same direction. Understand now this one? So diffusion current cause to flow in the case of semiconductors that has concentration gradient. Confirm now? It never appeared in the case of conductors where concentration gradient of electron is 0. And because of this concentration gradient, even the applied electric field is not there. The carriers have a tendency to move from higher to lower density side, that is in only one direction, called diffusion, and produce the current is called as what? Diffusion current. Suppose for hole, I define the diffusion current to be like this, minus qa dp into dp by dx I call, where dp by dx stands for concentration gradient. Change in hole density with respect to length you can call. Right, A stands for area, dp stands for diffusion constant for hole. This is the negative sign. Negative sign indicate that the density of the carriers are decreasing as length is increases. Confirm on this? Check out the next one. What is Einstein relation? Good. What is the Einstein relation you can call? So Einstein relation now to be applied for this semiconductors. According to this Einstein relation, he said that the ratio of diffusion constant, the ratio of diffusion constant, D for diffusion constant, sir, diffusion constant to the mobility of a carrier at a given temperature is constant. This is the formula. So kT by Q, that itself called as a thermal voltage. Because K constant, Q constant, sir, this ratio depend on temperature, sir, and this ratio is nothing but represent the voltage value. Why, sir? D is a diffusion constant, just now I told, whose unit is meter square per second, sir. Mu is a mobility, sir, whose unit is what? Meter square per volt second, sir. If I consider that ratio of these two things, this ratio is equal to voltage, that is called thermal voltage. Vt stands for thermal voltage, you say. It represents the thermal voltage, sir. The ratio of diffusion constant to the mobility of a carrier at a given temperature is constant. The ratio of diffusion constant to the mobility of a carrier, right, is purely dependent on temperature you can call. At a given temperature it is constant, where Vt stands for thermal voltage you can call. So this ratio equal to kT by Q, that equal to thermal voltage. Confirm now? What I told you? The ratio of diffusion constant, and so now to the mobility of a carrier, so mainly depend on temperature you can call, at a given temperature is constant. At a given temperature is constant, you say. Understand now? At a given temperature is constant. Understand now? So that ratio is mainly based on thermal voltage, sir. This ratio is mainly based on thermal voltage. I think that Vt equal to kT by Q you can call, sir, substituting K and Q. K is a Boltzmann constant, Q is the charge, you know, that value equal to T by 11,600 volts. And at room temperature it is, exact value is 25.8 millivolts, sir, at room temperature of 300 degree Kelvin. Got it? At room temperature of 300 degree Kelvin, it is about 25.8 millivolt you can call. And this Einstein relation is not applicable for a degenerative semiconductor, just now I told. So for the degenerative semiconductors, the Einstein relation should not be applicable, you can say, where the Fermi level lies either into the conduction band or into the valence band. For the degenerative body, this Einstein relation should not be applied. So the thermal voltage should be around 25.8 millivolt at room temperature of 300 degree Kelvin. Got it now? Check out the next question. What is the built-in potential due to P graded doped semiconductor, right? So in a P graded doped semiconductor, what is the built-in voltage we call? So originally you see this one now, it is a P semiconductor, suppose like this. This is a P graded doped semiconductor. So terminals are left open. One side is highly doped, other one is lightly doped, like this. Confirm? This is a P plus material. This is a P. So you see this one now, in a P graded doped semiconductor, concentration gradient is there. Concentration gradient is there means 100% diffusion current can flow. So because of the graded doping, diffusion current must and should exist. But you see this one now, according to the condition of electrical, the terminals of the body is open. You know that in the open circuit, the current never flow. Confirm my option? The current never flow in an open circuit body. But you say that according to the phenomenon of diffusion, so because concentration gradient is existing, diffusion current must be defined. But now what I told means, because of the body terminals are open, no chance for current flow. Then how do you justify your diffusion condition there? For that, he say that according to the condition of concentration gradient, sir, diffusion current can flow, but which must be cancelled, he call. How do you say it is cancelled means? So it should be cancelled by some internal current. That internal current is called as a drift current, he call. And already you know that drift current is a function of electric field. So he say that according to the condition of concentration gradient, diffusion current is flowing. It's there. But he said that total current 0. He said according to the condition of concentration gradient, diffusion current is there. But he said that again total current is 0. How he said total current 0, sir? There is a internal current is called, drift current is flowing by means of internal built-in voltage, which establishes some internal electric field. By that there is internal built-in voltage is there that can generating equal and opposite current of diffusion current. So that can generate a current called drift current, you call, that is equal in magnitude and opposite in polarity of diffusion current, so that the total current should be 0. That's called. So what you say, even the terminals are open, right? Originally you told current is there, but the terminals are open, current not equal to current should be 0, sir. How do you say total current 0, sir? For that he answered that. So this diffusion current exists and it should be cancelled by an internal current which is called drift current having equal magnitude and opposite in polarity of the diffusion current, so that the total current should be 0, you can call. You say internally drift current is flowing, but drift current is a function of field. So there is an internal built-in potential is there with this concentration gradient. He say that there is an internal built-in potential. By that internal built-in potential, there is a built-in electric field. That built-in electric field causing internal drift current. That drift current can able to say that of equal value and opposite polarity, making that the total current to be 0. So I taken from high doping side 1 point. This is highly doped area. This is 1 point. This is another point. He said that because of the concentration gradient, in between this, there is a built-in potential is exist. That built-in potential cause up an internal electric field, which we can establish internal electric field. By that internal drift current is flowing. That internal drift current should be same in magnitude and opposite polarity of diffusion current, so that the total current should be 0. So what is this built-in voltage he can call means, check up now, what is that built-in voltage? That built-in voltage he told that VBI he call, that is a built-in voltage you say, VBI equal to VT, VT stands for thermal voltage, sir, ln of P plus by P volt. Suppose both are equal doped conditions, P plus equal to P means this ln factor becomes 0, no built-in potential. Karma. So what understood now? Due to graded doping you call, that is area to area different doping. Doping order changing from one area to the another area, that is called graded doping, right? Diffusion current flows I call. Diffusion current flows, confirm? But the terminals are open And so now terminals are open of the right. Then total current is 0. So this drift current, total current is 0. What is the total current, sir? I drift plus I diffusion is 0. Total current is 0, which means there is an internal drift current, flows, which is same in magnitude, confirm, same in magnitude and opposite in polarity. And so now opposite in polarity of diffusion current. Opposite in polarity of diffusion current, so that total current is 0. Sir, without source, how do you say drift current is there? I say that because of the built-in potential. So this built-in potential due to concentration gradient. So whenever there is a concentration gradient is there, that is graded doping is there, compulsory find out the built-in potential. That built-in potential can able to establish built-in internal electric field. By that internal drift current can flow. Confirm now? What I said, due to graded doping, a built-in potential exists. A built-in potential exists. That formula I written, derived formula it is. A built-in potential exists like this, which can establish an internal electric field. Internal electric field that causes drift current. That causes what you can call internal drift current, you can call. That causes internal drift current. And so now, so what are that? According to the condition of graded doping, diffusion current is there, but because of graded doping, built-in potential exists, which causing internal drift current of same magnitude of opposite polarity than diffusion current, making the total current 0, such that in an open terminal body, the total current should be calculated by 0, you can call. And so now these things. I now will discuss the next question now here. What is a Hall effect you call? Now I can able to check out what is meant by Hall effect. So Hall effect is applicable for conducting materials like conductors and semiconductors you say. And using Hall effect, we can able to identify the relation between magnetic field and electric field you call. Let us see this one now. Suppose I take some current carrying element. Now I show that one in a 3-dimensional axis. So this is some current carrying device I call. Right. I take some current carrying device. So whose length is along x-axis now I can call. Just 1 minute. I take some current carrying device. So this is a 3-dimensional condition I am taking. Suppose now I assume that this body can allow the current along x-axis. So the current should be passing through the body along x-axis I call. And this body I can keep in a magnetic field which is acting along some z-axis. So the magnetic field is kept along the z-axis you can call. Then according to the Hall effect, what you say means whenever a current carrying body is placed in a transverse magnetic field, electric field is induced in a direction perpendicular to both both what means magnetic field and current. Understand now? Whenever a current carrying device is placed in a transverse magnetic field, then what is means the electric field is induced in a direction perpendicular to both current and magnetic field. So current along x-axis, magnetic field along z-axis you call, then the electric field is induced along what means some y-axis you say. This is the electric field. So according to the Hall effect, whenever a current carrying device is placed in a magnetic field, then in perpendicular to both current and magnetic field, some electric field is induced in a direction perpendicular to both electric field and in a direction perpendicular to both current and magnetic field. So what is the importance of this Hall effect? Hall effect is used to calculate the carrier density, mobility of a carrier, and we can also find the nature of the type of body. Right, and what are the type of current carriers? Is it electrons or holes? And the nature of the material, it is a conductor or insulator or semiconductor of N type or P type. All this to be identified using Hall effect you call. Check up what is the Hall effect I call. So when a current carrying element is placed in a transverse magnetic field you call. I think that you know the meaning of transverse magnetic field. Transverse means electric and magnetic field are perpendicular to each other, and once again they are perpendicular to their direction of propagation. That is called transverse. So whenever a current carrying element is placed in a transverse magnetic field, what you can call an electric field is induced. An electric field is induced. Induced means generated temporarily, induced in a direction perpendicular to both magnetic field and current. This is the case you say. So using Hall effect, we can calculate the potential that to be measured between the terminals you can call. So in between the terminals of the body, you can measure the Hall voltage or Hall potential you can call. So in between the terminals of the body, you can measure the Hall voltage or Hall potential. This is that is. So using Hall potential, one can identify what type of material it is and what type of current carriers in it. Check up now this. What is the expression for Hall voltage? That is a derived one I am writing now. So Hall voltage VH equal to, you defined this is BI by rho W, where rho stands for what means so charge density you can call. So BI RH by W you can call, where RH is nothing but what you can call Hall coefficient. B stands for magnetic field, I stands for current, and RH stands for Hall coefficient you can call, and W stands for width of the body, and W stands for what? Width of the body you can call. So says for now here what is the width of the body I show to you. So in this one, so this would be the width of the body. This is the width of the body you can call. Okay. So W stands for what sir? Means width of the body you can call. Sorry. So W stands for width of the body, right? B stands for magnetic field, I stands for the current that is carried by the body. What is that RH sir? RH stands for Hall coefficient you call, where RH equal to Hall constant or Hall coefficient, that is a standard value for a given material you say, that is Hall constant. So Hall constant equal to 1 by rho, when rho is nothing but stands for charge density, that is nothing but 1 by NCQ we call. So whose unit is what sir? Means coulomb per meter cube. So reciprocal of charge density you can call. So reciprocal of charge density is nothing but what sir? Means meter cube per coulomb for this. So charge density unit is nothing but coulomb per meter cube. So reciprocal of this one is nothing but meter cube per coulomb we can call. Right. So What is that NC means? NC stands for carrier density, you say. NC stands for carrier density, number of carriers considered per unit volume. So already for a given material, Hall constant is a standard value you can call. So using Hall effect, one can define the carrier density. One can define what? Carrier density. And if Hall voltage is positive, the type of current carriers are electrons. If the Hall voltage you calculated is negative, the type of current carriers are holes. So using Hall voltage, you can identify the type of current carriers. If it is positive, current carriers are electrons. And if it is negative, the current carriers are holes. And if the Hall voltage 0, no current carrier, that will be look like what sir means insulator you can call. Kanvana? So what I say to you? If Hall voltage VH equal to 0 volt, no current carrier I call. No current carrier. What is the example of that one means? Insulator. Example equal to insulator you say. Confirm? Suppose if VH equal to positive, you say, so current carriers are what sir means electrons. Electrons are the carriers you say. Electrons should be the current carriers. So examples of this one is nothing but N-type semiconductor as well as conductor you say. N-type semiconductor as well as conductor. All these are the examples of this. Suppose if VH equal to negative, we can call, if VH equal to negative, so who are the current carriers means holes are the current carriers. Holes are the carriers you say. And who is the example of that one means that should be P-type semiconductor. Right? And so now this. So using Hall voltage, you can identify the type of current carriers and as well as what type of material it is. And using Hall effect, one can define the mobility of a carrier. What is the mobility of a carrier using Hall effect means? Mu equal to some sigma into RH, where sigma stands for conductivity. Sigma stands for what? Conductivity you call. So using Hall effect, we can also define the mobility of a carrier, where RH already know that is called as a Hall coefficient you say. So mu stands for what means mobility you call. So one can define the mobility of a charge carrier using Hall effect. And what is the unit for mobility you know? That is meter square per volt second. That should be the unit for mobility. Okay, so one can define the type of current carriers as well as one can define the carrier density also using a Hall effect. Mobility of the carrier you can define, type of current carriers you can know, and as well as the nature of the material can be defined by using Hall effect. Okay, check out the next question now. What is the function of the depletion region? Depletion region nothing but potential barrier you know that can be considered on combining P-type and N-type material together. So whenever P-type and N-type materials are combined or added, under that condition of diffusion of P-type and N-type, the barrier should be present across the junction. Barrier should be present across the junction. Suppose now I can able to go for some P-N junction pot. So this is a P-N junction body you call. So both P-type and N-type are diffused together. So the tunnel made from P-type called anode, the tunnel made from N-type is called cathode you can call. And you see this one now, this P-N junctions of two types are there. One is a linear graded P-N junction where the doping order of both P and N sides are same. Right, that is Na equal to Nd, where Na stands for acceptor density of P side, Nd stands for donor density of N side you call. And one more is nothing but non-linear or step graded or abrupt P-N junction is there. There what you find out means the doping order of P and N side is different, where Na not equal to Nd you call. Means either side doping should be more than other you say. Suppose if you go for P plus N junction as compared to N side, P side doping is more. If you go for Pn plus junction, there the doping order of N side is more than compared to what? P side you say. Confirm now? There are two type of P-N junctions are there. One is linear graded junction. For linear graded junction, what you say means Na equal to Nd you can call. I think that you know what is meaning of Na. Na stands for acceptor density of P side, Nd stands for donor density of N side. The doping order of each side is the same. For non-linear or step graded or abrupt junction you call. Step graded or abrupt junction. Confirm? Na not equal to Nd. Acceptor and donor densities are not equal. Example, if you go P plus N junction where Na greater than Nd, right? Next, Pn plus UC where Nd greater than Na. Where what do you call? Nd greater than Na you say. Nd greater than Na. So either Na greater than Nd or Nd greater than Na. So whatever it may be. So whenever you can diffuse p-type and n-type material together, across the junction, the depletion regions should be formed. Across the junction, what do you find out, sir? Means some depletion regions should be formed, right? So check up now. So this is the junction part. Across the junction, you find out some depletion region. So across the junction up to certain portion, the electrons and holes can get recombined. The electrons and holes can get recombined and leaving only ions. Which type of ions are left out on p side? Means you know that those are negative ions are left out on p side like this. And which type of ions are left out on n side? Means some positive ions are left out. So as long as the recombination is going on, in that area the free carriers are cancelled and leaving only ions. Such type of ions are negative ions on p side and positive ions on n side. And the process of this recombination should be continue. What sir means? Until this ions got the enough energy. Once these ions got enough energy, thereby the further recombination of electrons and holes is not be there. So the recombination of electrons and holes across the junction is happen while you diffuse p-type and n-type until these ions got the enough energy. Once they got enough energy, they can oppose the further diffusion of free carriers from p side to n side or n side to p side. So what is this region across the junction? That region is called as a depletion layer. This would be called depletion layer, you say. Right. So here who are there? Holes are there, you know. Here which one is there? Electrons, you know. Confirm. So that are the holes from p side to n side or electrons from n side to p side can able to diffuse until these ions not get the enough energy. Confirm. Once that ions got enough energy, they can stop the further movement of electrons and holes from p side to n side or n side to p side you can call. Confirm now. So what is the job of these ions? This is ions, that is nothing but a depletion region you call. This depletion region do not containing any free carriers. This depletion region do not containing any free carriers. It containing only ions. It has no majority carriers. It has no minority carriers. It is the area of only ions. Such type of ions are negative ions on p side and positive ions on n side. And what is the width of this one, sir? That you can call W, you say total width. The width of the barrier of p side now I can call some WP. The width of the barrier on n side is called Wn you call. So the width of the barrier on p side is Wp, width of the barrier on n side I call Wn I call. And you observe now the function of the depletion region is asking what is the job of this depletion region? Means the depletion region gives an opposition for the diffusion of majority carriers. So the function of the depletion region gives some barrier or opposition for the majority or for the free carriers who try to move from p to n side or n to p side. So the free carriers can able to move from one to the other side of the barrier whenever they find the energy. That energy should be greater than or equal to energy of the barrier. As long as the energy of these free carriers is less than the as long as the energy of these free carriers is less than the energy of the barrier, none of the free carrier can move across the junction. Got it now? The free carriers can make to move across the junction by having energy. That energy must be greater than or equal to energy of the barrier. Until that none of the free carrier can move. So the depletion region gives an opposition for the majority carriers which are try to move from one side to the other side across the junction. And remember now, this depletion region never gives any opposition for the minority carriers who are diffusing. On p side, minority carriers are electrons. On n side, minority carriers are holes. That you find out by the breakage of covalent bonds, not by the doping phenomenon. Already know in n type or p type, the minority carriers are caused by the breakage of covalent bonds with applied thermal energy. And what are the minority carriers, you may say, on p and n side that can easy to move from one to the other side without any opposition by the barrier. So this depletion region, nothing but barrier you call, that gives an opposition only for the majority carriers who try to move from one side to the other side. And one more thing you remember now, this depletion region act as a dielectric body of a capacitor whose edges, one is on p side, other one is on n side. They look like act as a plates of the capacitor. And so now this depletion region considered as what? Dielectric media of a capacitor, such that the p-n junction body have some internal junction capacitance. The p-n junction body have some internal junction capacitance which should be effective at high frequencies, and whose capacitance should be ignored. Nothing but capacitive impedance is very high at low frequency and act as an open circuit. So in the semiconductor device applications like amplifiers, all these things, you know, so the gain should be fall off at high frequencies due to what's internal capacitance that is considered by this barrier. Got it now? What is the function of the depletion region? I told the function of the depletion region gives an opposition, right? Gives an opposition for the carriers who try to move from one side to the other side. Which type of carriers I call? Majority carriers, you say, right? It gives, and so now opposition for the diffusion of majority carriers. Right, majority carriers across junction. And do not oppose the diffusion of minority carriers. What are the barrier? And do not oppose the diffusion of minority carriers. Confirm now? So that is the function of the depletion region you call, and this depletion region look like as dielectric body of a capacitor. And when do you find the majority carriers can move across the junction? Means by having energy, that energy should be greater than or equal to energy of the barrier, you know. So based on that, that required energy should be done by application of external source. That application of external source you may know somewhat called biasing, forward bias, reverse bias, all these things. Come on now. And this depletion region I told you look like to be act as a dielectric body of a capacitor, by that the diode offering some junction capacitance. And so now this next one you check out how the width of the barrier varies with the junction voltage you call. Confirm? So you're asking that how the width of the barrier varies with the junction voltage, that you can able to examine. I told that from the depletion region the barrier width look like to be what, sir? Means on p side WP I call, on n side is what you can call WN. Just I indicate now what it is. So this is the PN junction device. So this is the barrier you call. This is the barrier on P and N sides. So here it is negative ions, you say. Here it is positive ions. So this is the total width of the barrier I call W. Confirm? Here the current carriers are holes. Here the current carriers are what? Electrons. So the width of the barrier on P side is a WP you call. The width of the barrier on N side is called WN I say. He asking that how the width of the barrier varies with the junction voltage. How it is varies with the junction voltage. Already I told you there are two type of junctions are there. Linear graded junction and as well as what, sir? Means step graded junction you say. Right? Sir, width of the barrier varies like this in general. The width of the barrier, right? Width of the barrier, that is W I can call, varies with the junction voltage some Vj I can call. Vj proportion, what, sir? Means W proportional to Vj I can call. Vj stands for junction voltage. So Vj power of N I say. What is that N? Where N equal to 1 by 2 for step graded junction, that is abrupt or step graded junction you can call N equal to 1 by 2, and N equal to 1 by 3 for linear graded PN junction you call. For linear graded PN junction, the corresponding width of the barrier with respect to junction voltage varies to be like this. Vj stands for junction voltage there. So what is this junction voltage? You can examine later, right? So in unbiased circuit, junction voltage is itself barrier potential, and somewhat it is changing with applied bias of forward and reverse bias. Okay, what is that junction voltage value? You can examine later. And what is this N, sir? N stands for 1 by 2 for step graded junction. Look like P plus N or Pn plus junction. And N equal to 1 by 3 for linear graded junction. How do you say this one now? Suppose I can go for step graded junction like this. This is the formula of the width of the barrier. Direct one I am writing. Under root of 2 epsilon Vj by Q into 1 by Na plus 1 by Nd. This is the width of the barrier for what, sir, means step graded junction you call, right? Where Na stands for acceptor density on P side, Nd stands for donor density on N side, Vj stands for junction voltage. What is this junction voltage means? Under open circuit, it's look like a barrier potential only. Under biased circuit, it should be changing. You check up later. Epsilon stands for permittivity of media. So that you see this one now, W proportional to Vj. So proportional to root of Vj it is. W proportional to root of Vj. That is nothing but Vj power of half. So that is for step graded junction. And one more is there for linear graded junction. What the formula of that width of the barrier means like this? So W equal to, one more is nothing but what, sir, means total epsilon Vj by W power of 1 by 3. This is for what, sir, means for linear graded PN junction you can call, right? 12 epsilon Vj by W power of 1 by 3. This is for what, sir? Linear graded PN junction. This is for linear graded junction you say. For linear graded PN junction, the width of the barrier is nothing but W equal to 12 epsilon Vj by W power of 1. So 12 epsilon Vj by A, sorry. So 12 epsilon Vj by A power of 1 by 3 you can call. Sir, what is that Vj stands for junction voltage you can call. So width of the barrier varies with the junction voltage as Vj power of 1 by 3 there. And epsilon stands for permittivity of the media you can call. A is called what, sir, means impurity gradient you can call. A stands for impurity gradient depending on the doping concentration. Depending on the doping concentration you can define. So the width of the barrier for linear graded PN junction to be what, sir, means 12 epsilon Vj power Vj by A whole power of what? 1 by 3. So for linear graded PN junction, the width of the barrier varies with the junction voltage as W proportional to Vj power of 1 by 3 you call. Where A stands for what? Impurity gradient, right? That is purely depending on the doping concentration of P and N sides. So the width of the barrier varies with the junction voltage to be like this, and it to be taken for step graded and linear graded junction to be like this. For step graded N equal to 1 by 2, for linear graded N equal to 1 by 3. So this is the formulas for the width of the barrier of both step graded and linear graded PN junction. Understood now this? Check out the next question. If we connect a voltmeter across the diode terminals, can built-in voltage is measured, we call. Confirm my option. If we connect a voltmeter across the diode terminals, can built-in voltage is measured, we call. Suppose this is a PN diode, right? We say that if we connect a voltmeter across these terminals, can you measure the built-in voltage, we call. If I connect a voltmeter across that, is that voltmeter can measure the built-in potential is asking. So what is the built-in potential? That is nothing but barrier potential you can call. Sir, how do you define the barrier potential means? See, for now, the barrier potential, that is built-in potential VBI equal to VT ln of NA ND by Ni square volts. So this is the formula of barrier potential, that is called built-in potential you can call. So Vt ln of Na Nd by Ni square volt. Sir, it is a person depend on what? So it is depending on, the thing is, one is a temperature, right? Next, doping concentration of both p-type and n-type materials. Doping concentrations, it is depending. So on doping concentration of p and n sides on which it is depending. Next, intrinsic carrier density of germanium or silicon by which the diode is made. So depend on intrinsic density you can call. Intrinsic carrier density, on which also it is depending you call. So these are the key factors on which the barrier potential look like be depending. On which the barrier potential look like be what? Depending you can call. Got it? Suppose, now let us consider for nominal condition, what is the barrier potential? Means you may say that this barrier potential is around 0.3 volt for germanium. Under nominal condition, this value is 0.3 volt for germanium and it is 0.7 volt for silicon. So it is around 0.3 volt for germanium and 0.7 volt for silicon. Under nominal condition we can call, but that value is purely depending on these factors. Let us see this for now. He say that if such a PN diode, if I connect across a voltmeter, so is this voltmeter can measure this voltage, he asking. My answer is what means this PN diode, what is the barrier potential it have, either 0.3 or 0.2, whatever it may be. It do not be measured by the corresponding voltmeter. So what is the barrier potential? It is internal only, that do not be measured by the corresponding voltmeter who should connect it across the terminals. Why sir? Means the internal barrier potential should be nullified or cancelled by the ohmic contact potential. So ohmic contact potential of the body. So ohmic contact potential of anode and cathode here you take. So what is the internal barrier potential should be nullified by this ohmic contact potential of the PN diode. So what is the ohmic contact potential of the PN diode? Should be cancelling this internal barrier potential such that this voltmeter do not measure that built-in potential. Even you connect a voltmeter across the diode terminals, that voltmeter reading is just 0. It do not show 0.3 volt or it do not show 0.7 volt of the diode. Now, so why sir? The internal barrier potential should be cancelled by what sir means? The ohmic contact potential of the PN junction. So for this purpose only, in the case of solar cell is also look like a PN diode, you know. In the case of solar cell, to avoid the ohmic contact potential on P and N sides, we are using what sir means some metallic plates, such that in the case of solar cell, you know that the ohmic contact potential is not there, such that in the case of solar cell, the internal barrier potential should be read by the voltmeter. That is called open circuit voltage for solar cell. There you can read out that one by the voltmeter. But in the case of ordinary PN diode, it should not be possible. The internal barrier potential should be cancelled by the corresponding ohmic contact potential such that voltmeter reading is 0. Got it now? What I am saying? The internal barrier potential understand now? The internal barrier potential, nothing but VBI you call, is cancelled by ohmic contact potential of terminals ohmic contact potential of the terminals we call. So that voltmeter reads how much? 0 volt only. You do not read that barrier potential, sir. It reads just 0 volt only. You do not read that concerned barrier potential. So that should be the answer for that you call. Understand this? Check out the next question now. How the barrier potential varies with the temperature? One more thing he asking. So already I told that barrier potential depending on temperature. One more is nothing but doping concentration of N-type and P-type, and as well as intrinsic carrier density of germanium or silicon I call. He asked that what means, how the barrier potential varies with the temperature you call. Let us see this one now. According to the derivation of the barrier potential, what you can call means, the barrier potential is directly proportional to the energy gap. Barrier potential is directly proportional to what, sir, means energy gap you can call. So directly proportional to the energy gap of a semiconductor by which the PN diode is made. So barrier potential directly proportional to energy gap, and already knows somewhat this energy gap varies inversely with the temperature. So barrier potential directly proportional to energy gap, but energy gap is inversely proportional to temperature. So by this you can confirm, as the temperature increases, the barrier potential decreases. As the temperature increases, the barrier potential decreases you call. And so now, as temperature increases, the barrier potential decreases. So according to the practical condition, he said that this barrier potential decreases by what means around 2 millivolt per degree centigrade. Some reference books it indicated as 2.5 millivolt you call. So roughly you can consider as a 2 millivolt per degree centigrade. So as the temperature increases, the barrier potential decreases around 2 millivolt per 1 degree centigrade. So main reason is this. Barrier potential mainly defined by the right energy band diagram of that one now, energy gap based one. So this energy gap in turn depend on temperature, like this you already know. So that as the temperature increases, the barrier potential decreases. It should be practical around 2 millivolt per 1 degree centigrade. Using this you can write the formula of change in barrier voltage. Change in barrier voltage, like this you may write. Delta VB I call change in barrier voltage. That is commonly written as what means minus 0.002 into delta T volts. This is the formula to calculate the change in barrier voltage with respect to temperature we call. Okay, minus stands for decreasing. So 0.002 indicate it is decreasing around 2 millivolt you can call, 2 into 10 power minus 3. Delta T stands for change in temperature in degree centigrade, where delta T stands for what, sir? Change in temperature in degree centigrade you call. Delta T is what? Change in temperature that you take out in degree centigrades. So the barrier potential depend on the temperature to be like that. It is varies inversely with the temperature. Okay. Check out the next question now. How the electric field distribution in a open circuit PN junction? You are asking that how the electric field distribution is considered for an open circuit PN junction, that is either linear graded or step graded, or it may be. How it is now you can able to go. See this one now. This is the PN junction you call. Either linear graded or step graded, what it may be, sir. This is the open circuit PN junction you say. So barriers should be existing across the junction, right? Barriers should be existing across the junction you call. This is the barrier, suppose. This is of negative ions. This is of positive ions, you know. Right? This is the width of the barrier you call. And so now, so the width of the barrier of P side it is WP. The width of the barrier of N side it is WN you call. Now indicate how the charge distribution, and as well as I can able to go for electric field condition you say. See so now this is the junction, sir. That's a junction you call. Now I can able to take the x-axis is nothing but distance from junction you say. Distance from junction I can able to go. This is the distance from junction. Right? Distance from junction I call. So now I can able to go for, this is a charge density now, rho I call. Rho stands for charge density there. how the charge density distribution, now I can able to go for the barrier first. See this one now, this is the boundary of it. Confirm. So here the charge density is considered by negative ions, you can call. That should be considered by negative ions. So this is considered by negative ions, I call like this. Next, how it is considered by means of the positive ions, I say like this. So charge distribution is linear on both sides, you call. This is considered by positive, this is considered by negative. Confirm on this, right? So with respect to the positive ions, with respect to the negative ions, and the charge density at the junction is 0. The charge density at the junction part is 0, you can call. This is considered by negative ions, this is considered by what? Positive ions. Now based on that, now I can able to indicate what the electric field distribution across the junction I am showing to you. Now indicate the electric field distribution across the junction. This is the case, now I go. Again, this is the distance from junction. This is distance from junction, I go. So this is the junction part, right? So now how the electric field is considered. Now I can able to examine the distribution of electric field on both sides of the barrier with respect to charge distribution. So now I can able to examine that, how it is. See this one now, this is the junction part, you can call. This is the junction part, right? Now the distribution of the charge on both sides of it to be like this. So outside the barrier of P or inside, the electric field distribution is 0. No electric field distribution outside the barrier. Inside the barrier, that should be linear like this. Here the electric field considered by negative ions. Here the electric field considered by positive ions. The electric field goes to be changes linearly, call like this. Distribution of electric field inside the barrier is linear at any point. And once it comes to the junction, there the electric field look like to be maximum. Electric field look like to be maximum at the junction part, and inside the barrier at any point it should be linear variation. The distribution of electric field is linear. Outside the barrier, that is nothing but the electric field distribution is 0. And so now, so for a given PN junction, this is the distribution of the electric field. Here the electric field considered by negative ions. This one, it to be distributed linearly at all points. Whereas here it is considered by positive ions. It is also distributed linear at all points. While you come to the outside of the barrier, the electric field is 0. And at the junction part, the electric field is a maximum, you can call. The electric field look like by maximum. Can you know? And so now what I told? So, electric field outside the barrier is 0. Confirm? Electric field for any junction, it is linear graded or step graded of P plus N or Pn plus any one. Electric field is maximum at the junction, you call. Electric field is maximum at the junction, you say. And inside the barrier, the electric field distribution is linear, you can call. And what is this maximum electric field means? This is the formula you can call. E max equal to sum QA W square by 8 epsilon, where W is the width of the barrier, epsilon equal to permittivity, A is called impurity gradient, I told, depending on the doping concentration. So this is for linear graded, you say. This is for linear graded. And what is this formula for? Other one means, that is either Q NdW by epsilon. This is for step graded of P plus N. For P plus N junction, the maximum electric field like this, Q NdW by epsilon, you call. Suppose if it is P N plus, you can call, that is Q NaW by epsilon. This is for Pn plus junction. Confirm? The maximum electric field to be like this for linear graded, for step graded of P plus N and Pn plus you can call. So it is irrespective of the type of PN junction, that is a linear or step graded junction, the electric field should be maximum at the junction part. And inside the barrier the electric field distribution is linear. Outside the barrier the electric field should be 0. Outside the barrier the electric field must be 0, you can call. For linear graded it is QA W square by A epsilon I call, where A stands for impurity gradient, W stands for width of the barrier. Here same one, W stands for width of the barrier, ND stands for doping concentration on N side, NA stands for doping concentration on P side you say, epsilon stands for permittivity of media. So this is the distribution of electric field in an open circuit PN junction. Confirm? Check out next how the barrier width varies with doping you call. How the barrier width varies with doping, that you can able to analyze how the barrier width varies with the doping. Again I go for now. So this is my PN junction. Confirm? So on both sides you find out what sir means the barrier. So on P side the barrier containing negative ions, on N side the barrier containing what? Positive ions, you know. This is the barrier on a P side of negative ions. Here the barrier containing what? Positive ions you say. So the width of the barrier on P side is a WP, you know. This is a WN. Total width you may call W. So you remember now, while you can consider the barrier on P side holes are cancelled, on N side electrons are cancelled. So while the barrier is formed, there is some recombination of electrons and holes that takes place, you know. By that there is some loss of positive charge by holes on P side, loss of negative charge by electrons on N side. How many holes are lost on P side? Same number of electrons lost on N side. So that you may find out while the barrier is formed, so loss of positive charge on P side, loss of positive charge by holes on P side you call equal to loss of negative charge by electrons on N side, you know. Sir, how do you know this number? You know that on P side doping concentration is Na. Na stands for number of acceptor atoms added per unit volume. What is the junction area? I call A. So on which width the holes are cancelled, not complete one, or width of WP. So this is the number of holes that could be cancelled on P side while the barrier is formed. Where A stands for junction area, WP stands for width on the P side over which the holes are cancelled. Na stands for acceptor density, multiply to the volume. So this is the number of holes that could be cancelled while the barrier is formed. Multiply to charge on each one, that is like this. Similarly on N side, Nd stands for donor density call. Nd stands for donor density. So the number of donor atoms added per unit volume. So the electrons are cancelled over the width of what sir? Wn. So A equal to junction area, Wn is the width where the electrons are cancelled. So this is the number of electrons cancelled on N side into charge. So Q cancelled, A cancelled. So you say that this is the standard formula in the PN junction, NaWp equal to NdWn. So now we can able to generate the formula Wp by Wn equal to what you can call Nd by Na. So width of the barrier inversely proportional to doping. Width of the barrier of P side inversely proportional to acceptor density. Width of the barrier on N side inversely proportional to donor density you can call. So the width of the barrier varies inversely to doping. Width of barrier varies inversely to what sir? Doping you can call. It is a person that to be varies inversely to doping. Higher the doping, lower the effect of the barrier. Lower the doping, higher the effect of the barrier you call. Confirm? So wherever the doping is less, where the barrier effect is more. Wherever the doping is high, where the barrier effect is less you call. Suppose if you go for P plus N graded doped diode, in the case of P plus N graded doped diode, the barrier can be expanding mostly on N side, not on P side. If it is a Pn plus junction, the barrier can expand mostly on P side you call. Mostly on P side. So this is the formula. By that you can define the width of the barrier varies inversely with what? Doping you can call. Varies inversely with the doping. So how can you define the width of the barrier? In terms of the total width also you can discuss like this. Just use this. One more formula for the width of the barrier recall. So this one now. We know that what you call WP plus WN equal to W. Then WP is nothing but what you call W minus WN you call. So can I substitute this one here? NA into WP means W minus WN equal to ND into WN you can call. So if you minimize this, you may get that WN equal to total width into right NA by what you can call, sir, ND plus NA you may get. So this is the formula for width of the barrier on N side in terms of the total width. Not only that, you can also write similarly, what is that WP means? WP equal to W into ND by ND plus NA. So in this way you can able to define the width of the barrier of P side or N side. Confirm? So width of the barrier varies inversely with the doping, and particularly if you want to define the width of the barrier in terms of the total width of the barrier means like this. Anyhow, the width of the barrier varies inversely with the doping. That is most important condition in the case of semiconductor appliances. Suppose if you go for BZT, emitter is highly doped, so effect of barrier is less there, whereas base is too lightly doped. You know, most of the barriers should be expanding into the base of the BZT you call. Confirm now? Check out the next question. If the charge storage on either side of the barrier is the same or not, explain. So he asked that charge storage of a barrier of P side and N side is the same or not, you call. So 100%, what is the width of the barrier, whether P side is more or N side is more, it's not the case. The charge storage on P side and N side must be same, you can call. What is the charge storage on P side and N side? That must be same, you call. Check up this. So again, this is the PN junction you say. So this is the barrier of N side, this is the barrier of P side. I assume that the charge storage here I can call some Q plus. The charge storage here I can call as some Q minus. I said that both must be same. Check up now, what is the charge storage there? Now I can able to go for P side. Suppose for P side, how much is that charge storage there? That is considered by positive ions there. Sir, what is the width of the barrier of P side means WP, you know, acceptor density NA, A is the junction area, WP. This is the total number of holes into charge Q. Confirm now? This is the positive charge on the case of a P side. That is the charge storage on P side. Now I can able to rewrite like this, NA, A into Q. WP can I write as a W into ND by ND plus NA, can I write now? So finally this formula comes like this, QA into, right, QAW into ND, NA by ND plus NA. Any wrong? If I go for N side also, see this one now, what are the doping? It's not the case. For N side, if I go Q minus equal to, sir, on N side donor density ND you call, area is A, junction is the junction area, that is next WN you call, right, into Q. Confirm? What is WN, sir? WN you can written like this, NA, A, Q into WN equal to what? W into, right, NA by, sir, ND by ND plus NA, you know the formula. W into ND by ND plus NA you call. Now you can able to rewrite this one again, that is QA W, right, QA W into ND NA by ND plus NA. So you confirm now the charge storage on P and N sides of the barrier should be same. So what the question is asking is the charge storage on either side of the barrier is the same or not, explain you call. So the charge storage on either side of the barrier must be same, you can call. Q plus equal to Q minus you call. Confirm now? Charge storage on either side of the barrier should be same or different, sir? Same you call, right? Charge storage on either side of barrier is same irrespective of the doping conditions, you say. Charge storage on either side of the barrier should be same. That is what I can call Q plus equal to Q minus. That is what you call QA W into ND NA by ND plus NA coulombs. So this is the charge storage on either side of the barrier, that must be same, you can call. Got it now? Check out the next question now. How the junction voltage in an open circuit and in biased PN junction. So how this junction voltage in an open circuit as well as in biased junction you say. Says for now in the junction, in the open circuit, the junction voltage itself is the barrier potential. Like this I indicate by the graph show to you. So this is the junction voltage height, Vj you can call. For open circuit, graphically you can define like this. Right? So that's a junction voltage for open circuit PN junction. This is the barrier height. Okay. So for open circuit PN junction, junction voltage equal to the barrier potential. Confirm? If I go for biased case, see for now, with applied forward bias, the junction voltage decreases. With applied forward bias, right? With applied forward bias voltage, what is that one, sir? Means this is that. This is the barrier potential. This is that one now. How much it is, sir? Means it comes to reducing like this. VBI minus VF. With increase of forward bias voltage, the corresponding junction voltage reduces there. VBI minus VF. So this is the forward bias condition. For forward bias condition, the junction voltage Vj equal to VBI minus VF. Confirm? So as if the forward bias, VF is the applied forward bias voltage there. VF equal to applied forward bias. As the applied forward bias increases, the junction voltage comes to reduces. Right? If I go for reverse bias case, the junction voltage increases with increase of reverse bias. Like this. This is the case you call. So what this value means? That is called VR plus VBI. This is the case of reverse bias, where junction voltage equal to VR plus VBI you call. So VR equal to applied reverse bias voltage you call. VR equal to reverse bias voltage, applied reverse bias voltage you say. This one is forward bias voltage you call. This is unbiased one, where junction voltage itself is the barrier potential. In the case of forward bias, as the forward bias voltage increases, the resultant junction voltage reduces. In the case of reverse bias, with the increase of reverse bias voltage, the junction potential goes to be increases, you can call, means opposition increases. In the case of forward bias, the junction voltage reduces, means opposition reduces. It is the case of unbiased circuit. So for unbiased, as compared to unbiased circuit, in forward bias, the barrier effect is less. In the case of reverse bias, as compared to unbiased, the barrier effect goes to be increase. Got it now? So this is the junction voltage in the case of open circuit condition and biased PN junction of forward and reverse bias. Got it now? Check out the next question. So what is an ideal diode you call? Next of the question I go, what is an ideal diode you say? So ideal diode is commonly a theoretical condition you call. How do you say that a diode is an ideal? Means a diode look like an ideal device if it look like a perfectly closed switch in forward bias and perfectly open switch in reverse bias. A diode is said to be an ideal. It look like a perfectly closed switch in forward bias and perfectly open switch in reverse bias. You can call that to be called as an ideal diode. So this one now. So ideal diode means act as perfectly closed switch. Perfectly closed switch you call. Perfectly closed switch. Closed switch means R tends to 0 ohms. Perfectly closed switch in forward bias and perfectly open switch. Open switch in reverse bias. Open switch means R tends to infinite. Confirm? So what is the meaning of that condition, sir? According to the ideal condition, he said that barrier effect on the PN diode is 0. For ideal case, the barrier effect is 0, barrier potential is 0. So if I consider that VI graph of that ideal diode, the graph may come like this. This is the ideal diode VI graph you see. This is the forward bias condition. This is the reverse bias condition. Right? This is the current you call. Confirm now? So this is the reverse bias case. This will be the forward bias case. Plus V plus I denote the condition of voltage and current relation in forward bias you call. So if I go for forward bias, what he say means even for 0 volt the current become maximum. You are identifying a maximum current even for 0 volt of the forward bias like this. Confirm? And what is the meaning of reverse bias, sir? Irrespective of the applied voltage, the current in the reverse bias 0, indicating that in the case of reverse bias, no current is allowed even by minority carriers. Practically you know that there is a minority current, but ideally no minority current can flow there. So this is the ideal diode VI characteristic. Check up my option is right or not. Suppose if I calculate that forward resistance RF equal to V by I. So current is a maximum, but voltage is 0. 0 by anything? 0. Confirm? If I go for reverse bias case here, this one you check up, the diode of reverse bias resistance R equal to V by I. So what is the reverse bias voltage you apply, the current do not flow, right? That look like infinite. So for ideal diode, resistance look like unlimited. For ideal diode, resistance ranging from 0 to infinite, that is unlimited you can call, right? For ideal diode resistance is unlimited. Confirm? And for ideal diode, the barrier effect is 0, so that even for 0 volt itself, the carriers are moving across the junction to get the conductivity. So for ideal case, the barrier potential is 0. VBI to be taken as 0 volt for ideal case. Confirm? For ideal case, got it now? For ideal case, the barrier potential look like be 0, you call. And what is the equivalent model of a PN diode like? This means like this. Diode just act as a switch. This is the ideal diode condition. In forward bias, it look like a closed switch of 0 resistance. In reverse bias, it look like an open switch of infinite resistance, you call. And according to the ideal condition, the barrier effect is not there. No opposition to the movement of carriers. So the carriers are easy to diffuse across the junction. Confirm now? This is the case of ideal diode. So ideal diode is just a theoretical one. If I go for practical diode resistance just limited, not be unlimited you can call. In forward bias, you can have some barrier effect so that up to certain potential, you don't expect the current, such that some opposition to the flow of carriers you can call, such that in forward bias, resistance is not 0, just as a minimum. right? In the case of reverse bias, here I told ideally current 0, but if I go for practical case, some minority current can be defined such that the resistance just maximum like mega ohms, not infinity call. So as compared to the ideal, if you go for practical case, so real case you can call barrier potential should be present, it's not be 0. And as well as some what you can call, sir, means diode resistance must be there, that should be limited, that is not be unlimited as I told in the ideal, that must be limited, ranging from few ohms in forward bias to maximum value of mega ohms in reverse bias. So that should be the practical case you say. So if I go for practical case of diode, this is the equivalent model you call. So yes, so now if I go for practical case, what is the equivalent model of a diode I show to you? For practical or real diode, for practical case, this is the equivalent model of a diode. Diode has a switch, along that what you can call some opposition there, that opposition should be opposite to the forward bias condition. So it is always be opposing potential in the forward bias. Barrier potential always be opposing potential to the forward bias and favoring potential to the reverse bias you call, right? And itself it having some resistance. Resistance must be there. So this is the equivalent model of a PN diode according to the practical case. So this is the internal design of a diode according to the practical case, right? All this is that. So this is I taken 0 for ideal case, this is unlimited, I don't take there. So this is the practical case where R stands for dynamic resistance or AC resistance. So for a diode, DC resistance is not allowed. Why, sir? Means a diode is a non-linear device. So DC or static resistance will be applicable only for linear devices. But diode is a purely non-linear where the current growth is exponential, you call, such that non-linear or dynamic resistance should be used. That is called AC resistance should be used. Got it now? Check out the next one. What is the effect of temperature on reverse saturation current? So, in the case of forward bias, you can expect the current by majority carriers, and that majority current strongly depend on voltage, not on temperature. In forward bias, the current strongly depend on temperature, so strongly depend on applied forward bias voltage, strongly depend on applied forward bias voltage. But while you come back to the reverse bias, the current not depend on voltage, the current strongly depend on temperature you can call. Why you say that one means, in the case of reverse bias, the current is considered by the diffusion and recombination of minority carriers. The diffusion and recombination of whom? Minority carriers. Already you know that on P side or N side of the semiconductor, how do you generate the minority carriers? Means by the breakage of covalent bonds. So the applied reverse bias potential is unable to break the covalent bonds because it looks like an attractive force for the covalent bond structure of P and N sides. So in the reverse bias, how do you break the covalent bonds of P and N sides? Means that to be done with the junction temperature. So in the case of reverse bias, the minority carriers generated by the breakage of covalent bonds with junction temperature, such that minority current strongly depend on temperature. And because of this minority current depend on temperature, independent of voltage, this is commonly called as a reverse saturation current. Saturation means the current of reverse bias independent of voltage depend on temperature. Practically, this minority current goes to be changing 7%, right? It is increasing 7% per 1 degree centigrade in temperature. Per 1 degree centigrade increase in temperature in both the germanium and silicon diodes, the approximate increase of this minority current is around 7%. 7% per 1 degree centigrade, this minority current can increase. Practically, you can also say that this minority current can almost doubles per every 10 degree centigrade increase in temperature. This minority current can almost doubles per every 10 degree centigrade increase in temperature you call. Got it now? What I told you? In forward bias, current depend on voltage, confirm, and that current variation is exponential. By that commonly you say that diode is nothing but a non-linear. In reverse bias, the current due to minority carriers, you know, current depend on temperature you say, because the main person to break the covalent bonds in the reverse bias right, is the junction temperature. And this minority current, that is reverse saturation current you call, that is denoted as a I naught. I naught, that is reverse saturation current you can call, increases by 7%. Increases by how much? 7% per 1 degree centigrade. Per 1 degree centigrade increase in temperature, this minority current almost increase by 7% per 1 degree centigrade you can call, or you say that almost doubles, or almost doubles for every 10 degree centigrade increase in temperature. Confirm? So why this minority current strongly depend on temperature means in reverse bias, right, the current not by majority carriers, only by minority carriers. That minority carriers can able to move across the junction to recombine to generate the current. But how do you generate the minority carriers means by the covalent bond breakage. This covalent bond breakup to be done in reverse bias, not with applied reverse bias voltage, because it is unable to break the covalent bonds. Only the person who can break the covalent bonds means temperature. Confirm now? So minority current almost doubles for every 10 degree centigrade increase in temperature. Using that, I think that one of the relation commonly can use in reverse bias, that is I02 equal to I01 into 2 power of T2 minus T1 by 10. Means minority current almost doubles per every 10 degree centigrade increase in temperature, right? This one 10 you call. So T2 minus T1 by 10. So minority current almost doubles for every 10 degree centigrade increase in temperature. What is this I01 and I02 means? Where I0 is nothing but minority current, I0 equal to I01 at a temperature of T equal to T1 degree centigrade, and I0 equal to I02 at temperature of T2 degree centigrade. At a temperature of T2 degree centigrade, this is I02. At a temperature of T1 degree centigrade, it is what you can call means I01 you can call. So I01 and I02 are the minority currents at the temperatures T1 and T2 degree centigrade respectively called, keeping reverse bias voltage constant. Okay. What is meant by static and dynamic resistance you call? Now I can able to examine what is the meaning of static and dynamic resistance. So just now you discussed that diode resistance you call. For a PN diode of non-linear, which type of resistance is mostly applicable means dynamic resistance is applicable. Static resistance would not be applicable for a diode of non-linear. So static resistance is commonly called as a DC resistance you can call, that to be applicable only for linear elements. What is the static resistance means? Nothing but called DC resistance means it is the ratio of voltage to the corresponding current at a given point of the characteristic graph you call, and that should be same at any point of the characteristic graph. So what is the ratio you defined at one point of the graph? That should be defined at all points of the graph, then it will be called as a static resistance. But that should be possible if and only if the device is linear you call. Confirm? See this one now? Static resistance, nothing but DC resistance also call, or DC suppose. What I told you, it is the ratio of some voltage to the corresponding current at a given point of characteristic graph. Like this, suppose if I go for PN diode forward bias graph like this, this is the forward bias graph. In this one, you define the ratio at one point, suppose X, this is Vx you can call, okay, this is corresponding Ix you call. So, but he said that this resistance should be same at all points of the graph. But you see this one now, this graph is a non-linear, nothing but exponential graph. This thing is not be valid. What are the resistance you calculate one point should not be same at all points of the graph. It should be different from point to point. So this would be useful if and only if this VI graph is a straight line, linear one. So I told that this should be applicable only for linear devices. It is applicable for what? linear devices where this resistance should be constant, right? It is applicable for linear devices, not for non-linear device. Diode is a purely non-linear. This static resistance will not be applicable. Where you can able to find out the dynamic resistance you can call. So dynamic resistance nothing but AC resistance, that is can be used in BJT, FET, MOSFET. For all semiconductor devices, the most commonly used calculation of resistance is dynamic resistance. Static resistance is not applicable. Static resistance would be indicating that the resistance would be fixed at all points of the graph. Whatever the resistance you calculated, that should be same at all points of the graph. That should not be possible for non-linear. Confirm now? As what I call diode is non-linear, I say. Diode is non-linear. What you can take, sir? Dynamic resistance is valid. Dynamic resistance is used. Dynamic resistance is also called as a AC resistance. And remember this, the dynamic resistance is not fixed value. Even it's not a fixed value, it should be preferred. Because the dynamic resistance you define right at a particular point, at a particular area, that should be true in that place only, not at all points. Confirm now? This is the case of dynamic resistance, I say. So in a certain operating voltage region, you take a slope. Suppose this is the VA graph. Right? This is the change in voltage I call, this is the change in current. So dynamic resistance should be calculated in a given operating voltage region like this. So this is the dynamic resistance R, that equal to reciprocal of slope, that you call dV by di, change in voltage to the corresponding change in current. And he said that it is not fixed. But even it is not a fixed value, but it is true, right? And it is depend on the selection of what? Operating voltage region. Based on that, this dynamic resistance to be defined. So even it is not a fixed one, this is mostly preferable for nonlinear devices. It's purely depending on the selection of the voltage region where you calculate. Suppose if I calculate the resistance, it can be defined something. If I go to the other area, the other value comes. That should be true in the other area. So in your real life, you know that dynamic items look like gold, silver, fuel. These are called dynamic items. Suppose if you go for gold, so same price, same quantity, same right quality. If you go from area to area, that can be able to be changing. What are the gold price in one city should not be same in the other city, like a fuel, like a silver. All these are the dynamic items you may call. So that price is not be same at all areas. Area to area, the price is different. Even the price is different, that is a true value, because that price is defined depending on the selection of the place. Same thing here also. Dynamic resistance is not a fixed value, that's purely depending on the selection of the operating voltage region. And you remember now, this dynamic resistance is inversely proportional to the forward bias current. Suppose if I go for forward bias current, this dynamic resistance like this. Now indicate, suppose in forward bias, this is the derived formula I am writing. Dynamic resistance for a diode is R equal to eta Vt by I ohms. So dynamic resistance varies inversely with the forward bias current. Dynamic resistance varies inversely with the forward bias current, and this is the formula most useful in the case of amplifier circuit to define the gain. So the amplifier gain to be defined there in our BJT amplifiers in terms of AC emitter resistance. There, this is the most useful formula you can call. I think that you know Vt stands for thermal voltage, I stands for DC bias current. That is a forward bias current you call. Right? What is that eta? Eta stands for ideality factor, you say, where eta equal to ideality factor or recombination factor also you call. So this is considered as either 1 or 2. So how do you take eta equal to 1 or 2 means higher the conductivity, lower the value of eta, lower the conductivity, higher the value of eta. If I compare germanium to silicon, so as compared to silicon, germanium conductivity more, so eta should be less. As compared to germanium, silicon conductivity is less, that is a 2 for silicon. This is the case. Where I stands for forward bias current, you can call. Vt stands for thermal voltage, you say. So dynamic resistance varies inversely with the forward bias current. Dynamic resistance varies inversely with what, sir? Forward bias current, you can call. Got it now? Next question now we can discuss. See this one now. How does diffusion capacitance vary with forward bias current you call? So you asked that how the diffusion capacitance varies with the forward bias current. Already you learned that the depletion region exists across the PN junction, you know, that look like as a dielectric body of a capacitor. That look like a what? Dielectric body of a capacitor, you know, and the diode with that one having a some internal junction capacitance. And this internal junction capacitance is of two types you can call. One of that one is diffusion capacitance you can call. So what is this diffusion capacitance? See this one now. Suppose now I can able to check out this. This is my PN diode. Confirm. Across the junction there is a barrier, you know. This is P side. Sorry. This one now I can able to go for anode and cathode of this. This is P and right. Anode and cathode of that. So across the junction you know that barrier effect is there. So this is the barrier you call. It have negative ions. It have what? Positive ions. Here the current carriers are holes. Here the current carriers are electrons. So the diffusion capacitance is considered by what sir means due to the barrier effect across the junction and which is exist under the diffusion of majority carriers in a PN junction. So the diffusion capacitance is caused by the barrier effect under the diffusion of majority carriers across the junction you call. So in which mode of biasing you know that these majority carriers can move across the junction means the majority carriers can move across the junction in forward bias. Holes are diffusing from P side to N side, electrons are diffusing from N side to P side. That could be happen in forward bias. So the diffusion capacitance is expressed in forward bias. Confirm now? So how it varies with the forward bias current you can able to examine what I told. It is due to barrier effect you say. So this diffusion due to barrier effect sir, diffusion capacitance under the diffusion is nothing but crossing over, diffusion of majority carriers, diffusion of what? Majority carriers across the junction. Confirm? So this capacitance is due to the barrier effect under the diffusion of majority carriers across the junction, and according to the condition this capacitance is possible in forward bias. So diffusion capacitance is possible in what area means in forward bias you can call. And you remember this, here this can act as a one plate, another one plate it is. So the carriers are moving from one plate to the another plate means this person have a charge storage property. So because of the carriers are able to carry from one plate to the another plate of the body of capacitance, capacitance maintaining some charge storage property. Confirm? It has a charge storage property call. So diffusion capacitance has a charge storage property you say. And this person to be expressed as CD equal to dq by dv. So you don't write q by v, you can write as a dq by dv. Why do you write a 2q by dv sir instead of q by v? Means for a small change in voltage you find out that there is a large number of amount of carriers diffusion. So the number of carriers that are diffusing from P to N or N to P side is a large quantity for a small change in voltage, such that commonly this will be expressed as a dq by dv you can call. And it to be derived to be as tau I by eta Vt. This is the formula you may get of the diffusion capacitance, where tau stands for carriers, tau stands for lifetime of the carriers, I stands for forward bias current, eta stands for ideality factor, Vt stands for thermal voltage you can call. Vt stands for what? Thermal voltage. So the diffusion capacitance to be defined like that. So how do you define this one now sir? Where I equal to forward bias current you can call I equal to I naught into exponential of V by eta Vt. This is the forward bias current, and you know that current equal to rate of flow of charge, that equal to q by t, that to be written as a q by tau. So by using this equation you can get this. This is the formula of forward bias current you can call. Check up now this. So this diffusion capacitance, how it varies with the forward bias current you can call. So you observe now this diffusion capacitance varies directly proportional to the forward bias current. CD proportional to I. So diffusion capacitance varies directly proportional to the forward bias current. Now, and one more thing you discuss here, sir, the diffusion capacitance have a charge storage property. Based on that, it can be used in the design of storage elements. So can I use the diffusion capacitance for variable capacitor application of any electronic circuits? Means the diffusion capacitance never be preferred to be as a variable capacitor. Now, so diffusion capacitance is due to barrier effect, that is possible in forward bias I call, but it have a charge storage property only, and thereby it is used in the design of some storage elements, and it's never be preferred to be used as a variable capacitor. Why don't you prefer this diffusion capacitance as a variable capacitor? Means the main reason is that for a small change in voltage, the growth of the change in charge is large, right? Voltage change is minimum, but the charge variation is more. So that if I use this one as a variable capacitor, for a small change in voltage, there is a large variation in capacitance. Means capacitance jumping or changing suddenly from one value to the another value. You are unable to get a number of capacitance values with respect to voltage, such that diffusion capacitance do not preferred as a variable capacitor, because the change of charge is exponential or rapid with respect to voltage. Means for a small change in voltage, there is a rapid variation in the charge, indicating that the change of charge is exponential or rapid. Means voltage is not, capacitance would be changing rapidly for a small change in voltage, such that diffusion capacitance never preferred as a variable capacitor. Understand my option? What I told you? Sorry. So diffusion capacitance do not preferred as what, sir? Variable capacitor I call. You do not prefer to use as a variable capacitor I call. You do not prefer, sir. You do not prefer to use as a variable capacitor. What is the reason for this? Because charge is changing rapidly for a small change in voltage. For a small change in voltage, there is a rapid change variation of the charge, such that capacitance will be changing rapidly, so that I don't prefer this person to be used as a variable capacitor, right? The diffusion capacitance commonly is high as compared to the another capacitance, that is a transition capacitance, but even it is high, it's not be preferred, because the variation of capacitance with respect to the voltage is nothing but very rapid. Confirm now? Check out the next question now. Is the diffusion capacitance preferred to use as a variable capacitor? Recall. Just now I told that it should not be preferred to be used as a variable capacitor, I told, because the charge is nothing but changing rapidly with respect to the voltage, right? Indicating that the capacitance should be varied rapidly. So diffusion capacitance never be preferred to be used as a variable capacitor. So if not, which one to be preferred as a variable capacitor you can call. And one more capacitor is there, that to be called as a transition capacitance. So that to be preferred to be used as a variable capacitor. Confirm my option? So diffusion capacitance not preferred to use as a variable capacitor you call. So who is preferred to be used as a variable capacitor? Means a transition capacitance, right? This one I am saying. Diffusion capacitance that is considered by the diode in forward bias do not preferred, right, to use as a variable capacitor you call. Confirm? Since what sir means, the variation of capacitance with respect to the voltage is rapid. So who to be preferred to be used as a variable capacitor you can call. So the person that to be preferred to be used as a variable capacitor is nothing but what you can call, sir, means that to be transition capacitance. So transition or depletion capacitance you can also call. Transition or depletion capacitance, that is denoted by some C2 you can call, right, can be preferred to use as a variable capacitor. So this depletion or transition capacitance is considered by what, sir, means again the barrier effect. So this is also considered by the barrier effect under the depletion of majority carriers across the junction. So this capacitance is caused by the what, sir, means barrier effect under the depletion of majority carriers across the junction you call. So depletion means that carriers are moving away from the junction you say. See this one now. This is my PN junction you call. Confirm. So this is the barrier effect you can say. This is the barrier on P and N sides, you know. This is the anode, this is the cathode, this is the width of the barrier, you know. These are negative ions, these are the positive ions. He said that this capacitance is considered by the barrier effect under the depletion of majority carriers. Depletion means they are moving away. So holes are moving away from the junction. Electrons are moving away from the junction. So in which of biasing, these majority carriers can move away from the junction means, I think that you know that to be possible in reverse bias. So in reverse bias, the majority carriers are depleted like this. So this is the capacitance considered by the barrier effect under reverse bias. Come on now. So here this capacitance has no charge storage property because none of the carrier can move from one plate to the other plate. So ideally it has no charge storage property. Practically they have a charge storage property by the diffusion of minority carriers. So which type of carriers can move across the junction here in the reverse bias, you know. So that minority carriers can able to move across the junction only. So that can have a small charge storage property that is ignored. So ideally no charge storage by means of the majority carriers we can call. However, a small minority carrier charge storage is there by the diffusion of minority carriers. By the diffusion of what? Minority carriers. So it have no charge storage property. Then how do you define the body capacitance means? That can be defined by the dimensions of it look like a parallel plate capacitor. So a diode in reverse bias look like a parallel plate capacitor and offering the transition capacitance, that is nothing but look like a parallel plate capacitance you can call. Confirm? So transition or depletion capacitance, which is preferred to use as a variable capacitor, operated in what, sir? So what I told you, transition capacitance is possible in what? Reverse bias or forward bias? It will be possible in reverse bias, I told. Transition capacitance is due to depletion of what, sir? Majority carriers. Depletion means moving away. Depletion of majority carriers across the junction. So which carriers are moving away from the junction means majority carriers you can call. So that to be possible in what area, sir? Means that to be possible in reverse bias you call. That to be possible in what area? Reverse bias. Okay. So and is possible in reverse bias. Confirm? And I told that this depletion or transition capacitance has no charge storage property, and the diode in reverse bias look like as a parallel plate capacitor. Look like as what? Parallel plate capacitor you call. Confirm now? This transition capacitance has no charge storage property, and it is nothing but look like what, sir? Means parallel plate capacitor look like a parallel plate capacitor, that is the transition capacitance I call. Look like a parallel plate capacitor operated in what, sir? Reverse bias you can call. What is this capacitance you can call? Ct equal to epsilon A by W you say. Ct equal to what? Epsilon A by W, where W stands for width of the barrier. And you know that where W is nothing but what, sir? Width of the barrier, that is proportional to junction voltage as a power of N. And what is that N value, sir? N equal to 1 by 2 for abrupt junction. That is step graded junction. Right? And 1 by 3 for linear graded junction you call. For linear graded junction it is 1 by 3, sir. For linear graded junction, it is 1 by 3. For abrupt junction, it is 1 by 2 you can call. So as the junction voltage increases, the width of the barrier goes to be increases, and thereby the capacitance decreases, you can call. Correct now? And it is commonly operated in reverse bias, you can call. And what is that Vj means? You know that Vj equal to VR plus Vbi. Vj equal to what, sir? VR plus Vbi you can call. So where Vj stands for junction voltage in reverse bias, the junction voltage equal to sum of the applied reverse bias voltage and internal barrier potential you can call. Confirm now? So this depletion capacitance to be very like this, Ct equal to epsilon A by W. Ct proportional to 1 by W is say. So the reverse bias voltage increases, junction voltage increases, the width of the barrier increases, the capacitance decreases. Suppose if the reverse bias voltage decreases, junction voltage decreases, the means width of the barrier decreases, capacitance goes to be increases, such that the depletion capacitance should be preferred to be used as a variable capacitor. That is considered in reverse bias. Best example on this principle is what, sir? Varactor diode. Varactor diode can operate on this principle, you can call. Varactor diode is nothing but a voltage variable capacitor that can operate on the phenomenon of this. Right? And so now Ct proportional to 1 by W you can call, where W stands for width of the barrier. So that width of the barrier to be varies with the junction voltage like this. And again you told that it is in reverse bias. In reverse bias the junction voltage is like this, VR plus Vbi. Where VR is the applied reverse bias voltage I call. As the applied reverse bias voltage increases, junction voltage increases, width of the barrier increases, the corresponding capacitance decreases, and vice versa, such that the depletion capacitance preferred to use as a variable capacitor. And one more thing you remember, if I compare diffusion and depletion capacitance, the order of depletion capacitance less as compared to diffusion capacitance. Even the depletion capacitance is less order, right, less range you can call, but it is mostly preferred to be used as a variable capacitor because it can offer wide range of variation of capacitances as compared to diffusion capacitance. So among diffusion and depletion capacitances, the mostly preferred variable capacitor is depletion capacitance. Best example you may find out is Varactor diode. You check out Varactor diode later. Okay. What is the next one you check out? What is meant by Zener and Valence breakdown? Right? What is meant by what? Zener and Valence breakdown. So in the case of PN junction, you can expect two types of breakdowns depending on the doping profile. Depending on the doping profile, you can expect two types of breakdowns. Those are Zener breakdown and Valence breakdown. So you can expect the two types of breakdown, Zener and Valence breakdown, and commonly you can define this breakdown in reverse bias. So this breakdown to be happen in reverse bias you can call, where that minority current can increase sharply, keeping the voltage constant almost. Right, at the breakdown point, commonly you say that there is a rapid increase in current, keeping the voltage almost constant, and depending on the doping profile of PN junction, you find out two types of breakdowns. One is what? Zener, other one is Valence breakdown. First of that I can go some Zener breakdown. So what is this Zener breakdown? So according to the condition, so Zener breakdown is possible if the doping is high, right? It is possible if doping is high. Confirm? If the doping is high, this type of Zener breakdown is possible. Already you know the condition. Sir, if the doping is high, the effect of the barrier is less. Already you know that. Width of the barrier or effect of the barrier is inversely proportional to doping. So if I operate this type of diode in reverse bias at a particular reverse bias voltage called breakdown voltage, what you find out means there is a strong reverse bias electric field is acting. So there is a strong reverse bias electric field is acting across the junction. So based on that, so many thousands of covalent bonds should be break up almost same time. By that, the minority carrier number is increasing too rapidly. So due to which the minority current can increase very sharply, keeping the voltage almost constant, And so now, so what I told that, so depending on the doping is high, right? Because of the doping is high, irrespective of the bias, so even it is an open circuit we call, what I told sir, the barrier effect to be very, very less. The barrier effect to be less, you call. This is a negligible barrier effect you call. So this barrier to be order of nanometers. This barrier effect to be order of what? Nanometers. In ordinary diode, it is commonly in the range of micrometers. But here, because of the doping is high, the barrier effect to be order of nanometer to less. What I told you, if such PN junction, if I operate in reverse bias, if I operate that in reverse bias, right? If I operate in reverse bias at a particular reverse bias voltage, that particular reverse bias voltage is called breakdown voltage. So at a particular reverse bias voltage, what can I expect, sir? Means breakdown voltage you can call. There is a sudden breakage of so many covalent bonds on P and N sides. So at this particular breakdown voltage, I can expect so many covalent bonds are break up on P and N sides. So that you may find out there is a rapid growth of minority carriers. So whenever a covalent bond broken, electron hole pairs are generated, you know. Among that, one is a majority, other one is a minority. So in reverse bias, the current can be expected by minority carriers. Due to this breakage of covalent bonds, so many minority carriers are generated suddenly. So they can move across the junction, recombine each other and causing a minority current. And that minority current increasing sharply like this. This is that one. This is the reverse bias voltage you call. Reverse bias current. Once that applied reverse bias voltage reach the breakdown, so this particular voltage where you find out electric field is strong. According to the practical case, this electric field is what, sir? Means around 2 into 10 power 8 volt per meter, sir. So at a particular reverse bias voltage, there is a very strong reverse bias electric field is acting. E equal to V by W, and this particular voltage I call breakdown voltage I call. So at that particular reverse bias voltage called breakdown voltage, this electric field is very strong, sir. That is around 2 into 10 power 8 volt per meter. Due to this high electric field impact, so many covalent bonds are broken. By that, the minority carrier density is more, and due to which the current increasing fast, keeping the voltage almost constant. So this one. So the voltage where the sudden increase of current to be done due to high electric field impact, that is called breakdown voltage. And that type of breakdown is called Zener breakdown. So Zener breakdown is possible if doping is high, I call. Doping is high. So it is based on Zener effect. Based on what? Zener effect you call. Okay, based on what, sir? Means Zener effect you can call. It is also called as the impact ionization. Okay, Zener effect. So according to the Zener effect, what I told, sir, at a particular reverse bias voltage, so there is a strong electric field is acting, I call. Originally, to get this much high electric field, I apply high voltage, but I don't apply high voltage. Practically, I can apply ordinary voltage less than 6 volt. Okay, so what I can call, according to the Zener effect, we can call at particular reverse bias voltage, that is at particular voltage, say VZ, and so now that is called breakdown voltage. A strong electric field, that much you call acting, so that there is a sudden so that there is a sudden breakage, confirm, of several covalent bonds on both P and N sides, sir. And you know that whenever a covalent bond break up, minority carriers are generated. One should be majority, other one minority, and minority current can increase sharply. Minority current can increase what, sir? Sharply, keeping the voltage almost constant, you can call. Right? Minority current can increase sharply, keeping the voltage is almost constant. Got it now? So, and minority current increase sharply, call, keeping voltage almost constant. So this type of breakdown is a Zener breakdown you call. So this is based on electric field impact ionization, you can also call, right? So it is nothing but also called what, sir? Based on electric field impact ionization. It is nothing but based on electric field impact ionization you call. So practically this is possible. So this Zener breakdown is possible for the breakdown voltage less than 6 volt, right? Any breakdown voltage less than 6 volt come under the category of Zener breakdown, sir, right? Because you are getting high electric field impact even for ordinary voltage, practically it should be less than 6 volt. And anyhow, you remember now, sir, Zener breakdown has a negative temperature coefficient. Zener breakdown has negative temperature coefficient. Means as the temperature increases, the breakdown comes somewhat early. So that is the breakdown voltage decreasing with increase of temperature. How much means it is around 0.1% per 1 degree centigrade. 0.1% per 1 degree centigrade, sir, not much high. So there is a little bit of decrease in the breakdown voltage with the temperature you can call. Means if I go into say that temperature increasing means, so that can able to break up so many number of covalent bonds somewhat earlier condition as compared to the previous. Based on that, what you say, sir, means breakdown somewhat comes earlier. Confirm my option. As the temperature increases, so you find out that, so with the effect of temperature also the covalent bonds are break up, you can hear, you know that. So the breakdown voltage somewhat decreases, you can call. So how much decrease of this one with respect temperature means around 0.1% per 1 degree centigrade, per 1 degree centigrade. Based on that, this Zener breakdown have negative temperature coefficient of breakdown, right? Negative temperature coefficient, nothing but as the temperature increasing, the breakdown voltage decreases, you can call. And one more is there, that is what you can call, sir, avalanche breakdown. One more breakdown you can call, that you can call avalanche breakdown. Confirm? So what is that avalanche breakdown that I can able to examine now? Check out this. Avalanche breakdown I go. So as compared to Zener breakdown, this avalanche breakdown is possible if the doping is moderate or normal. Confirm? So practically you say that it is possible if the doping is moderate. Possible if the doping is moderate, you can call. Suppose you know in a BZT, collector junction is moderately doped, that I have an avalanche breakdown, you call. BZT, FET and MOSFET have avalanche breakdowns, right? Possible if the doping is what you can call moderate. So if the doping is moderate, the type of breakdown you may get is what you call avalanche breakdown, you can call avalanche breakdown. And this person to be based on what, sir, means collision effect, you can call. Thermal ionization, nothing but collision effect. So it is based on collision effect. Sorry. So based on ionization or collision effect. So it is based on collision effect, you call. What is that collision effect means? So here, because of the doping is moderate, barrier effect is not much minimum, you call. It should be wider, you say. So here you can apply high voltage of reverse bias. With applied high voltage of reverse bias, kinetic energy is acting on minority carriers. So with that kinetic energy, they can able to collide the other covalent bonds. By that, they can able to break up that covalent bond. Confirm my option. By that, additional minority carriers are generated. Right? With applied high voltage of reverse bias, a minority carrier can get kinetic energy, and with that kinetic energy, it can collide the other covalent bond to get one more minority carrier. Now these two minority carriers with again kinetic energy collide two more covalent bonds, again generate two more minority carriers. So it is a cumulative process, continuous process, and within a short span of time, this number to be huge, large number, and due to which you can find out a breakdown that is called avalanche breakdown. To get the kinetic energy for the carriers, applied reverse bias voltage must be high, you can call, and practically this should be greater than 6 volt. Greater than what? 6 volt you can call. Confirm now? So condition is you must also apply high voltage of reverse bias with applied high reverse bias voltage Confirm? So before sharp breakdown, what are the one or two minority carriers or few minority carriers are there? Those minority carriers can get kinetic energy. Maximum energy call. Minority carriers get kinetic energy and collide the other covalent bonds. Confirm? Other covalent bonds to generate additional carriers. Electron hole pairs are nothing but minority carriers you can call. So these additional carriers again get kinetic energy and they again collide the covalent bonds and generate other carriers. So this is a cumulative process, and this process is cumulative, you say, and it is cumulative. So causing sharp breakdown, that is called as a avalanche breakdown you can call. So it should be possible, right? It is possible for VZ, that is breakdown voltage should be greater than 6 volt. So Zener breakdown is happen for less than 6 volt, but avalanche breakdown possible for VZ greater than 6 volt you call. Got it now? And one more thing is, it has negative temperature, it has positive temperature coefficient of breakdown. It has positive temperature coefficient of breakdown as compared to Zener breakdown. So avalanche breakdown have positive temperature coefficient you can call. As a positive temperature coefficient you can call. So as the temperature increases, the breakdown voltage goes to be increases. Why sir? Means temperature increases means your applied energy is wasting. So to get kinetic energy, you need to apply some more voltage. Confirm my option? Sir, why the temperature increasing, the breakdown comes later means? So here temperature is increasing means your applied source is nothing but wasting. So that to get the kinetic energy, you must should apply some more input voltage. Some more input voltage to get the kinetic energy. So the increase of temperature makes to say that the applied source voltage again to be increasing to get kinetic energy. Confirm? So based on that, as temperature increases, the breakdown voltage goes to be increases. So it have positive temperature coefficient of breakdown you can call. And how much it is, sir? It is also nothing but plus 0.1% per 1 degree centigrade. So Zener breakdown has a negative temperature coefficient there, but avalanche breakdown have positive temperature coefficient you can call. Means as temperature increasing, the breakdown voltage goes to be increases. How much we have, sir? That should be around 0.1% per 1 degree centigrade. Confirm? And this is nothing but what you can call, sir, right? The avalanche multiplication also you can call. Avalanche breakdown is also called as avalanche multiplication. Means here the minority carriers numbers should be increasing in a multiple order. 1 goes to 2, 2 goes to 4, 4 goes to 8, 8 goes to 3, 16 like this. Within a short span of time, it can increasing in a multiple order and causing a very sharp breakdown. By that, avalanche breakdown is also called as avalanche multiplication. Confirm? Check out the next one. Is a tunnel diode is based on classical or quantum mechanics? Explain. Check up now. So what is classical mechanics? What is the quantum mechanics you call? So according to the classical mechanics, he said that any charge carrier can move across the junction. Any carrier can move across the junction by having energy greater than or equal to energy of the barrier. That to be called as a classical mechanics, sir. Suppose this is the barrier you call. This is my potential barrier. Right? This is the width of the barrier, you know. Confirm now? This is the barrier, I say. So what is the energy of the barrier? I can call some EW, you say. So this is one of the carrier here. I wanted to make that carrier to move from one side to the other side. Okay. This carrier I wanted to carry to the other side. So he said that this carrier can able to carry from one side to the other side if and only if the energy on that is should be greater than or equal to energy of the barrier. So according to the classical mechanics, any carrier can move from one side to the other side of the barrier by having energy that should be greater than or equal to energy of the barrier. Energy of the barrier you can call. So this should be around 0.3 electron volt for germanium diode and 0.6 or 0.7 electron volt for silicon diode. So a ordinary PN diode is based on classical mechanics. According to the classical mechanics, a carrier must and should move across the junction by having additional energy in such a way that that energy must be greater than or equal to energy of the barrier. Suppose if the applied energy less than the energy of the barrier, simply it is returned back, reflected back. Don't go to the other side. Your ordinary PN junction diode is based on classical mechanics, where to move the carrier from one side to the other side, you must and should apply some source of energy that can keep to say that the energy should be greater than or equal to energy of the barrier. By that you can able to reduce the opposition of the barrier. Confirm? That to be called classical. Confirm? According to what I say? Classical mechanics, confirm, a carrier, and so now a carrier can move across the junction by having energy greater than or equal to energy of barrier and is done by applied source. Confirm? And is done by applied source you can call. So this is the principle you can use in ordinary diode, right? This principle used in what, sir? This principle used in ordinary diode you call? Ordinary PN diode you can call. Ordinary PN diode, this principle you can operate. But particularly quantum mechanics, if I go, according to the quantum mechanics, you say that a carrier without asking any additional energy, without asking any extra energy from source, easy to move from one side to the other side. According to the quantum mechanics, without asking any extra or additional energy, the carrier can move from one side to the other side of the barrier. How it to be possible means, according to the quantum mechanics, instead of updating the energy of the carrier, you can able to update the barrier effect by means of what's high doping. So keeping of high doping, already you know that barrier effect should be minimum. So based on that, the carrier can easily move from one to the other side without asking extra energy. That's called as a quantum mechanics. According to the quantum mechanics, a carrier without any additional energy can move across the barrier or across the junction, and this is to be done by reducing the effect of the barrier, keeping high doping. Confirm? That is called quantum mechanics. So this quantum mechanics, so the tunnel diode is completely based on this quantum mechanics principle. Based on that, in the case of tunnel diode, both the p side and n side of the diode should be strongly doped one. That order of doping is 1:10 cubed. Even as compared to Zener diode, the doping is too much high in the case of tunnel diode. Got it now? That's the case you say? Check up what I told you. And so now, according to quantum mechanics, what I told, the barrier effect to be negligible like this. The barrier effect to be very, very less. So this is the barrier. So the carrier here that can easily move from one side to the other side without asking any extra energy call, right? According to quantum mechanics, confirm, according to quantum mechanics, you call a carrier can move across junction without any additional energy. Confirm? Without asking any extra energy from source, it can easily move from one side to the other side without any additional energy you can call, and is done by How, sir? And is done by reducing the barrier effect to minimum by reducing the barrier effect to what, sir? Minimum I call, sorry, reducing the barrier effect to minimum by a very strong doping. Already know, as the doping is more, barrier effect is less. By a very strong doping you call. So tunnel diode is based on what, sir? Means quantum mechanics. So in the case of tunnel diode, both the P and N types are very, very strongly doped. Confirm? So tunnel diode is based on quantum mechanics. Is based on what? Quantum mechanics you call. Where doping is very high. So how much means? That you know 1:10 cube, sir. Means for every 10 cube atoms, one impurity is added. For every 10 cubed atoms, one impurity is added. So as compared to Zener diode, it is still more. So Zener diode is originally highly doped. Even as compared to Zener diode, in the case of tunnel diode, the doping is order is too high, such that the barrier effect is almost negligible. Such that you may also say that tunnel diode have a fast switching response also. So here you can get the conductivity of current in the case of tunnel diode immediately from 0 volt of forward bias. Commonly in the case of diode, you know, the current is possible in forward bias once the applied voltage cross the barrier potential. But here barrier effect almost zero you can call, indicating that the tunnel diode have the conductivity in forward bias immediately from 0 volt. Immediately from 0 volt you can call. That's the importance of the tunnel diode. Got it now? Check out the next one. Why tunnel diode do not made with silicon? Why tunnel diode not made with silicon? See, for now, a tunnel diode is made by preferably gallium arsenide or germanium, not preferred with silicon, right? So it is commonly made by what, sir? Germanium, gallium arsenide, like this. So it is made by germanium, gallium arsenide, sir, but not by silicon. Why this one, sir? So now you can able to examine this one now from the graph. Just now I told that tunnel diode who have fast switching response, sir, barrier effect is negligible in the case of tunnel diode due to doping is high. Barrier effect is negligible you can call. And what the thing you say that one means? So no junction capacitance it also have. Ideally the junction capacitance is 0, sir. Because of no barrier, no junction capacitance you can call. And this tunnel diode can easy to operate even at high frequency. Tunnel diode can easy to operate even at high frequency, and because of the doping is high, occur the type of breakdown. Zener, the tunnel diode have a Zener breakdown, sir. Tunnel diode have Zener breakdown. So this is the VA characteristic of tunnel diode. See this one now? This is the VA characteristic of tunnel diode, sir. Confirm. So this is the reverse bias condition. This will be the forward bias condition you call. If I consider the tunnel diode, sir, what the thing you can expect there? In the case of tunnel diode, the current conductivity starts immediately from 0 volt I told. Just now I told the conductivity of current starts immediately from 0 volt because of the no barrier effect is there and it is too strongly doped, you know. So this is the variation of current in the case of tunnel diode. But in the case of tunnel diode, we can expect the current right up to certain portion just due to the flow of electrons. Just due to the flow of electrons from N side to P side. So that is jumping of electrons from N side to P side. So that is nothing but this one, sir. Initially the tunneling of electrons is increasing from N side to P side, and once the current reaches the maximum, that to be called peak current you can call. Thereafter the current decreasing to minimum, that is due to what you can call, sir, decreased tunneling of electrons. So initially the tunneling of electrons is more, current increases, and thereafter once you reach a certain peak value, thereafter the tunneling of electrons decreases and the current decreases to minimum, called valley point you say. So this is called peak point, sir. This is called peak point. and crossing the peak point, the tunneling of electrons come down, thereby the current decreases, sir, and thereby you reach the current minimum. That is called valley point, sir. That to be called valley point. Sir, after which the current now increasing due to both electrons and holes recombination like ordinary diode. So this is the VA characteristic of a PN diode, sir, tunnel diode in forward bias. Tunnel diode mainly operated in forward bias, sir, having a different characteristic you can call. So the VA characteristic of a tunnel diode in forward bias look like hills and valleys. Look like what? Hills and valleys you can call. So initially the current is 0 at forward bias voltage of 0 because of none of the electrons is tunneled from N side to P side. Just a little bit above 0 volt, the tunneling of electrons is increasing with forward bias voltage and thereby current increases. After that, once you cross the peak point, sir, the tunneling of electrons decreases, the current decreases and reaches a minimum value called valley point. So once you reach a valley point, sir, there the tunneling of electrons is stopped. Now the current look like what, sir? Ordinary diode, look like ordinary diode, the current due to the recombination of electrons and holes. And you observe now, here current response is a multi-valued function. Initially 0, increase, decrease, again increase exponentially, such that this tunnel diode has a multi-valued function of current. Multi-valued function of current. Now, and in this one, the main important portion is what, sir? This one, sir, IP to IV. So this is a negative resistance portion, sir. This is what you can call negative resistance region you call. So which diode have negative resistance, sir? Tunnel diode have negative resistance region. So in which the negative resistance lies between peak and valley points. Negative resistance lies between what, sir? Peak and valley points you can call. Where you observe now, in between peak and valley points, what the thing you remember, sir? Voltage increases but current decreases you can call. Voltage increases but current decreases have negative resistance property. So with that negative resistance property, the tunnel diode should be used as an oscillator. And where it is commonly used as an oscillator, sir, already I told that it is free from internal junction capacitance because of no barrier effect. So because of the barrier effect is not there, no junction capacitance is there, it can easy to operate at high frequency. So that is called microwave frequency of gigahertz. Tunnel diode used as an oscillator in gigahertz ranges are called microwave oscillator. Sir, for good oscillations, for good response of oscillations, negative resistance portion I require wider. So that to be characterized by IP to IV ratio. IP to IV ratio you can call. So tunnel diode has a negative resistance, sir. So that is shown by IP to IV characteristic, sir. What is this IP to IV means? This one. Peak current to valley current ratio, sir. IP to IV ratio is how much, sir? 6 for germanium. For germanium device it is 6, sir. If I go for gallium arsenide it is 10, sir. If I made with the silicon, just it is a 2, sir. So if you made a tunnel diode with the silicon, this negative resistance portion is very, very less, such that it is very difficult to sustain the oscillations. Such that tunnel diodes mainly prefer to made with the gallium arsenide, otherwise germanium. It never preferred with the silicon. The main reason is IP to IV ratio is poor for silicon. It's just 2, sir. It's just 2 you can call, such that this negative resistance portion is very small, sir, and it is very difficult to sustain oscillations. It is very difficult to sustain oscillations by this ratio is poor. So tunnel diode is always preferred to made with the gallium arsenide or germanium, but not preferred with what? Silicon. What the main reason means? IP to IV ratio is poor, sir. Peak current to valley current ratio. That should be 4. And one more thing, see this one now. Tunnel diode in reverse bias having a sharp breakdown, that to be called Zener breakdown, and that breakdown is very close to 0, sir, like this. So look like a Zener diode, it have a very sharp breakdown. So even it have a very sharp breakdown as compared to Zener diode, it do not be used as a voltage regulator. Why this tunnel diode do not used as a voltage regulator means, the main reason he said that having a sharp breakdown, but that breakdown is very close to 0 volt. That's my option. So it have a very sharp breakdown, but that breakdown is very, very close to 0 volt, sir. So that it is unable to use as a voltage regulator. Confirm now? So it have a Zener breakdown, and that breakdown is very close to 0 volt, such that the tunnel diode do not preferred as a voltage regulator. Do not preferred as a voltage regulator. Who is preferred as a voltage regulator? You know, that to be Zener diode only, not this tunnel diode, sir. Not this tunnel diode. And so now this, why it is not made with silicon means this is the reason. Okay, so it has negative resistance. It has what, sir? Negative resistance between peak and valley points. And so now students, it has negative resistance between peak and valley points. Confirm? With that negative resistance property, it is used as an oscillator, I call. And because of low junction capacitance, it can be used as an oscillator at a microwave frequency, I told. With negative resistance property, it is used as oscillator, I call. Right? But negative resistance portion should be wider required, so that negative resistance portion should be very less for silicon, and it is difficult to sustain the oscillations. Right? For silicon made, negative resistance area is small and difficult to sustain oscillations, sir. Difficult to sustain oscillations. By that, tunnel diode do not preferred with the silicon. So it has what type of breakdown? I told you, Zener breakdown. So Zener breakdown means, can I use this one as a voltage regulator? Means not preferred as a voltage regulator, sir. Why I say that one means, because of that breakdown comes very close to 0 volt. So if I want to use as a regulator, it can give an output of 0 volt only, very close to 0, sir. So even it have a Zener breakdown, it do not be preferred as a voltage regulator because the breakdown close to 0 volt. Okay. It has Zener breakdown, sir. Zener breakdown, which is close to what, sir? 0 volt, you can call. So it is unable to prefer to be used as what, sir? Voltage regulator. Unable to prefer as voltage regulator, you can call. Got it now, students? Check out the next one now. Explain the principle of Varactor diode. Right? Explain the principle of what you call Varactor diode. Sir, Varactor diode is commonly called as a varicap or volta cap or voltage variable capacitor. It is a person purely based on depletion capacitance, sir. It is a person purely based on what you can call depletion capacitance, transition capacitance. Just now you learn. Right? So, what I told you, it is a voltage variable capacitor, sir. It is a person of what? Voltage variable capacitor, you say. Confirm? Based on transition capacitance, sir. Based on what? Transition capacitance, you can call. Transition capacitance, sir, and operated in reverse bias. Confirm? And this fellow operated in what, sir? Reverse bias. This person should be operated in reverse bias, you can call, based on transition capacitance. Sir, it is a graded PN junction, you say. It is a graded PN junction, that is P plus N or PN plus junction, you call. So it is a graded PN junction. Based on that, what is the formula of this one, sir? C equal to epsilon A by W, where A is the stand for junction area, you can call, and W is equal to what you know, just now I told, where W equal to Vz power of 1 by 2, sir, for step graded. Vz equal to what, sir? Vr plus Vbi power of half. This is the case you can call. So now let us consider this capacitance is proportional to like this 1 by under root of VR plus VBI. So VBI stands for internal barrier potential, VR stands for applied reverse bias voltage, sir. So thus capacitance can decreasing at the scalar rate of the applied voltage. So capacitance can able to vary at the scalar rate of the applied voltage, sir. Junction voltage can call. So if I consider that the graph of this capacitance would be like this. So this capacitance would be like this, sir. This is the variation of this capacitance you go. This is the capacitance. This is the applied reverse bias voltage you can call VR. So what you can find out, sir? So the capacitance can be varies at the scalar rate of the applied voltage you can call like this. This is the variation of capacitance. So whenever the voltage is minimum, the capacitance is maximum, right? Some hundreds of picofarad you can call. The voltage increases, the capacitance goes to be decreases and minimum like this. So this is the range of capacitance offered by the Varactor diode. Some hundreds of picofarad to some few picofarad you can call. Some hundreds of picofarad to some few picofarad you can call. Sir, what is the symbol of Varactor diode mean? This is the symbol for it. So whose anode, whose cathode? This would be the symbol of Varactor diode, where cathode look like a capacitor. And this is the equivalent electrical model of a Varactor diode, sir. Whose anode, cathode you call. So this is the dynamic resistance, you know, that is reverse bias resistance are commonly order of mega ohms. Reverse bias dynamic resistance of the diode, because it is operated in reverse bias, it should be in mega ohms. So this is the variational capacitance, sir. What is the range of capacitance known by this? And this Varactor diode to be used as what, sir? Variable capacitor in the tuning circuits of radio and TV receivers. So this Varactor diode to be used as what, sir? Variable capacitor. It is used as a variable capacitor, sir. Variable capacitor in the tuning circuits of radio and TV receivers we call. Radio and what? TV receivers, students. So in radio and TV receivers, this person to be used as what, sir? So variable capacitor. So the main purpose of the Varactor diode to be used as what? So as a variable capacitor in the tuning circuit of radio and TV receivers. And in communication systems, this Varactor diode to be also used in the generation of FM signal, frequency modulation signal, frequency modulation signal. For that also it can be used, sir. The Varactor diode can also be used in the generation of what, sir? FM signal you can call, frequency modulated carrier signal, FM signal. So that's the Varactor diode you say. Okay. Check out the next one. What is the equivalent model of Zener diode you call, sir? What is the equivalent model of Zener diode you say? Now you can able to examine the equivalent model of Zener diode, sir. Sir, Zener diode is basically a highly doped PN diode. Both P-type and N-type are highly doped one. Zener diode is made by silicon or germanium, sir. And as compared to the ordinary diode, it can differ by means of doping, sir. It can differ by means of doping. So with that doping, it can maintaining a very sharp breakdown in reverse bias, sir. So no importance in forward bias, sir. In forward bias look like same as normal diode. Because of doping is high, the current is more, sir. Just you show this. This is plus swing, minus swing, plus I, minus I. So this is forward bias. This will be the reverse bias I call. Sir, what I told, sir, as compared to the ordinary diode, it is mainly used in reverse bias, sir. See, so now, this is our ordinary PN diode graph. This is your PN diode graph, sir, both in forward and reverse, like this. If I go for Zener diode, sir, that graph may come like this. So, in forward bias, this is the conductivity. In reverse bias, like this. So this is the Zener diode, sir. What is that red shape marked one is Zener diode characteristic graph. So you observe now in the reverse bias it have a very sharp breakdown. Just now I told that is due to Zener effect. So in forward bias not be much important, sir. It look like a normal diode, act as a closed switch. Once the applied voltage crosses this cut-in voltage or barrier potential, thereafter the current increasing rapidly act as a closed switch. While you come to the reverse bias, sir, in the case of reverse bias, particularly you consider a breakdown point, sir, keeping the voltage constant, the current increasing sharply. Keeping the voltage increasing constant, the current increasing sharply, you can call. Got it now, sir? So before breakdown, it act as a off switch, sir. This place it act as a off switch. And this is the breakdown region where the Zener diode can act as a voltage regulator or battery. Zener diode can act as a voltage regulator or battery, you can call. Got it now? So if I go for particularly breakdown region, sir, in that breakdown region, the Zener diode look like to be act as a battery. So for the applied reverse bias voltage, so less than Vz, it act as a off switch. For applied reverse bias voltage greater than or equal to Vz, it act as a voltage regulator, nothing but a battery, nothing but look like a constant voltage source. So this one now what I told, it is a highly doped PN diode we call. Confirm? Both P type and N type are highly doped, sir. Order of doping is 1:10 power 5. Confirm? In forward bias, it act as closed switch. Confirm? It act as closed switch like ordinary diode, sir. Understood now? It is mainly operate in reverse bias. Mainly operate in what, sir? In reverse bias. Having a sharp breakdown, you call. Having a sharp breakdown according to Zener effect, you call. According to Zener effect, that is Zener breakdown, you know. According to Zener effect, just now you discussed Zener breakdown. Zener effect called as breakdown diode. So Zener diode also called by what, sir? Breakdown diode you can call. Also called as what, sir? Breakdown diode you call. Confirm? Understand this? So Zener diode also called as a breakdown diode you can call. So this one now, particularly in the case of reverse bias, what happens, sir? So wherever the breakdown happen, up to that it can act as a off switch. Up to that minority current is negligible. So don't find sharp breakdown you can call. Confirm now? This is the case in reverse bias for V less than Vz, right? So no sharp breakdown. No breakdown you call. Confirm now? And act as off switch. And act as off switch. Right? For in reverse bias, for applied voltage V greater than or equal to Vz, V greater than or equal to what, sir? Vz you call. V greater than or equal to Vz, it has a very sharp breakdown. It has a sharp breakdown and act as a constant voltage source. This is the case. Act as a constant voltage source. So commonly you can operate the Zener diode in the breakdown region, keeping that reverse bias voltage should be greater than or equal to Vz. So what is the equivalent model of the Zener diode in that breakdown region? I can go. I can show that one. See this one now. Particularly if I go in the breakdown region, in breakdown region, you are asking equivalent model of a Zener diode. See this one now. this is my Zener diode. This is the symbol for Zener diode, you know. Cathode look like a letter Z. Cathode, anode. This is the Zener diode specified with the breakdown voltage VZ equal. Right, operated in reverse bias, you say, like this. So supply resistance, this is the case. So this is my supply equal, and that applied voltage should be greater than or equal to VZ, you say. Got it now? So it is a reverse bias, the current flows from cathode to anode equal. So these are the terminals of the diode. Some V0 I can call. This is the cathode, this is the anode. So according to the condition of equivalent model, what you say, sir? So this part I can replace. Just now I told that for the applied reverse bias voltage less than VZ, it acts as an open switch. It acts as an open switch. It acts as an open switch means no current in R. R look like B, short. No current in R means voltage across R 0, that look like act as a short. So V0 should be equal to Vi. V0 equal to Vi. Once the applied reverse bias voltage greater than the breakdown voltage, what you can find out there? So it can be operated as a constant voltage source. What is that one condition I can able to go? Like this. So this is the equivalent model of a diode. Cathode, anode. So this part I replace. So this is the current I said. So in the breakdown region, right, of applied voltage greater than or equal to VZ, the equivalent model of the Zener diode to be like this. So Zener diode look like as a battery. The terminal voltage of the Zener diode just equal to VZ. This is the ideal case. According to the ideal condition, no resistance of the diode, right? There the current increasing sharply without changing of voltage. So resistance, Ohm's law, according to the Ohm's law, you can call resistance RZ. Dynamic resistance of Zener diode in breakdown region is dVZ by diZ. dVZ by diZ, sir, that equal to 0 ohm for ideal case. Why, sir? So voltage is constant, current increasing very fast. So change of voltage 0. Change of voltage 0, current change is more in the breakdown region. If I go for practical case, sir, voltage is almost constant but not 100%. So minimum, that is 1 to 15 ohms for practical. So ideally in the breakdown region the resistance is 0, sir. Practically small changes of voltage is there such that the resistance in the breakdown region is minimum even in reverse bias. So what is the practically equivalent model of the Zener diode, sir? Like this. So it look like a voltage source with a small resistance. Being a voltage source, resistance should be in series like this. This is the cathode, this is the anode of a diode. So this is IZ. So what is the terminal voltage of Zener diode, sir? The terminal voltage V0 equal to what you can call, sir, VZ plus IZRZ. So according to the practical case, the output voltage is not 100% constant. The output voltage is changing due to IR variations by RZ. According to the ideal only, it is look like a good voltage source. While you can go for practical case, sir, there is a small voltage variations you find out by means of that IZRZ. So practically you can find out some resistance because in breakdown region small changes of voltages are there. According to the ideal condition, no change of voltage, sir. Voltage is constant in the breakdown region such that dynamic resistance 0. While you can go for practical case, sir, the resistance is there because small voltage changes you may find out. So this is the equivalent electrical model of a Zener diode in breakdown region where it look like a voltage source. This is the case. This one he asked. And so now these things. So you can check out the next question now. Given that what are the specifications of Zener diode equal? So already you know that Zener diode mainly operate in reverse bias of breakdown region, and Zener diode should be specified with some specifications. What is that one you can check out? So this would be the VA characteristics of Zener diode of reverse bias, you know. So Zener diode mainly operate in reverse bias. So this is the reverse bias graph of Zener diode, you know. So this is the reverse bias voltage, and this would be the what? Reverse bias current you can call. If you sketch the characteristics of Zener diode in reverse bias, what the thing you can expect means this is the graph you may find out, right? Up to some portion the current is negligible. Once you reach a particular point that is called as a knee point you can call, where the voltage is called as a breakdown voltage, you say. where you find out that there is a sudden breakage of so many covalent bonds such that the minority current can increase sharply, keeping the voltage almost constant. Now you can able to examine what are the different characteristics of the Zener diode, right? So one of the specification of Zener diode is what means, first one of that is breakdown voltage. So this is the one of the specification of a Zener diode you call, that is called breakdown voltage you call. So what is this breakdown voltage means? It is the reverse bias voltage at which there is a sudden increase of current. It is the reverse bias voltage at which there is a sudden increase of current, keeping the voltage almost constant. So that is called as a breakdown voltage. And you know that because of its sharp breakdown, Zener diodes are commonly called as a breakdown diode, right? What I told you, it is the reverse bias voltage, right, at which there is a sudden increase of current, you know, there is a sudden increase of current, keeping voltage almost constant. So that should be the breakdown voltage you define, at which the voltage is almost constant, you call. Confirm now? At which the voltage is almost constant. So Zener diodes are available in the market with the breakdown voltage is ranging from 2 volt to 200 volt, you can call. So this is one of the specification of Zener diode. And one more important thing of the specification of the Zener diode now I can able to go, that should be called Ni or minimum Zener current, you can call. One more specification of the Zener diode I can come back. So that is Ni or minimum Zener current. So this is that one now. This is IZK or IZ minimum also you call. So this is the minimum Zener current required to maintain the voltage regulation. What is the minimum current of Zener you require to maintain the voltage regulation? That to be called as a minimum Zener current or Ni current you can call. For that, the condition of that one is applied reverse bias voltage must be greater than or equal to breakdown voltage. So Zener diode in reverse bias to act as a regulator, provided that the applied voltage variation should be greater than or equal to Vz. So if the applied voltage greater than or equal to Vz means this current should be possible. So you are in breakdown region. Confirm now? So one more specification what I can call, Ni or minimum Zener current I call. Ni or minimum Zener current I say, that is IZK or IZ minimum. Okay. What is this Ni or minimum Zener current means? I told you it is the minimum current required to maintain the voltage regulation you call. Understood now? It is the minimum Zener current, confirm, required to have regulation. So what is the minimum Zener current to maintain the voltage regulation? That to be called as a IZK or IZ minimum you can call, right? That is the minimum Zener current you discussed. And so now sir, right, for this what is the condition this one means? For this, applied reverse bias voltage V must be greater than or equal to Vz. Condition for this, applied reverse bias voltage should be greater than or equal to Vz. Confirm? Suppose if the applied reverse bias voltage V less than Vz, so it has no breakdown, you call, you are in this region, so no breakdown is there. So Zener act as an off switch, like ordinary diode. Confirm? So in the reverse bias, for the applied reverse bias voltage less than Vz, it acts as an off switch. For V greater than or equal to Vz, it acts like a voltage source. Confirm of this thing? Okay. So next, one more specification of this one you call, that is dynamic resistance, that you discuss something already know. So third specification I go, that is what you can call means dynamic resistance you say. Third one of that I go. This is one more specification I call, that is what you say sir, dynamic resistance you say, RZ. So this is the another specification of a Zener diode, and you calculate this dynamic resistance in breakdown region. So this would be calculated in breakdown region you call. So in breakdown region of the Zener diode you calculate this. So what is this dynamic resistance means? That you know that change in voltage to the corresponding change in current ratio. Change in voltage by change in current you can call. So you know that per ideal case in breakdown region voltage is constant, means change of voltage 0. This is 0 ohms. This is for ideal. Confirm? For ideal case the dynamic resistance 0 you can call. If I go for practical case, what you can say means this would be minimum. So for practical case it is minimum, that is how much you say, 1 to 15 ohms. This is for practical case you say. Why sir? Means in practical condition small variations in the breakdown region you can find out for voltage. In the case of breakdown region of small voltage changes you find out, such that instead of saying 0 ohm it has some minimum resistance. It have what sir? Some minimum resistance. Understood on this? So now we can able to examine the next one more specification, that is called what sir? Means power rating you can call. Now I can able to examine one more thing, that is what you can call power rating. So every Zener diode must be specified with the power rating you can call. Not only Zener diode, for every electrical electronic component you know that the power rating is specified by the manufacturer. That is a standard value. What is the power rating? You know, power rating represent the maximum power allowed by a body without any heating. Maximum power allowed by a body without any heating effect you call. So in the case of Zener diode, the manufacturer can specify depending on the doping profile, both breakdown voltage you can specify, and as well as what you can sir? Means this power rating also can specify. So indirectly the power rating indicate how much is the maximum current allowed by a Zener diode without any heating effect. Confirm now? So without any heating effect, how much is the maximum current allowed by the Zener diode is specified by the power rating. Confirm? So one more I can go sir. Power rating you call, that is denoted by PZ, right? What is this power rating I call? It represents the maximum current, and so now it represents the maximum current, that is maximum Zener current you call, maximum Zener current allowed without any heating effect you call. So without any heating effect, how much is the maximum Zener current that to be allowed, that to be indicated by the power rating. So you know that power equal to product of voltage into current. Then what is that maximum current you can call? Iz equal to Iz max, right? That equal to PZ by VZ you can call. So the current must also be within the limit of Iz max, so that the Zener diode do not get overheating effect. If the Zener current passing through the Zener diode is greater than Iz max, that Zener diode can overheated to be burned out. That's the case. Now, so these are the specifications of the Zener diode. So from this graph you can find out the Zener diode look like as what sir? Means current limiting device. Zener diode look like as what sir? Current limiting device. The minimum current is Izk and maximum current is defined by the power rating, so that is called Iz max. This is the case. So in this region the Zener diode can act as a regulator. Confirm? So Zener diode is a current limiting device, limits the current between Izk and Iz max for safe regulation you can call. And one more thing you remember now, so here the breakdown voltage is depending on the factor that already I told you, the zero breakdown voltage depending on what sir? Means doping. So what the thing you can find out means this breakdown voltage is inversely proportional to doping. Higher the doping, lower the breakdown voltage. So as doping increasing, the breakdown voltage goes to be decreasing. Based on that, you know, in the case of tunnel diode, because of too strong doping, the breakdown comes too close to 0 volt. By that I told you, the tunnel diode do not prefer to be used as a variable, do not prefer to use as a voltage regulator. I told there. Check out now this. So these are the 4 specifications of Zener diode, right? Based on that, it can look like to act as a regulator. What are the specifications? Breakdown voltage, dynamic resistance, right? Minimum current, that is knee current, and one more is nothing but maximum current defined by what sir? Power rating. So Zener diode is a current limiting device. not a voltage limiting, it is a current limiting device, and as well as voltage reference device we call. Zener diode is a current limiting element as well as voltage reference device. Got it now? Check out the next question now. Why Schottky diode is called a hot carrier diode? So it is not a PN diode originally. Schottky diode is a metal to semiconductor diode. So as compared to the remaining other diodes, it's not a PN diode. It is what sir means? It is a metal to semiconductor diode you can call. So it is not PN junction body. It is a metal to semiconductor device you can call. This metal may be gold or silver or platinum. Other side is a semiconductor is N-type semiconductor of silicon. So it is a body of metal to semiconductor diode you can call. See this one now, metal is a conducting element, so the current carriers are electrons. In N-type semiconductor also the current carriers are electrons. So entire body the current carriers are only electrons, such that it is a unipolar device. And one more thing as compared to the other diodes, what's here the barrier effect is not exist. So the barrier effect is negligible, you can call ideally zero you can say, so that you do not have any internal junction capacitance. As compared to the ordinary PN junction device, it has no internal junction capacitance, indicating that this Schottky diode is free from barrier effect and free from internal capacitance and maintain its characteristics as well as the applications even at high frequency. Even at a high frequency you can call. So look like ordinary PN diode, it can also be used as a switching element. It can also be used as a switching element. And as compared to the ordinary PN diode, whose switching response is fast. Why do you call the switching response is fast? Means because of the barrier effect is negligible, opposition to the carriers is not there, so that the switching response is somewhat faster as compared to ordinary PN diode. And probably this Schottky diode is operated in what means operated in forward bias we call. So this one now, keeping the metal side to be at a positive potential with respect to the N side to get the conductivity. So why it need some forward bias voltage means, as compared to metal side, the electrons of N side have lower energy. So metal is a conducting element of free electrons, you know. So whenever you can compare the electrons of metal and N-type semiconductor as compared to the N-type semiconductor of silicon, the electrons of the metal side have high energy. So the current is caused by the flow of electrons from the semiconductor to metal. But because of their lower energy, this metal side electrons do not allow them. So to carry these electrons of the N-side semiconductor, N-type semiconductor to the metal side, now we can able to give up extra energy to the electrons of the N-type region. Now, so in order to carry these electrons towards metal side, you can able to provide extra energy to that. That extra energy to be done by this applied forward bias voltage. This is a negative potential given to the N-type material. So by that, the electrons energy on N side to be increasing. With that increased energy, this N-type electrons now called as a hot carriers. They can be called as what, sir? Hot carriers, and they can drift towards metal side. They are drifting towards metal side. Here current by drift mechanism. They drift towards metal side to produce the current like this. So here electrons are moving from N-type to the metal region and getting energy by the applied source. By that they are called as a hot carriers. By that only the conductivity possible. Based on that, this person to be called as a hot carrier diode. Hot carrier diode. Look like a PN diode, it is also a switching element, and it is a person to be used as a rectifier. Sir, already ordinary PN diode is there as a rectifier. Again, why do you call this Schottky diode as a rectifier? Means your ordinary PN diode can rectify the signals of AC of low frequency only. At high frequency, ordinary PN diode can lose the rectification property because that person suffered by internal capacitance, junction capacitance. So it do not act as a switching element at high frequency. So if I go for Schottky diode, it is free from barrier effect, free from junction capacitance. So this is a person to be preferred to use as a rectifier at high frequencies. So who is a person that to be used as a rectifier at high frequency means Schottky diode. Confirm? What I told you, it is a unipolar device I call, means current by only electrons. Confirm? It is a body of unipolar device. Right, metal should be gold or silver or platinum I call. So operated in forward bias I told you. Operate in what? Forward bias I call. So with applied forward bias voltage, the electrons of N side get energy called hot carriers. Confirm now? With applied forward bias energy of electrons on n side increase called what, sir? Hot carriers. Increased energy called hot carriers we call, and they drift towards metal side. They drift towards metal side to get current. Confirm? So barrier effect is negligible, ideally zero you call. So no junction capacitance, it is free from junction capacitance I call. Confirm now? Barrier effect is zero ideally or negligible you call. Understood now? Barrier effect is negligible, alright? No barrier effect you can call. And junction capacitance is also not there and has no junction capacitance. So right, you know that whenever the PN junction body is free from junction capacitance, it maintains its properties even at high frequency. So it is preferred to use at high frequency you can call. It is preferred to use at high frequency, and due to its switching property it is used as a rectifier at high frequency you can call. Right? Used as rectifier at high frequency, and its switching response is faster. So this is the Schottky diode. So why do you call the Schottky diode as a hot carrier diode means? So the electrons of n side can get extra energy from supply of forward bias. By that they are called increased energy carriers are called as a hot carriers we call, and they can drift towards metal side to produce the current. Because it is free from internal capacitance, so it is used as a rectifier at a high frequency. Got it now? Check out the next one. What is LED? How it differs from ordinary diode? LED stands for light emitting diode you can call, and LED is nothing but what, sir, means a photosensitive device. So it is a photosensitive element you can call based on photoluminescence effect. LED is nothing but what, sir, means emissive element you can call. So it is a person of what, sir, means it is nothing but a PN diode based on what, sir, means photoluminescence effect. So as compared to ordinary diode and LED, what the difference means? LED is a body of PN diode made by direct bandgap semiconductor where the energy is radiated in the form of light. And your ordinary PN diode is an indirect bandgap semiconductor body where the radiation should be come out as a heat energy like a current conductivity you can call. So ordinary PN diode made by germanium or silicon you call, and this LED is made by direct bandgap semiconductors like gallium arsenide, gallium phosphide, gallium nitride, all these things. And one more thing is, so as compared to ordinary PN diode, where that is a body of indirect bandgap semiconductor, LED is a direct bandgap semiconductor you call. So as compared to ordinary PN diode, in the case of LED, the carrier lifetime is less. So what is the carrier lifetime? The time for which carrier can stay before recombination you can call. So the carrier lifetime somewhat less as compared to that of ordinary PN diode, such that LEDs always gives the type of emission of light is nothing but a spontaneous emission. That emission of light is not be continuous, sir. As long as the supply is there, so they can able to emit the light. So that type of emission is a spontaneous we can commonly call. And in the case of LED, the intensity of the light output purely depending on the amount of forward bias voltage you apply. So how much is the intensity of the light, sir? The intensity of the light output depend on the amount of forward bias voltage you can apply. And the color of the light depending on the type of semiconductor material you can use. The color of the light output depend on what, sir, means the type of semiconductor material you are using. So based on that, you are getting that light conductivity. In the case of what, sir? LED you say. Got it now? So LEDs differ from ordinary diode is what, sir? This is the way you call. If it comes to LED, this is what, sir, means ordinary PN diode you call. If I just take a comparison condition, so it is direct bandgap device, you know. It is a direct bandgap device, confirm. It is indirect bandgap device you say. It is an indirect bandgap device. Understood now? So example are germanium, silicon, you know. So here the examples, you know, gallium arsenide, gallium phosphide, gallium nitride, like this. Now. So as compared to ordinary p-n diode, lifetime is less, carrier lifetime is less, you say. Lifetime is more for carriers than compared to the direct band gap. Confirm. So it is a person radiates light energy, emits light, you call. It emits light, it emits heat, that is nothing but electrical conductivity can call. Nothing but emits heat, you say. Nothing but causing current, conductivity of current, you can call. Okay. So LED is nothing but a faster switching element as compared to ordinary p-n diode. Switching response is faster than compared to ordinary p-n diode, right? And this LED can able to give the light. LED gives the light depending on the type of semiconductor material, you can call. Okay, check out this. So in LED, if you go, in LED, if you consider what is the thing you find out, sir, means, right, the light output depend on the type of semiconductor you are using. So depending on the type of direct band gap semiconductor used, the light output can define. Suppose if I use gallium arsenide, it can give infrared light. It is a person that gives infrared light. If I use that one with the gallium arsenide, you say. Now, if I use gallium arsenide phosphide, it gives red light, you say. If you use gallium phosphide, it gives green. Now, it is a person that gives what, sir? Green. If I use that on gallium nitride, it gives blue light. And where it gives the light, remember now, the LED body gives the light only in forward bias, where the principle is look like same as ordinary diode. The recombination of electrons and holes can radiate that what, sir, means light conductivity. In ordinary diode, that recombination can able to convert as a current conductivity, can call. Here, the recombination of the carriers can be converted as a light conductivity, can call. So it emits the light in forward bias. And why don't emit the light in reverse bias means, in reverse bias, the recombination of minority carriers you may consider, and the recombination of minority carriers is less, so that the light output is very, very less, you can call, or such that in reverse bias it is a person to be act as a off switch. So this LED body can able to give the light in mainly forward bias. The intensity of the light output depend on the amount of forward bias voltage you apply. So the intensity of the light output depend on what? The amount of forward bias voltage you apply. And this LED can emit the light, right? And that emitted light can travel up to certain length. That length is known called what, sir, means wavelength, you can call. So what is the wavelength of the emitted light means? That is defined by lambda. Lambda equal to hc by Ez. So wavelength of the emitted light equal to what, sir? Lambda equal to hc by Ez, you can call. Sir, h stands for Planck's constant, c stands for velocity of light, Ez stands for energy gap. So that the wavelength of the emitted light is inversely proportional to energy gap. The wavelength of the emitted light is inversely proportional to energy gap, you can call. If I minimize this, this is the formula, like this you can call. Lambda equal to 1.24 by Ez. So this energy gap is in electron volt, and this lambda to be measured in micrometers. So this is the formula for calculation of wavelength of the emitted light, you can call. So the wavelength of the emitted light is inversely proportional to what, sir? Energy gap, you say. See this one now, you know that three primary colors are red, green, blue. So three primary colors are what, sir? Red, green, blue. If I go for the wavelength of the red light is greater than wavelength of the green light, greater than wavelength of the blue light. This is the case. Wavelength of the red light is greater than wavelength of the green light, greater than wavelength of the blue light. Then their corresponding energy gaps, what, sir, means? The energy gap of red light is less than energy gap of blue light is less than energy gap of what, sir? Green light. So energy gap of green light less than energy gap of blue light. This is that one now. So wavelength inversely proportional to energy gap. Based on that, you remember now the energy gap of red light is nothing but less than green, less than blue. And you know that their internal barrier potential, already you know barrier potential is directly proportional to energy gap. Then what you find out means the barrier potential of red light is less than the barrier potential of green light is less than the barrier potential of what, sir? Blue light. This is the case. So the barrier potential of red one is less than green, again less than what, sir? Blue, you say. So three primary colors are red, green, blue. What are the conditions are there? Their internal barrier potential should be like this. And what are the applications of LED? LED is a fast switching element, you can call, and it is one of the key person, remember now, used as a light detector in fiber optic communications. It is used as a light detector in, sir, it is used as a light source, sorry, it is used as a light source in fiber optic communications, where light detector is a photodiode. Now, LED to be used as a light source in fiber optic communications, LED to be used as a light source in fiber optic communications we call, where light detector is whom, sir, means photodiode. Photodiode used as a light detector in fiber optic communications. The person who to be act as a light source means there the light source is a LED. Light source is what you call LED. Confirm this one. And LED should be operated in forward bias. It do not operate in reverse bias you call. So in reverse bias it is a person to be act as a off switch. It emits a light only in forward bias. In reverse bias it can operate, that can act as a off switch. Do not emit the light. Do not emit the light. And LED having what, sir? Fast switching response. And this LED gives monochrome light. So not coherent light you can call. It is a person of gives monochrome light. Monochrome light is nothing but what, sir? Single color radiation. So the output color should be of a single radiation you can call. It do not give what, sir, means coherent radiation. Sir, coherent radiation should be possible in laser. Light amplification by stimulated emission of radiation you call. A laser beam is also a direct band gap semiconductor. There you can find out both monochrome and coherent radiation. Both monochrome and what? Coherent radiation you call. But this LED gives only monochrome light, and that to have only spontaneous emission. Confirm now? So if I compare PN diode and LED, PN diode is a direct band gap body, LED is a, sorry, PN diode is a indirect band gap body, and LED is a direct band gap body. So LED is a direct band gap body, PN diode is what? Indirect band gap body you call. In the case of PN diode, the recombination gives heating effect. In the case of LED, the recombination can give light conductivity can call. Sir, who are the indirect band gap metals? You know, germanium, silicon. And in LED, direct band gap semiconductors like gallium arsenide, these things can use. Gallium arsenide, gallium phosphide, like that. And carrier lifetime for direct band gap of LED is less as compared to the indirect band gap of PN diode. So this LED can give the light in forward bias, and in reverse bias it do not give the light, where it acts as a off switch. As compared to ordinary PN diode, in the case of LED, the switching response is fast. It have a fast switching response. And what is the wavelength of the emitted light means, that is indicated by this one. The wavelength of the emitted light is inversely proportional to energy gap. If I compare the main primary colors red, green, blue, you can call the internal barrier potential of red light is less than that of green, again it is less than that of blue light. Got it now? And LED to be used as a light source in fiber optic communications, where light detector is what? Photodiode. And not only this LED to be used as a, what sir means, 7-segment display device. LED to be used as what, sir? 7-segment display device, right? So it can also be used as a 7-segment display device you may call, and it can be used as on-off indicator in the electronic appliances. In all electronic appliances, the on-off indication to be indicated by LED call. Got it? Check out the next one. Is a photodiode is photoconductive or photovoltaic or both? Explain. Good. See this one now, the question. Photodiode is a photoconductive or photovoltaic or both you call. So my knowledge is that the photodiode is nothing but both photoconductive and photovoltaic it call. Sir, it to be photoconductive as well as photovoltaic, sir. Sir, the photodiode when operate in reverse bias, you see this one now, it can be look like a photoconductive. There with operated in reverse bias, based on the incoming light conductivity, the output minority current could be changing. So Under reverse bias condition, it looks like a photoconductive, sir, where for a given light intensity, the corresponding photocurrent can be increasing as a function of temperature. So, according to the condition of a reverse bias mode, it is look like a photoconductive. According to the photoconductive phenomenon, the incoming light energy converted into proportional current conductivity. Got it? Next, one more is there. It also acts as a photovoltaic, I can call. Without any applied bias, it look like a photovoltaic. Best example is solar cell. You know that solar cell is nothing but a PN junction without any applied bias. And this solar cell is nothing but PN junction diode without any applied bias. It look like a what, sir, means photovoltaic body. It is nothing but look like what? Photovoltaic body, you say. So photodiode is nothing but both photoconductive and photovoltaic condition, I say. Confirm? It is both photoconductive and what's the photovoltaic call. So photovoltaic phenomenon used in solar cell, photoconductive phenomenon considered by photodiode. So yes, for now. So according to the photoconductive phenomenon, what I told you, so you are converting light energy into proportional current conductivity, right? So a photodiode operate in reverse bias as a photoconductive element. Confirm? Where current flows as a function of incoming light intensity. This is photodiode photoconductive phenomenon as a function of intensity of light. Says for now what it is. Sorry. If you go for photodiode, observe now this. This is the case you call. Suppose this is a photodiode, I say. Operate in reverse bias, I call. Right, sir? That reverse bias voltage is a fixed one, not be variable. And on this junction area, you are introduced to fall on the, introduced to make a light energy call. So you are introduced to keep the light energy on that to fall. So with that junction temperature increases. So based on that junction temperature, on P and N sides, you know, the covalent bonds are break up that can able to give up the carriers of what's our means electron hole pairs you can call. Among that minority carriers on P side are what's our electrons, minority carriers here are holes. They can diffuse across the junction like this. So they diffuse across the junction and recombine each other and making that current to be increasing. So without applied light intensity, the current is small, that is called as a dark current. With the applied light intensity, the current increasing as a function of light intensity you can call that to be called photodiode. It is based on the photoconductive phenomenon. So whose graph should be like this? This is the graph of this. So this is the photodiode phenomenon you call. This is that. This is the dark current you can call. So that dark current flows without any applied light source. It is the same as ordinary diode reverse saturation current you can call. And with applied light intensity, the minority current is increasing as a function of light energy like this. This is some 50 lux, 100 lux like this, where the current flows as a function of what means a temperature you say. So according to this photodiode phenomenon of photoconductive phenomenon, right, this photodiode can be using to convert what means incoming light energy into proportional current conductivity. And what I told sir means it is also based on photovoltaic effect without any applied bias. It can also be based on photovoltaic effect without any applied bias you can call. Best example is what, sir? Solar cell you can say. So it is also based on what, sir? Photovoltaic effect you can call. It is also based on photovoltaic effect without applied bias. It also based on photovoltaic effect where incoming light energy converted into proportional voltage, sir. It is based on photovoltaic effect without applied bias. Confirm? So what is the best example of that one, sir? Solar cell, you say. Solar cell is a solar energy converter, sir, that is based on photovoltaic effect, you call. Right, based on what? Photovoltaic effect. So depending on the incoming sunlight energy, we are going to be defining what, sir, means the barrier potential across the junction and which should be taken across the terminals. So converting the incoming sunlight energy into proportional voltage. So there, no biasing voltage you apply to the solar cell, sir. Zero biasing voltage you can apply, such that the solar cell is nothing but what, sir, look like a photodiode with zero bias you can call. The difference between photodiode and solar cell is what, sir, means, sir, the spectral response of the photodiode is less because there the incoming light energy is concentrated on only junction area in photodiode. But in the case of solar cell, sir, there is a wider spectral response you can use because the incoming sunlight is fall on what, sir, means complete top surface area. So in the case of solar cell, we can allow the sunlight energy to fall on the complete top surface area, wider spectral response you can use. Whereas in photodiode, the spectral response is a narrow spectral response, sir, because the incoming light energy fall on the junction part only. So confirm now, the photodiode is either photoconductive or photovoltaic means, or both means he asking. It is both photoconductive and photovoltaic. With applied reverse bias, it look like a photoconductive, where converting the incoming light into proportional current conductivity. Without applied bias, it look like a photovoltaic you call, where the incoming sunlight energy converted into a proportional voltage. Got it now? Check out the next. What is reverse recovery time, we call? So this is the thing considered due to the charging storage property of a PN diode under forward bias, that you already know, diffusion capacitance. So you know that across the junction there is a barrier effect. That barrier look like a dielectric of a capacitor, you know. And you said that this junction capacitance is of two types. One is diffusion capacitance happen in forward bias, and one more is a depletion capacitance happen in reverse bias, I call. And I told that the diffusion capacitance have a charge storage property. Why means, in the case of forward bias it is possible, where you know that carriers are moving across the junction, such that carriers are moving across from one plate of the capacitor to the other plate of the capacitor, that have a charge storage property. In the case of reverse bias, you find out depletion capacitance. There you don't find any majority carrier charge storage property, only can find minority carrier charge storage, that is negligible. So main thing is, in forward bias, by the diffusion of majority carriers across the junction, there should be some charge storage property by the barrier. So this can able to causing some what's I mean, so difficulty in the PN diode. Now what is that one you can able to examine? Say so now, suppose I take some PN diode with zero cut-in voltage, means barrier potential I consider is a neglected one, and this is the load element. Suppose it is connected. Confirm. So this is the switch, I can say, suppose this is the switch I call, and two positions I take out. This is one of the position, this is one more position. Confirm. This is some supply of V volt. This is also same supply of V volt, but applied with the negative opposite polarity call. This is the switch that could be connected to either 1 or 2, I say. Suppose first case I keep the switch connected to the position 1, this one. So if I keep the switch connected to the position 1, what the thing you can expect, sir? The thing you can expect is the diode should be forward bias. I assume that zero cut-in voltage on the diode, such that the diode can conduct now. The diode can conduct and allows the forward bias current. So now I can keep the switch towards position 1, and thereby diode is forward bias, and thereby it allows the current to pass through the load. So what is that current I can call, sir? That current I can call some IF equal to V by RL ampere. So this is the current allowed by the diode. Now after that I don't consider any time. Now what will I do, sir? I can able to consider the time now. I can able to consider the time, and I set my time to 0 second. I set my time to 0 second, and immediately I can switch over from 1 to 2 now. Keeping the time t equal to 0, what can I do, sir? I can keep the switch towards position 2 now. So diode is suddenly reverse biased. So occur the condition of reverse bias, no my forward bias current can flow, you call. But here he say that even it is reverse bias, he say that this current can, what is the forward current you discuss, that forward current still can flow. Even in the reverse bias, that forward current can flow, but in reverse direction, but for a short interval of time. So understood my option? So even the diode is reverse bias, suddenly that current not become zero, same current still flows through the diode, but in reverse direction, and this current can flow forwards a short time, not for a long one. This current can flow for a short interval of time. Why this current still flowing for short interval of time, even diode reverse bias means? Because this is due to the charge storage property of the diode that is considered in forward bias. Due to the charge storage property of the diode in forward bias, so in the reverse bias, it requires some time to remove the stored charge from the body of the diode. To remove the stored charge from the body of the diode, it requires some time. That time is called as a reverse recovery time, during which the same forward bias current can flow, but in reverse direction. But in what? Reverse direction. See this one now? I can go. This is a simple thing I call. So this is the forward bias current. Suppose this is the current I call. This is the forward bias current that is flowing now. Now what I told, sir, I set my time to 0 seconds, sir. This is the 0 second time. At that time, I can immediately, what I do, sir, means switch over from 1 to 2 I can call. 1 to 2 I can call. Virtually you say that current may become to 0 I call, but I say that the same current flows but in reverse direction like this. The same current can flow but in reverse direction. So for how much time means that current is nothing but minus IF, that is what, sir, means minus V by RL I call. So virtually no current can flow. So ideal zero current, practically minority current can flow, but I say that same majority current still flows now, but not for continuous, sir. This is only for short time. That short time is called as a, what, sir, means switching time you can call. This is called switching time, some TS. After that over, now the current comes to decaying like this. This is called as a transition. So this is nothing but what, sir, means transition time. So by this time it can get recovered to the original value. What is that original value? That is called I0 you can call. What is that original value, sir? What is that original value means? That you can call as a, sorry, that you can call what, sir, means I0 you call. Just you can go. See this one now? So the current goes to be increasing, you can call. So the current goes to be maintaining for certain time, you can call. That is called what, sir, means switching time. After that, now the current come to reducing like this. And go back towards, sir, its ideal value of I0. This is I0, sir. That is reverse saturation current you call. So this time required is called as a transition time. Sir, by combining these two times, that is called as a reverse recovery time. The reverse recovery time is the sum of switching time and transition time. What is this reverse recovery time, sir? It represents the time required by the diode to remove the stored charge completely from it. So how much is the time required by the diode to remove the stored charge completely from it? That is called reverse recovery time. So after that reverse recovery time, the current is now the change towards, sir, means I0. Confirm now, sir? So if the diode is suddenly reverse bias, what I told, sir, the same current still flows in still flows through the diode but in reverse direction for a certain time. This is purely due to what? The charge storage property of the diode. Charge storage property of the diode that is considered in reverse bias. So how much total time you require to remove the stored charge completely? That to be called as a reverse recovery time. From the graph, this reverse recovery time is equal to sum of switching and transition time. What is the switching time? Switching time is the time in which the same forward current can flow but in reverse direction. That is this. What is this transition time? Where now the corresponding current is searching for its original value, and in this region the current is going to be decreasing. Right, and after certain time over, it can come back to the original value I0, that is minority current. So the sum of this switching and transition time is called as a reverse recovery time you can call. The reverse recovery time is the time during which the stored charge is completely removed by the capacitor. It is the time required to remove the stored charge completely from the diode, and thereby after that reverse recovery time, the diode current should be I0 only, not majority current. Confirm now? So if a forward bias diode is suddenly reverse biased, What I told, the same forward bias current still flows for a certain short interval of time. That is what call switching time I can call. And how it flows, sir, means that is due to the charge storage property of the diode that is considered in forward bias. Confirm now? After that, it can go for transition mode where the current comes to decreasing and find out its ideal value, that to be I naught. So what is the total time is considered by switching and transition, that is called reverse recovery time. Reverse recovery time is the time required to remove the stored charge completely, right? That is called as a reverse recovery time we call. Check out what I told you. See this one now? If a forward bias diode is suddenly, what, sir? Reverse biased, forward current that is IF still flows but in reverse direction. Confirm? For a short interval of time. For what, sir? Short interval of time. And it is due to charge storage property of a diode in forward bias. So that charge storage now to be released by the diode in reverse bias, and is due to the charge storage property of the diode that is considered in forward bias. So that removes, that is stored charge to be removed in the diode by reverse bias you call. So what I told you, reverse recovery time, what's your answer? Reverse recovery time is the total time required to remove the stored charge, to remove, what do you call? To remove the stored charge completely from it. To remove the stored charge, okay, completely from it. Stored charge completely from it, so that the current return to its original value, that I call TRR equal to TS plus, what you can call, sir, TT you can call. TS is switching time, TT is nothing but transition time. So completely from it, and current become its ideal value. What is the ideal value in reverse bias, you know? That is I naught, reverse saturation current. That is the case. Current become its ideal value, say what, sir, means I naught. So this is called as a reverse recovery time you say. So this is not much longer interval, this is to be a fraction of nanoseconds you may call. So anyhow, this is the time interval you may call, that is required by the diode to remove the stored charge from it and become to the original value of current. So become to have the original value of current, that is called what, sir? I naught you say. Got it now? Check out the next question now. What is BJT called? Sir, BJT stands for bipolar junction transistor. BJT stands for bipolar junction transistor. Confirm? It is simply called as a transistor. It is a bipolar junction transistor you call. Sir, it is a bipolar device like a PN diode. like a ordinary PN diode is a bipolar device. Bipolar device is nothing but indication that the current is due to both electrons and holes, you can call. Current is due to both electrons and holes, and as well as it have a bijunction. It is a bijunction device. Bijunction device is nothing but having two PN junctions. And what is this a transistor, sir? Transistor indicating that trans plus star, transfer resistor. So this transistor indicate what, sir? Transfer resistor. It indicated transfer resistor. So this transistor having an ability to carry the applied signal from low resistance to high resistance and make look like to act as an amplifier. So a BZ is a bipolar device. Here the corresponding current is due to both electrons and holes, you can call. And as well as it has two PN junctions, you find out. It is a body of transfer resistor and carrying the signal from low resistance to high resistance and make it to act as an amplifier. It was the first semiconductor body that can be used as an amplifier. Before the invention of this transistor, the amplifier circuit is made by what means? The vacuum tubes. And this transistor characteristics are similar to what, sir, means a triode vacuum tube. So this BZT characteristics are similar to triode vacuum tube, we can call. Confirm of this. So what is the BZT, sir? It is a bipolar device, you can call. So bipolar is what, sir? Current due to both electrons and holes. It is bipolar device. That is current is due to both electrons and holes, sir. It has two PN junctions, you say. It is a person of two PN junctions. Right? What I told, sir? It carry the signal from where to where? Signal from low resistance to high resistance. Low resistance to high resistance and act as amplifier. And act as an amplifier, sir. So it can also act as a switching element. It also acts as a switching element used in the design of switching circuits, I call it. Design of what, sir? Switching circuits. Confirm of this. So BZ is a bipolar junction transistor, sir. Means nothing but what? So this is a body of bipolar device where the current is due to both electrons and holes. It is a bijunction device, sir. It is a combination of two PN junctions, you can call. Okay, bijunction element. So what is the transistor indicate, sir? Transfer resistor, you can call. It can having an ability to transfer the applied signal from low resistance path to high resistance path and make it look like it act as an amplifier. And it can completely avoid the use of vacuum tubes, sir. So the invention of the transistors completely avoid the use of vacuum tubes. And the characteristics of this transistor is similar to triode vacuum tube, I call. Triode vacuum tube. It not only acts as an amplifier, sir, it itself also acts as a switching element used in the digital circuits. Okay. Check out next. What are the different operating modes of BZT? What are the different operating modes of a BZT you can call? Bipolar junction transistor. Sir, a BZT have two PN junctions, you can call. A BZT is nothing but considered as a combination of two types are there. One is NPN model, other one is what, sir? PNP model, you can call. So there are two types of BZT is there. NPN transistor, other one is PNP transistor, you can call. So in the case of NPN transistor, the main current carriers are electrons. In the case of PNP transistor, the main current carriers are holes, you can call. And these BZT have two PN junctions. One of the junction is between emitter and base, that is called emitter junction, sir. Another one is called collector junction, sir, between collector and base. Suppose if I go for NPN transistor, sir, this is the case. Right? N, P, N I call. This is emitter, this is base, this is collector. So one of the junction is between emitter and base, sir, JE you can call. One more junction is between collector and base, sir, that is called JC. So just now you discussed that this BJT can be used as an amplifier and a switching element I can call. So how do you know where it is a switching element, where it acts as an amplifier, sir? That can be defined by the different operating modes of this different operating conditions of both JE and JC. So this input and output junctions should be properly biased, sir, to make it act as what, sir, means amplifier, and as well as switching element you can call. Check up this one now, sir. What are the different operating modes of that I can call? So this is the mode of biasing, sir. Okay, mode of biasing I call. So this is the mode of biasing. Input junction ZE you can call. That is between emitter and base, sir. And one more is output junction JC, between collector and base you can call. And what type of application you find out? What is the type of application you find out, you can able to examine, sir? Check up now. So it can able to operate 4 different modes, sir. One of that one is called forward active mode. Sir, by default it is the mode of operation you can call a BJT. So default operation is a forward active mode. What is this forward active mode means? Where input junction JE, that is between emitter and base, you can call forward bias, sir. Output junction is between JC, sir, that is between collector and base, that is reverse bias, sir. Input between emitter and base, forward bias. Output between collector and base, reverse bias you can call. So carrying the signal from low resistance to high resistance act as an amplifier. So this is the place where it acts as an amplifier, you say. Next of this, it is nothing but saturation you call. Sir, here both junctions are made forward bias you can call. Here the BJT can act as a closed switch. It is the application where BJT can act as a closed switch you call. Next, one more is cutoff you call. In the case of cutoff, both input and output junctions are reverse bias. So in the case of cutoff, both input and output junctions are reverse bias you can call. Here the BJT can act as an open switch. This is the area where the BJT can act as an open switch you can call. And next one more is there, that is what, sir, means reverse active. That is also called inverted mode. Reverse active, opposite to forward active region you can call. This is also called as a inverted mode. Sir, default mode is forward active you call. This is also called reverse active you say. Sir, in this one now input is reverse bias, output is forward bias. Input is reverse bias, output is forward bias you can call. So in this mode the BJT can act as an attenuator. Attenuator means reduce the strength of the signal. Instead of increasing the strength of the signal, in this mode it can able to reduce the signal strength, right? So these are the operating modes of BJT. Default mode is called as a forward active mode. Sir, what are the condition of this voltages? So this is the emitter voltage here, emitter node voltage, sir. This is the base node voltage you can call. This is the collector node voltage you can apply there. So what are these node voltages in this corresponding biasing conditions now I can able to examine, sir? So yes, for now I can able to indicate that. So if I take a thing, so now we can indicate where the where the corresponding operating voltages, right? So this is VBE I call, base to emitter. This is VBC I call. Now I can able to indicate that one, sir, operating modes, 4 modes I told you. Confirm now, sir? Suppose this one I can go, sir, reverse active, sir. So reverse active is nothing but quite opposite to forward active I can call. There what the thing you remember, sir, means VC less than VB, VB less than VE, condition for it. VC less than VB, VB less than VE call. You already know that input is reverse bias and output is forward bias, quite opposite. VC less than VB less than VE, sir. All this is the thing that I made for NPN, sir. All these are the things that I can made for what? NPN you can call. If you go for PNP, less than become greater than become less than. Sir, quite opposite to this become a forward active, sir. Sir, forward active we can call, what the thing means, VC greater than, VB greater than, VE you can call. Confirm? So, one more condition I can go, sir, saturation. In saturation, what do you say, sir? VE less than VB as well as VC less than VB. Cutoff I can call, sir. In the case of cutoff, VE greater than VB, sir, and VC greater than VB. Confirm? These are the operating modes with the concerned node voltages I call. Sir, all this is the thing I made for NPN condition, sir. If I go for PNP, sir, so less than become greater than become less than. Just you can able to changing the conditions of that. Less than replaced by greater than, sir, greater than replaced by less than. For PNP model you can call. Now, sir, so these are the operating modes of a BJT. So there are 4 operating modes if find out that those are active mode, saturation mode, other one is what sir means, so cutoff mode, and in reverse active mode you can call. So the default mode of a BJT is called forward active region, where BJT look like to act as an amplifier by carrying the signal from low resistance to high resistance, you say. And other than that, you can find out that switching mode of operation, sir, those are saturation and cutoff. In saturation region, BJT act as a short circuit of closed switch. In cutoff region, BJT can act as an open switch, you can call. In the saturation region, both input and output junctions are forward bias. In cutoff region, both input and output junctions are reverse bias, you can call. And one more is there, I told reverse active, sir, that is quite opposite to forward active region, you can call. There input is reverse bias, input junction reverse bias, sir, output junction forward bias you can call, and BJT look like to be act as a attenuator, you can call. BJT can act as a what, sir? Attenuator. Confirm? Check out the next one. Is BJT is the current or voltage controlled? Explain, you call. So BJT is which type of controlled you call? Whether it is a current controlled or voltage controlled is going to be asking, sir. Now can able to examine what type of controlling of BJT it is. Sir, BJT is basically a current control device, whereas FET and MOSFET are voltage control devices. So BJT is basically a current control device. Current control device is nothing but what, sir? Any change in the output current controlled by input voltage. So in the case of BJT, any change in output current controlled by input voltage, controlled by input voltage. So, sir, in the case of BJT, any change in output current controlled by input current, sir. In the case of BJT, any change in output current can be controlled by input current. By that, it is called as a current control. If it is a voltage controlled, sir, any change in output current controlled by input voltage. So, that is done now in the case of FET and MOSFET. But as per BJT, it is a current control device where output current controlled by input current you call. Output current controlled by what, sir? Input current. Confirm on this? So based on this, even the output junction is reverse bias. In the case of BJT, output junction even it is reverse bias. How that majority current can flow means that is purely depending on input forward bias current. So I think that in the case of BJT, output junction reverse bias, there you can able to find out both majority and minority currents. Minority current can flow according to the reverse bias nature of the BJT. But other than that, it can also allow majority current. So how it can allow majority current in the output junction of reverse bias means that majority current not depend on the output of reverse bias, sir, that depend on input forward bias current according to the current controlled phenomenon. And so now BJT is what type of device? Current control device. Based on that, any change in output current controlled by input current. I think that using this one only, you can define the current gain factors, current amplification factors, alpha, beta, gamma. Okay. So what type of it is? It is a current control device. Not a voltage control device, sir. It is a current control device, that is output current can be controlled by input current. So it is also called as what, sir? Current controlled current source. It is called as a what, sir? Current controlled current source you can call. So even output junction is reverse bias, you can expect the majority current according to the current controlled phenomenon. Based on the reverse bias nature of the output junction, minority current flows. Other than minority current, it also have majority current in output or reverse bias junction. That is purely due to current controlled phenomenon. That is completely due to what, sir? Current controlled phenomenon you can call. Understand this? Check out the next one. What is Ebers-Moll model of BJT? What is Ebers-Moll model of BJT? Remember now, this Ebers-Moll model is applicable only for BJT, not for any other person. So this Ebers-Moll model is applicable only for BJT, you can call, not for any other person, you say. So what this Ebers-Moll model, sir, means? This Ebers-Moll model indicate that, so this Ebers-Moll model indicate that any change, sir, this Ebers-Moll model indicate that the BJT is equivalent to 2 PN diodes connected as back to back. This Ebers-Moll model indicates that the BJT is equivalent to 2 PN diodes connected as back to back. So it is applicable only for BJT, not for any other person. And according to the Ebers-Moll model, you say that the BJT body is electrically equivalent to 2 PN diodes connected as back to back. See this one now. What is that Ebers-Moll model? Suppose I indicate for NPN, sir. So this is the electrical equivalent model of a BJT that look like how many diodes? 2 diodes, you say, connected as back to back. So this is emitter, this is base, this would be collector. Emitter, base, collector. Suppose this is N type, you know, this is P type you call, and so now this is N type. So it is the combination of 2 PN diodes connected as back to back, you can call, sir. Now, so this is the input junction you can call, right? Across that I use some current source. This is output junction. Across that I indicate current source again. Confirm? So this is the output current source or current controlled current source you call. So this is a current source, or depending on input current you can call. This is what, sir, means current controlled current source. So indicating that any change in output current controlled by input current. Any change in output current controlled by input current you call. That is a current controlled current source. Confirm now, sir? And across input junction also I take one more current source, sir, that define input current. You say, sir, this is a input current value depending on input applied bias voltage. Sir, this is the input current value depending on the applied input bias voltage you can call, and this current source is called as a voltage controlled current source, you say. It is a voltage controlled current source, sir. This is a current controlled current source. This is the equivalent Ebers-Moll model for NPN transistor. For what, sir? NPN transistor you can call. So according to the Ebers-Moll model, BJT body is electrically equivalent to 2 PN diodes connected as back to back. It is electrically equivalent to 2 PN diodes connected as back to back. And I think that, you know, in the IC technology, what is the advantage of back to back PN junction, sir? Even by any mistake or by any chance, even any junction is a short, you do not allow the other junction to be short. Suppose if the collector junction is shorted, you do not make emitter junction to short. So back-to-back PN junction avoid the shorting of one junction by the other. So if any junction is shorted, which do not make the other junction to short. So both junctions are operating independent of others. So even this junction is shorted, it do not allow this one to short. Suppose if it is shorted, it do not make this one to be short. And one more thing, sir, this Ebers-Moll model is applicable for all operating modes of BJT, not a particular operating mode, sir. For every operating mode of BJT, this Ebers-Moll model should be applicable. That will be active mode, saturation mode, cutoff mode, inverted mode. For every operating mode of BJT, this Ebers-Moll model should be applicable. Confirm now, sir? So Ebers-Moll model represent what? It represents BJT, confirm, as what, sir? 2 diodes connected as back to back. It is electrically equivalent to 2 PN diodes connected as what, sir? Back to back you can call. And what I told, sir, Ebers-Moll model is applicable. Ebers-Moll model is applicable to all operating modes of a BJT call. For all operating modes of BJT, the Ebers-Moll model should be applicable, sir. For all operating modes of BJT, the Ebers-Moll model should be applicable. Understand this? Check out the next question now. Why base region is lightly doped in a BJT? So you asked the question is, why base region is lightly doped in a BJT? Now you can able to examine. In the case of BJT, three regions are there: emitter, base and collector. All the regions do not have the same doping level. So the emitter area is a highly doped one, collector area is moderately doped one. Among all the three regions, so base region is lightly doped one. Suppose now I can able to go for BJT of NPN structure. See this one now. This is a BJT of NPN structure I take out. So among all these things, so you find out the base should be a smaller area as well as it is what sir means lightly doped one. So base is having a smaller area as well as it is lightly doped one. So this is the base, this should be the emitter, and this should be the collector. Recall, it have the two junctions, you know. One is emitter junction between emitter and base, other one is collector junction between collector and base, you call. So among all the three regions, if we find out the highest doped is emitter. Among all the three regions, emitter is the highest doped one, and base is lightly doped one. Doping order is less. Confirm. And if you go for collector, that is moderately doped one, whose doping order is in between base and emitter, means the doping order of collector is greater than base and less than emitter. So the question he asked is, why the base region is lightly doped one, he asked. So the main reason is, in the case of base region, the current is mainly due to what sir means recombination. So by having a less doping, the rate of recombination reduces, such that in the case of BJT, the base current should be look like to be minimum. So not only that base is lightly doped, and as well as its area is small, and most of the space is occupied with the barrier again because of light doping. So most of the barrier can expanding into the base either across emitter or collector junction. The barrier effect, if we compare, that most of the barrier can be penetrate into the base because of light doping. So the effective base space is less, right, and as well as doping is minimum, so automatically it can reduce the chance of recombination. So rate of recombination is less, such that base current should be kept minimum in the case of BJT. So the main purpose to keep a less doping in the base region is to reduce the rate of recombination, such that the base current should be minimum. So based on that, you know, in the case of BJT, the collector current is almost equal to emitter current, you call. That's the reason. Understand this? So base is what I told you, lightly doped to reduce the recombination rate. To reduce the recombination rate. So in the case of BJT, in base region, the current is due to recombination of electrons and holes. So to reduce the recombination rate of electrons and holes, so that what I told that base current is minimum. So as base current minimum, what you can call means, then you say that in a BJT, the collector current is almost equal to emitter current. Collector current is almost equal to emitter current. So that's the reason. So that's the reason you say that the base is too lightly doped in the case of a BJT. Confirm now? Check out the next question. Which region of BJT has wider area and what is its necessity, you can call. So which region of the BJT has wider area it is? which region of BZT has wider area and what is its necessity is asking. Sir, in the case of a BZT, among the three regions, if we find out here, suppose here you can find out here, among all the three regions, collector region have wider area. So as compared to emitter and base, the collector region should have wider area. Why the collector maintain a wider area means, in the case of BZT, the power that can be dissipated as a heat considered in collector region only. The power dissipation not comes in emitter or base. The power dissipation as a heat is considered only in the collector region. So having a larger area, the heat dissipation should be done very easily so that the body never get overheating effect. So for that purpose, in the case of a BZT, the collector region choose to be as a wider area, mainly to avoid that overheating effect, you can call overheating effect. So what are the heat that is produced that can be cooled instantly by having a larger area? So that's the reason to maintain the collector have larger area. Understand this? So what I told you? So in a BZT, the power dissipation, confirm? In a BZT, the power dissipation as a heat considered in collector area. So not in emitter, not in base. And I think that you know what is the power dissipation of the collector region means. So that it defined as some collector voltage VCE into collector current IC you call. So this is the power dissipation in the collector region of a BZT. So the power that can be appeared as a heat in the collector region is VC into IC, where IC stands for collector current, VC stands for collector voltage you say. So by having a larger area, the heat dissipation should be done very easily so that the body never get overheating effect, you can call. Confirm now? By having a larger area, okay, the collector heat dissipation is done very easily call. Is done very easily you say. Right? So that the body can be free from what sir means overheating effect. By having a larger collector area, collector heat dissipation should be done very easily so that the body is free from overheating effect. So that body is free from overheating effect you call. So this is the main purpose, to have larger collector area. So why the BZT of right collector region have a larger area means mainly to reduce what sir means the heat dissipation you can call. So by that one the BZT look like be free from what sir means heat dissipation, nothing but heating effect you call. Now? So in the case of BZT, among all the three regions, collectors should be have a larger area mainly because of heat dissipation you say. Mainly because of what sir? Heat dissipation. Heat dissipation never comes in the base or emitter region, that considered only in collector region. Choosing of a larger area, the body can be cooled very fast such that the heat dissipation should be done very freely. So that's the case you say. Check out the next one now. Explain the current mechanisms used in a BZT. So explain the current mechanisms used in a BZT call. Says for now, the BZT have three regions you will know, that is emitter, base and collector, all this. So now you can able to examine this. This is the BZT. Suppose NPN model I use. This is emitter, base, collector you call. So base is a smaller area among all the things you call. So this is emitter you know. This will be the base. This will be the collector recall. This is the emitter junction ZE. This is collector junction ZC. Just now I told that among all the three regions, base would be lightly doped one as compared to emitter and collector, so that most of the barrier that could be expanding into the base, the barrier expansion into the emitter is too less than compared to base, like this. So now I indicated this. On N side of that emitter that containing a positive ions, on P side of the base that containing what means negative ions. Just I indicated the shaded area. So this is the barrier recall. This is the barrier effect across the input junction. And I can able to go for one more barrier effect across the collector junction. If I compare collector and base, you observe now as compared to collector, base is lightly doped one. Again, the most of the barrier expanding into the base as compared to the collector. So in the collector region, the barrier effect is less. This is the case. So either across collector junction or emitter junction, what you can call, sir, most of the barriers should be considered into the base. So the P type of the base region having negative ions, N type of the emitter and collector containing positive ions. And this barrier potential is approximately around 0.1 volt or 0.2 volt for germanium, around 0.5 to 0.6 volt for silicon transistor. So in the case of BZT, the conductivity is considered by the flow of carriers from what means emitter to collector. How do you provide that one means that to be done by the applied bias. Already you know what the type of biasing conditions means. There are four modes of biasing you can call: active mode, saturation mode, cutoff mode and inverted mode. Among all these three modes, the most popular one that is a normal mode of biasing is what means active mode. Default mode of operation of BZT is active mode you can call, where you find out input to be forward bias and output to be what? Reverse bias you call. Input to be forward bias and output to be reverse bias. And among this, you can observe now, among all the three regions, you already know that which region is highly doped one means. So that is nothing but what means emitter. Emitter is a highly doped region as compared to base and collector. So it is N-type region means more number of excess electrons. The number of excess electrons is a large number here, like this. So it have a large number of electrons. Here base is of opposite type of material, that is a P type here. The base is a P type means holes are the current carriers. There the base is a lightly doped one, so the number of holes is less. Because of less doping, the number of holes to be less. Holes are the majority but number of holes is less. Here it is a collector of N-type region you can call. The current carriers are electrons. It is a moderately doped one, like this. This is the case. So these are the current carriers in each region according to their doping level. Now I can able to operate in the active mode, keeping input forward bias and output is reverse bias. By that you can able to examine what type of current mechanisms I use in each region. So it is N types. Now I can able to keep to connect like this. It is a forward bias supply. Suppose this is called emitter supply I call. Right. Now I can able to keep this one as a reverse bias. Now I can able to operate like this. Positive terminal supply, negative terminal I call. This is VCC supply. I use two supplies. One is emitter supply, other one is what? Collector supply I can call. Let us see this one now. So here in emitter region, the current is mainly due to the diffusion mechanism. Why do you say diffusion mechanism? Means because emitter is strongly doped than compared to base. So independent of this applied bias, the carriers have a tendency to move from emitter to base only. What is the purpose of this bias supply, sir? The purpose of this bias supply is to make this barrier effect to be less. So to avoid the barrier effect, you can able to use the bias supply. So originally the carriers have a tendency to move only from emitter to base. No carrier can move from base to emitter. That's called diffusion phenomenon. According to the diffusion phenomenon, the carriers have a tendency to move from higher density to lower density side. So this is the flow of electrons you can call. So confirm now, in the emitter region, the current mechanism you can use is diffusion. Diffusion mechanism you may use in emitter region to get generate the current, and in the case of a BZT, the main current flow is emitter current flow, and that is due to diffusion you call. And electrons are flowing like this, the current due to which must be in a direction opposite for NPN. This is the case. So confirm now, emitter current IE is mainly due to diffusion of emitter carriers into base. Confirm, but amount of diffusion is more for a small change in voltage because it is highly doped one. So for a small change in applied forward bias voltage, more number of carriers are diffusing such that emitter current must be high value. Now come to the base. So what are the emitter carriers who are diffused into the base? Right there you can find out that opposite polarity carriers like holes you can call. There in the case of base region you can expect the current by the recombination process. So in the case of base region the current is due to recombination of holes and electrons. But amount of recombination is less, so that recombination rate is less. It is a body of indirect band gap semiconductor. The recombination converts that radiation as a current conductivity. So in the case of base region, the current is due to recombination of majority electrons and holes, but amount of recombination is less, such that base current should be minimum, like this. So in the base region, the current is due to recombination of electrons and holes. That current is called as a base current. But rate of recombination is less, base current should be minimum, we call. Got it now? So what are the emitter carriers who do not recombine here? Most of them injected into collector. So most of them injected into collector and attracted towards collector supply. So how many of the carriers can injected or jumped into collector means that can be defined by one of the characteristic of a BZT, that is called base transport factor. So base transport factor indicate how many of the emitter carriers, right, that can be injected into collector to convert as a collector current. So base transport factor is one of the characteristic that define the number of emitter carriers that are injected into collector to convert it as a collector current. So among these emitter carriers who do not recombine here, most of them jumped into collector and they can drift towards collector terminal like this. So in the collector region, the current is due to drift of carriers. Due to what? Drift of carriers. The emitter carriers who do not recombine, most of them jump into collector and drift towards collector terminal by this collector supply and generate a collector current whose direction is opposite to these electrons, like this. I see. One more current. So in the emitter region, the current is due to diffusion. In the base region, the current is due to recombination. In the collector region, the current is due to what's a drift mechanism. So most of the electrons can drift into collector, I can call, and one or two electrons, very few of the electrons can also go like this. But number of electrons going in the reverse direction, it is an attraction for electrons. But the number of electrons going like this is too less. So most of the electrons can go into the collector by the effect of this supply. Very few electrons can go like this. That's just one or two electrons or very few number you can call that do not define the current. The current in the base region mainly defined by the recombination of holes and electrons only. So the number of electrons going like this is too less, that do not cause any current. So anyhow, depending on the direction of these electrons, you define the current is this. So find out three majority currents you call IE, IB and IC. So IE is the emitter current I call, that is mainly due to diffusion of emitter carriers. So the emitter is highly doped one, diffusion rate is more, emitter current is high. One more is a base current I call. Base current is due to recombination of electrons and holes I told. But amount of recombination is less, so that base current is minimum. Got it? Next I call that what sir means collector current. So the emitter carriers who do not recombine, most of them can inject it to jump towards collector terminal or drift towards collector terminal. According to the base transport factor, the more number of emitter carriers can drift towards collector terminal you can call. So base transport factor indicate how many of the emitter carriers that are jumped into collector to convert as a collector current. So all these are the majority currents. And in addition to that, we can also find out one more current called minority current that flows across reverse bias collector junction. Across reverse bias collector junction you can call. You don't expect that minority current in emitter junction because it is a forward bias. So it is a reverse bias junction. There you can expect that minority current. That minority current called as reverse saturation collector current. Reverse saturation collector current IC0. And it is due to recombination of minority carriers. Who are that minority carriers? In the base region, those are electrons. In the collector region, these are the holes. So these minority electrons and holes, they can combine across this collector junction. They can recombine across the collector junction and generating this minority current. Look like ordinary PN diode. And this minority current is strongly dependent on temperature. Almost doubles per every 10 degrees centigrade increase in temperature. So in addition to this majority collector current, in the collector region, you can expect some minority current that is mainly due to recombination of holes and electrons you can call. right? So this minority current is almost the same as your diode reverse saturation current you can call. So it here also this minority current is about microampere for germanium and nanoampere for silicon, almost doubles for every 10 degrees centigrade increase in temperature you call. So what the direction of this minority current means? You know that minority current always move from cathode to anode. So this is the direction IC0. So along with the majority current, the minority current IC0 also flows across reverse bias collector junction due to recombination of minority carriers, and it is strongly dependent on temperature. So small thing you can call here, sir, it is a reverse bias junction, so originally minority current is true. You don't expect any majority current in reverse bias, but why this majority current flows even it is a reverse bias junction? That is commonly asked question you call. So the answer for that is, he said that BZ is a current controlled. Any change in output collector current controlled by input current. By that you know BZ is a current controlled. So this collector current is not depend on this output supply. This collector current mainly depend on emitter current IE, and IE is nothing but a forward bias current. Based on that, BZ is called as a current controlled. So in the case of reverse bias collector junction, the majority current flows according to the current controlled phenomenon, and minority current flows according to its reverse bias nature. And in the NPN, if you find out IE is outgoing here, remaining currents are incoming. IE is outgoing there, IB, IC are incoming here. If you go for PNP, A to Z is same except the carriers are opposite. So there I is incoming, remaining are outgoing you call. So what are the current relation you find out in a BZ means, you know that IE equal to IB plus IC plus IC0. So as long as the majority current is there, minority current should be ignored, such that commonly you say that IE equal to IB plus IC. Confirm? Again, IB is 2 less than IC you call, because recombination rate is less, you know. As IB is less than IC, then commonly you say that IC close to IE. Confirm all these things? So check up what are the current mechanisms I told you. What I told you? In emitter, right? In emitter, current is due to what, sir? Diffusion of whom? Emitter carriers. Into base. Confirm? In emitter, current is due to diffusion of emitter carriers into base, and diffusion rate is high, so that emitter current is high, and it is nothing but what, sir, means the main current flow is nothing but a diffusion current, and that is nothing but what called emitter current IE. Next, what I told, sir, base current IB is due to what, sir? Recombination. Recombination of electrons and holes, sir. And I told that this recombination rate is less, so that base current should be minimum. Next, sir, collector current is due to a drift of emitter carriers towards collector terminal. Drift of emitter carriers towards what, sir? Collector terminal, which are not recombined in the base. What are the emitter carriers which are not recombined in the base, that are drift into what, sir, means that are drift towards what, sir? Collector terminal call, which are not recombined. Is it clear to you? So the emitter carrier that are not recombined in the base, that are jumped into collector and drift towards collector terminal to convert as a collector current. So that is identify one of the characteristic called base transport factor also. Okay, check out the next one. Explain the effect of minority current in a BZT. So this is also most useful one. So what is the effect of minority current in a BJT you can call? Just now you learn that in the case of BJT, the collector junction is reverse biased. There, according to the current controlled phenomenon, majority current flows I told, and according to the reverse biased nature, the minority current can flow I told. Means in the case of BJT, the total collector current IC equal to sum of majority and minority current, students. Total IC equal to sum of majority current and minority current equal. Majority and minority currents. So if we compare common base, common emitter and common collector regions, so among all these things, the minority current effect look little bit less in common base, and this is more effective in emitter, common emitter and common collector. And what is the minority effect you may consider in common emitter, which is the same in common collector also. So who should be suffered by the minority current effect means that is both common emitter and common collector, and the minority current effect look little bit less in common base transistor. In common base transistor. Let us see this one now. How this is I can able to examine for common base and common emitter, and what is the minority current effect you can discuss in common emitter, which should be same in common collector. Now come back here for common base first. Now I can go for common base. Suppose this is a common base transistor where base look like a common terminal for input and output. I think that you know. This is the common base of suppose NPN model, emitter, base, collector. Got it now? So this is NPN model. Confirm. Input made forward bias, you know. Output made reverse bias you call. So now I can keep input to be forward bias by input supply. This is that. This is emitter supply I call. One more thing, I can keep output to be reverse bias by means of collector supply I call. Got it now? So here the current that is flowing, you know, IE other than common current. Output current, you know that IC. IE outgoing means IC incoming. You know this. And according to the condition of active region, you know that the minority current flows across reverse bias collector junction I told. Across what, sir? Reverse bias collector junction. Says for now. The minority current flows across reverse bias collector junction you call. The minority current can flow across reverse bias collector junction only. That is nothing but this one. So there the corresponding current that is passing, you know, that is called IC naught. Now I can able to indicate that current is what you can call, sir, IC naught you call. That current is what you say, IC naught. Confirm, students? So now I indicate this current flows. Let us see this one now. I want to know the effect of this minority current in a BJT. That I need to know in common base. I want to know this effect of minority current, say IC naught in the case of common base. So for that, sir, as long as the majority current IC is there, what is the minority current? It is ignored. So this minority current is effective if no majority current at that time. So if you wanted to know the effect of the minority current, for the time being, you keep that majority current to be 0. For the time being, you keep that majority current to be 0. Means you can keep this IC equal to 0. So but IC is depend on what? IE. Already know BZ is a current control. So this IC should be made 0, keeping IE equal to 0. How to keep input 0 means keep this input as a open. For the time being, you keep this input supply as open. So if I keep this input supply open, automatically I can able to get the effect of that minority current, sir. Check up now. What is that total collector current I go? For common base, total IC I go. First one, majority current, sir. In the case of common base transistor, the majority current, that is nothing but IC, is flowing as a function of input current IE, and gain factor, I think that you know, alpha equal to IC by IE, you know. Then IC equal to what? Alpha IE. This is that one. This is the majority current, sir. Got it? Now I want to know the minority current, sir. For the time being, minority current, if you want to know the effect means, keep that majority current 0, that done by keeping input current 0, indicating that input is open. So under that, the minority current flowing across collector junction, named as what, sir? ICBO. This one. That minority current named as what, sir? ICBO. Minority current flow between collector and base terminals. Minority current flow between collector and base terminals with input emitter as a open. That is that. Minority current flow between collector and base terminals, keeping input emitter as a open. So at that value equal to how much there? So across collector and base terminals, which current flowing there? IC0, where the input is open, sir. Where ICBO equal to IC0 only. ICBO must be equal to only IC0, sir. Then you see this one now. IC0 is very small, sir. It is order of micro or nanoamperes, not much high. Then what is the total collector current for common base? You can call IC equal to alpha E plus IC0. So in the common base circuit, the minority current effect is less. In the case of common base circuit, the minority current effect is what, sir? Less, you call. Check up, is it right or not? See this one now. So if I keep input current constant, according to the condition, you mustn't should say that output current also constant. If the input current is constant, output current must be constant. Whether it is constant or not means depend on temperature, you call. So IC0 depend on temperature. For every 10 degrees centigrade, this IC0 doubles. But even it is doubles micro, sir, even it doubles not a problem, because whose order is micro or nanoamperes. So that keeping input current constant, the total change in collector current due to temperature is how many times here? Only one time the IC0. Only one time the IC0, and IC0 is negligible, you can call, such that in common base circuit the minority current effect is less, and common base circuit is quite stable. Minority current effect is less, common base transfer is quite stable. It should not asking any further stability from you. That's the case of it. Kanbana, what I told you? Keeping IE constant, that is input current constant, right? The change in IC, and so now change in IC due to temperature, how many times, sir? Is just one time the IC0. How many times IC0? Just only one time the IC0 you can call, and IC0 is negligible. IC0 is negligible, sir. So that indicates that common base circuit is quite stable. That is, CB is quite stable, sir, which don't need any stabilization. CB transfer is quite a stable person, you call. Check up the same thing now for common emitter also now. Now I can able to go for common emitter circuit, sir. How it is for common emitter I can go? Check up now for common emitter, sir. Now I can able to go for CE now. If I go for CE circuit, this is the case, sir. Emitter, base, collector you call. So keep operating in active mode, input to be forward bias and output to be reverse bias you call, sir. Input made forward bias, sir, output to be reverse bias you call. Check up now, this is P type, keep to connect positive. This is N type, like this. So this is called as a base supply you call. So here collector and emitter are both are N-type terminals. How do you keep in reverse bias or means either one to be connected with the positive potential to act as a reverse bias originally. Either collector made positive or emitter made positive to act as a reverse bias, sir. This is that one now. Both emitter and collector of same type, you know. Sir, how to operate in reverse bias means either collector made positive with respect to emitter or emitter made positive with respect to collector. But here in NPN particularly, we can able to operate in reverse bias, keeping collector to be positive with respect to emitter. Never prefer emitter positive with respect to collector, because in NPN current carriers are electrons and you need to make that electrons to move towards collector. In order to drift the electrons towards collector, it is mandatory to keep collector should be positive. So because here to drift the electrons towards collector, what you say means, so collector should be made positive with respect to emitter, sir. This is the case. Confirm? This is some collector supply I call. So it's not exact reverse bias, only one node to be at reverse bias with respect to the other. So what are the corresponding terminal currents in that? So I is outgoing, sir. Here it is IB call. Here it is IC call. And you know that it is our reverse bias body, sir. Their minority current flows. According to the condition, you know, sir, the minority current IC0 flows only from what, sir, means across collector junction, that is between collector and base. This one, sir. Here minority current IC0 flows. That flows between collector and base. Now I can able to examine what is the total IC here. Total IC equal to sum of majority and minority currents you can call. Sum of majority and minority currents you can call. Sir, what is the majority current? So majority current IC is a function of input current IB you can call. So what is the formula, sir? Here current gain factor is beta. Beta equal to what you say? IC by IB. Then IC equal to what? Beta IB you say. So the majority current is beta IB. Got it? This is the majority current. So there the output current is a function of input current you call. Now I wanted to know the minority current. Sir, same story as compared to common base. To know the effect of minority current, for the time being, you keep this majority current 0. How to keep this 0, sir? This current depend on input current. Keep this one as a 0. How to keep this one as a 0, sir? For the time being, you keep this one as a open. Then only minority current flows. That minority current flows between output terminals of collector and emitter, sir, with input base as open. That is called ICEO. ICO stands for minority current flow between collector and emitter terminals with other, that is base as a open. It is a minority current flow between collector and emitter with other, that is base as a open. So it is the minority current flow between collector and emitter terminals with other terminal, that is base as a open, sir. So what is that value? You can check out. Where ICO, minority current flow between collector and emitter, sir. Sir, you see this one now. From collector to base, the current that is flowing is IC0. Got it? From collector to base, the current flowing is nothing but IC0. And from base to emitter, what are the current that is passing, sir? That is boosted value of this one, sir. How much current, sir? That is beta IC0. So what is this current? After reaching the base terminal, that can able to be amplified by beta times and to give up a new value of beta IC0 and move forward to the emitter. So from collector to base, it comes as IC0, and after that at base it can be boosted beta times to be as a new value beta IC0 to the emitter. So base to emitter has beta IC0, sir. So this is the total minority current between collector to emitter you can call. So ICO equal to IC0 plus beta IC0 for CE. So that is 1 plus beta times of IC0, sir. So as compared to what, sir, means your common base, here the minority current is 1 plus beta times more. Remember now, the minority current is how many times more, sir? 1 plus beta times more, and beta should be high value such that the minority current effect is more in CE transistor. CE transistor is unstable. So the total collector current IC equal to beta IB plus 1 plus beta times of IC0. So minority current effect is more for common emitter circuit, sir. It is quite unstable, right? And so now, sir, minority current effect is more. Effect is more, sir, and is unstable. So which must also need stability before using in amplifiers. Same condition you may also consider in CC transistor also. CC transistor, common collector transistor also have the same one, sir. There you can also discuss the minority current between what sir means emitter and collector. Same one. Same minority current can also flow in the case of common collector. So that is also suffered from what sir means minority current you can call. So that is also unstable. Among all the three configurations, sir, who is quite stable means with respect to minority current means that is common base circuit, sir. That's with the advantage of common base transistor. Okay. What is base width modulation, sir? You asking that what is base width modulation you call? Now I can able to examine what is the base width modulation. So this one now, you know that among all the three regions of BJT, base is a smaller area as well as it is lightly doped, I told you, so that most of the barrier can expand into the base I call. Most of the barrier can expand into the base. Confirm now, sir. This is base, emitter, collector. This is emitter junction JE, sir. This is collector junction JC, you can call. Confirm now, students. So I keep input forward bias, you call. This is what? Reverse bias. Already you know that, sir, in the case of a BJT, right, the barrier should be expanding mostly into what? Base, because of light doping, like this. The barrier expansion into the emitter is very less. That I indicated as a shaded area like this. On N side, the ions are, positive ions are there. On P side, negative ions are there, you know. Like that, if I go for collector junction, sir, most of the barrier into the base and less effect onto the collector. Why, sir, means because collector is somewhat more doped than compared to base. This is the case. All this is the depletion region, sir. Barriers. Right? So now I can apply this one, sir. Active mode, keep input forward bias. Right? And I keep this one as a emitter supply, sir. And I keep this one as a fix. I don't disturb that. It is a constant value. Sir, output is a reverse bias supply I call. Confirm now? I keep this as a variable, sir. I keep this as a variable. Here which current flows, you know? IC. Here which current flows, you know? IE. IE can keep constant. Here it is IB. Sir, what is the base width modulation you can call? Suppose, according to the PN junction of reverse bias phenomenon, as the reverse bias voltage increases, the barrier can expand. Where it is expand, you know, that barrier can expand into lightly doped area. So, on increasing of this reverse bias collector voltage, what is the barrier? He call that to be now expanding now like this. So, the barrier go on expansion, sir. Sir, if the barrier expanding, you may confirm now the effective base width reduce or increase, sir? Reduce. So, what are the changes in the base width with increase of this reverse bias collector voltage is called as base width modulation. The changes in the base width with the applied reverse bias collector voltage is called as what, sir? Base width modulation. And this phenomenon studied by means of scientists called early. It is also called as the early effect you can call. It is also called as what, sir? Early effect you can call. What are the consequence of this early effect? I show that one to you. See this one now. What I told? As reverse bias collector voltage increases, confirm now, barrier can expand. Barrier means depletion region, right? Into base. Then, what do you know? Effective base width decreases. Understood now? Effective base width decreases. So what I told you, the changes in the base width with applied reverse bias collector voltage is called as what means base width modulation I call. What I told? The changes in base width with reverse bias collector voltage is called base width modulation use say. So it is also known as early effect, sir. It is also called as early effect call. This person should also be called as an early effect you can call. See, so now according to the base width modulation, what happened I can able to examine. According to the base width modulation, what the thing it is going now I can able to check up. According to base width modulation, BWM simply I call. According to the base width modulation, what the thing it is coming, sir? Check up now as reverse bias collector voltage increases, right? Barrier expands. Confirm? Barrier expands means base width decreases. Confirm? Base width decreases means recombination rate decreases. Confirm? Recombination rate decreases, you call. Then IB decreases. Correct, right? So as reverse bias collector voltage increases, barrier can expand, right? So whatever that base width are decreases, the recombination rate decreases, base current decreases, automatically the carriers who do not recombine in the base can jump into the collector. That to be known by the base transport factor I can call, that is base transport increases. The carriers who do not recombine into the base that can be jumped into collector, that value is increasing. Thereby injected collector current IC increases. Up to now I told that any change in collector current mainly depend on what, sir, means input forward bias voltage I call. For the time you say that there is a slight change in output collector current with this reverse bias collector voltage also. So originally I told that any change in collector current depend on input emitter current. But now I am saying that there is a slight change in output collector current with respect to this. What, sir, means collector supply voltage, that is reverse bias voltage you can call. How it is, sir? By decreasing base current that can be converted into what, sir? Output collector current you can call. So even I, sir, input is constant, IE constant. How the collector current increasing means by decreasing IB. So decreasing IB that can make to increasing what? Collector current. Confirm? Check up now. So collector current increases means what, sir? Resultant current gain factor alpha increases. Alpha equal to IC by IE, IE constant, but IC increasing. The alpha goes to be increases. So this is the concept of the base width modulation. So if I do this job continuously at a particular voltage called early voltage you can call, there the effective base width becomes 0. The effective base width is called 0, and that phenomenon is to be called as a punch through phenomenon or reach through phenomenon. As you do this process continuously, increasing of reverse bias collector voltage continuously at a particular reverse bias collector voltage, that is called as early voltage you can call, the effective base width becomes 0 because the barrier can expand throughout the base, where the barrier can complete through the base, so that what, sir, means recombination rate becomes 0. You can call, indicate IB equal to 0 or IC equal to IE, indicating that phenomenon as punch through or reach through phenomenon. Confirm now? So the changes in the base width with the applied reverse bias collector voltage is called as base width modulation. Confirm? Check out the next one. Distinguish between CB, CE, CC transistors. So now I can able to compare CB, CE, CC transistors. What are the main things of this? So all these three configurations compared in terms of their input impedance, output impedance, voltage gain and current gain, as well as phase relation between input and output, right? See this one now, any active device that can be used as an amplifier can be indicated according to the two-port network model like this. So you know that BZ is a body of two-port network taking one terminal to be common to both input and output. So this is the equivalent representation you see. So this is the two-port model you can call. And according to the condition, you are a person, you can apply the signal voltage here. This is the signal current. Confirm? And you may find out that output current and this is the output voltage. Got it? And says for now this active device can be used as an amplifier specified with the gain factor A. And what are that input impedance of the active device should be seen between the input terminals. This is the place. It's not the impedance corrected by you, it is the impedance of the active element between the input terminals. And depending on the gain, this input signal can be boosted by how many times, means A times, to get an amplified signal that is called AVI, like this. Confirm? So being an amplified signal AVI can be handed over to the output terminal via body output impedance. So being a voltage source, the impedance would be series, like this. This is the output impedance you call. So this is the internal model of an active element applicable for BJT, FET, MOSFET, operational amplifier, all that. So what the thing I am saying here means, sir, any active device useful for amplification, the main require is input impedance high, output impedance low I require. So any active device for good amplification, you must also require high input impedance, low output impedance you can call. Ideally, input impedance infinite require, output impedance 0 you require. I think that you know somewhat ideal characteristics of op-amp. Sir, what is the advantage of having high input impedance or high infinite impedance means? Sir, having high impedance or high input impedance or infinite impedance means input terminals are free from loading effect. Input terminals are free from loading effect. Suppose, see this for now, this is some Vs signal, sorry. Suppose this is some Vs signal I can apply to the input terminals of this active device through some supply resistance Rs. So these are the input terminals of your active device. So where you can find out the input impedance Zi, this one. So what is the net input can go for amplification means that you can call Vi, this part. Sir, how much signal you apply, it's not the case. What the signal received by the active element, that is only go for amplification. So what is the value of Es? That's not the case, sir. How much value it is receiving? So that is indicated by Vi, that only go for amplification. Sir, whether Vs equal to Vi or not, depending on this supply resistance, source resistance you can call. Suppose if the source resistance is more, most of the signal dropped there, then net input signal become less. If the source resistance is less drop is there, you can get maximum signal. But what is the source resistance? You can ignore that effect by using high input impedance you call. What is the source resistance, whether it is high or low? Irrespective of that, he said that having high input impedance, you can ignoring the source resistance effect you can call. How do you ignore, sir? Sir, you see this one now. Rs and Zi are in series. Rs and Zi are what, sir? In series. Series is a voltage divider network you call. Lower the resistance, lower the voltage drop. Higher the resistance, higher the voltage drop you can call. So as compared to the Rs, I say that Zi is high, ideally infinite, indicating that, so according to the voltage division formula, what you say means the voltage across Rs is negligible, because as compared to Rs, Zi is too high. Based on that, the voltage drop across Rs is negligible. Most of the signals should be appeared across the input impedance. That's the advantage. So having high input impedance, we can able to copy most of the signal to the input terminals. Suppose if Zi is less, I can call, then there is a loading effect on the input terminals. If Zi is less as compared to Rs, what I can call, sir, among the applied signal Vs, some of the signal to be dropped by Rs, then net input become decreases, then amplified output decreases. So to overcome this source loading effect, so compulsory you require high input impedance of active device that is used for amplification. Got it now? Next, one more thing you confirm now, sir. How the output impedance? Output impedance you must also require as far as possible low. Low value of output impedance required. Ideally 0 you require. Sir, why it means the amplified signal AVA given to the output terminal via output impedance. So you are a person, you connect to the load here. You are connecting some load. And you see this one now, this load and Z0 are in series. Suppose if this Z0 is 0 or low, then amplified signal drop there is less according to the voltage division. Then most of your amplified signal given to the load. So to hand over most of the amplified signal without loss of energy, so Z0 must be minimum, ideally 0. So any active device useful for amplification must and should require high input impedance and very low output impedance. Having a high input impedance, the input terminals are free from source loading effect. Having low output impedance, most of your amplified signal is given to the load. This is the case. Confirm what I told? For good amplification, okay, Zi tends to be high. Ideally, Zi need to be infinite, okay, to make input free from what's a source loading effect, so that most of the signal can be given to the input for amplification. This is one of the case, right? And Z0 tends to low. For ideal case, Z0 tends to 0 ohm, so that most of amplified signal given to output. So this is that. So doing like that, most of the amplified signal given to the output you can call. Check up now how the CB, CE, CC are compared with that input and output impedances and remaining voltage and current gains, all those things you check out. I can check out all that one now. See this one now. So now I can able to go for the comparison of all these three configurations I am showing. So now I call some parameter here. Confirm. So I use the configurations: common base, common emitter, common collector. Three configurations I am comparing according to your question. Got it now? So first case now I can go input impedance I call Zi. Input impedance I can go. So how do you know that input impedance? Input impedance is nothing but dynamic resistance because it is a non-linear device. How do you know that? From your characteristic graph you can define. This input impedance would be known from the characteristic graph of that BZT you can call. So input impedance to be calculated from the input characteristics of CB or CE or CC transistors. According to the condition it should be low. Common base circuit input impedance is low, that should be less than 100 ohms, order of few ohms. Confirm? For common collector, the input impedance is high, order of mega ohms. So this input impedance to be known from input characteristic graph of that BZT you can call, and that is nothing but a dynamic resistance only. And for common emitter, this input impedance would be moderate. That is about 1 kilo ohm to 2 kilo ohm we call. Moderate value, that is just around 1K to 2K. So among all these things, lowest input impedance is considered for common base and highest input impedance is considered for common collector. Moderate is considered for what? Common emitter. Now we can go for output impedance. Sir, for common base circuit, output impedance is high, ideally infinity call. It is commonly order of mega ohms. For ideal case, it is infinite. Okay. Now, for common collector, output impedance is low, order of few ohms, that is practically less than 100 ohms. Quite opposite. So, output impedance of common base circuit is high, ideally infinity can call order of mega ohms. So, for common collector it is low, that should be order of few ohms you say. If I go for common emitter, it should be again moderate. So, around 0.1 mega ohm to 1 mega ohm you call. It should be around 0.1 mega ohm to 1 mega ohm you say. So it should be moderate as compared to both common base and common collector. So observe now, common base have very low input and very high output impedances. Common collector have very high and very low, or very high input and very low output impedances. Common emitter have both moderate impedance values. Now what about that current gain? Current gain stands for output current to input current ratio. So that is what you can call, for common base, the current gain factor you call alpha. That is called what, sir? Alpha, you say. What is that alpha means? Alpha equal to IC by IE. It is close to 1. So it is poor, you can call. It do not have a good current gain. How much means? Practically it is around 0.9 to 0.998. The current gain of common base circuit is poor. It do not act as a current amplifier. As compared to output current, input current is a little bit more. So here current gain factor is beta. Beta equal to what you can call IC by IB, you say. That is greater than 1. So it is high value. So practically it says ranging from some 50 to 500 you call. Right? If you go for common emitter, current gain factor gamma you call, that is IE by IB you say. So it is also greater than 1. So it is also high. Even as compared to common emitter, its current gain is little bit more, that is 51 to 501. Among all the three configurations, CE and CC have good current gains, and particularly if you compare these two again, CC have some better current gain. So if you want to go for current amplification, CC should be preferred as a priority of current amplification. And the next one is the CE you can call. CB is worst for current amplification, whose current gain is poor. Confirm? Next, voltage gain you call AV, that is V0 by Vi, you say. We can express this voltage gain in terms of current gain and input and output impedance as, I think that you know, AI into Z0 by Zi. So a current gain AI into Z0 by Zi, you say. So the voltage gain of our common base, sir, it should be good for this. It is high, around 150 you can call. So for common emitter current voltage gain is good, that is around 500 you say. So both common base and common emitter have good voltage gains you call, and if you go for common collector, the voltage gain is poor, that is close to 1 due to feedback effect condition. So I think that you know, common collector amplifier is nothing but an emitter follower. So due to feedback effect, so here voltage gain gets suppressed and make to be as a unity gain. Voltage gain comes to close to 1. This is the case. And what is the phase angle between input and output you can call? Phase angle between V0 and Vi, output and input for common base, common emitter, all this. If I go for common base and common collector, the phase shift is 0 degree. Here input and output are in phase. If you go for common emitter, here phase shift is 180. So in the case of common emitter, input and output are opposite phase. That can be useful in oscillator circuits. So if I compare all these configurations, compare all these three configurations, what are the thing you can confirm here? You observe now, common base circuit, even it have a good voltage gain, not preferred as an amplifier. What the reason means? Because of low input impedance and high output impedance you call. Already I told that whenever you are using a transistor as an amplifier, you must also require high input impedance and low output impedance. Particularly for common base circuit, the input impedance is low, output impedance is high. It can amplify the signal. Amplified signal dropped across its output impedance, not given to the load. So CB transistor not preferred to be used as an amplifier. Confirm now? So voltage gain is good. Even the voltage gain is good, it do not act as an amplifier. So anyhow current gain is poor. But what is the advantage of the common base circuit, sir? As compared to CE and CC, in the case of common base circuit, what do you find out, sir? Means the minority current effect is less and it is quite stable. And later you can able to examine the analog circuits of amplifiers. You find out now, as compared to CE, CC amplifiers, in the case of common base amplifier, the internal capacitance effect is also less. So having a less internal capacitance effect, common base circuit is preferred to use at high frequencies. that is a radio frequency, such that common base circuit can be classified to be used as a RF amplifier, radio frequency amplifier. Confirm my option. That comes in analog circuits. There you discuss the internal junction capacitance effect in the case of common base transistor is less, so that it can able to use even at high frequency without losing its property. So common base circuit commonly preferred to use at high frequency called as a RF amplifier you call. Got it? So if I go for CC transistor, so current gain is so high and input impedance high, output impedance low, exactly matching your conditions. And not only that, it is a good having a good current gain. So even as compared to CE transistor, CC transistor is mostly preferred to be used as a current amplifier. And not only this, so voltage gain is poor. Originally it is a drawback, but in other way it is an advantage. What type of advantage means? It can be used as a voltage buffer. What is a voltage buffer? A voltage buffer is one that can carry the input signal voltage as it is to the output without loss. So in our electronic systems, to copy the data between two networks, we can able to perform some impedance matching. So who is a person that can do this impedance matching means CC transistor, that itself called as a emitter follower you can call, who can act as an impedance matching element between two networks of different impedance values. So it can adjust high impedance to low impedance or low to high impedance and carry the signal from one stage to the other stage without loss. So it is very popular to use in the electronic circuits as a buffer, voltage buffer, and as well as impedance matching device, as well as what sir means current amplifier. That's applications of CC transistors. Confirm now? So due to its high input impedance, low output impedance, it can be used as a impedance matching device. Why means even input and output impedance are different, copy the input signal as it is to the output. That's the property of impedance matching. Used as a current amplifier also. See this one now, among all the three configurations, who can have better voltage and current gain? Not only current gain, in terms of voltage, current as well as power gain, all good be in CE transistor. So CE transistor should be preferred to use as an amplifier in terms of voltage, current as well as power as compared to both common base and common collector transistors. So it have moderate input and output impedances, right? So main thing is having a good current and voltage gains you can call. Good current and voltage gains you say. So as well as power gain is also good for common emitter circuit, such that the most commonly preferred transistor configuration that can be used as an amplifier is CE transistor. CE transistor commonly preferred to use as a amplifier. Got it now? So this is the main comparison for common base, common emitter and common collector. And in the case of common base and common collector, input and output are in phase option, whereas in common emitter, the input and output are opposite phase by 180 degree call, right? Check out the next one. What is meant by thermal runaway call? Check out this question. So thermal runaway is one of the problem in the case of BZT, that is commonly due to excessive heating effect, right? And so now what I told, thermal runaway is mainly due to what sir means excessive heating effect you can call. What I told, it is due to excessive heating effect. So it represents the destruction, damage of a BZT, sir, right? It represents the destruction of a BZT due to excessive heating effect. It represents destruction, that is a damage due to what you can call heating effect, excessive heating effect you call. That is purely due to again what sir, minority current effect only. Check up is it my option is right or not. I show that one to you. See this one now, this is the cycle sir. Suppose temperature increases, you know that minority current IC naught increases. Confirm? If the temperature increases, the minority current increases, you can call. If the minority current increases, total collector current IC increases, sir. Total collector current IC increases means automatically the collector power also increases, sir. Collector power increases means power as a heat, that is power dissipation. PD also increases. Heat dissipation increases means temperature increases. So this is a cyclic. Temperature increasing, minority current IC0 increasing, by the total collector current increasing, collector power increasing, power as a heat, that is nothing but, I told just now, in the case of BZT, the power dissipation appeared in the collector region as VC into IC, that to be increases. So power dissipation increases, again temperature increases. It is a cyclic pattern. At one of the instant, so the heating effect by the BZT body may cross its limit, the power dissipation may cross its limit, automatically the body get overheated to get burned out. This is the case. So at a certain instant, the heat dissipation by the body may cross its limit, you can call, that is specified by the manufacturer. So what is the heat dissipation may cross the limit specified by the manufacturer. So that it is immediately indicating that the destruction of a BZT, damage of a BZT, burn out of a BZT you call. Sir, how do you avoid the thermal runaway? So, thermal runaway problem to be overcome by what, sir? Making collector current independent of temperature. That to be considered by the biasing techniques, that is called stabilization techniques we call. Right? So, thermal runaway can be overcome by what, sir? Stabilization process you can say. So, using which you can make collector current independent of temperature such that overheating effect you don't find out. That's the reason. And what you can call, sir, to avoid thermal runaway, one of the condition is also there, sir. Select the Q point such that the applied collector voltage should be less than or equal to VCC by 2 you call. That's also one more reason. The main thing is thermal runaway should be overcome by what, sir? By a stabilization process, by using biasing techniques. This is the thing I call thermal runaway is avoided by stabilization techniques, sir. By using what, sir? Stabilization, using biasing techniques, by stabilization process. And also if one more condition, sir, VCE, that is collector voltage, less than what you can call, sir, half the supply voltage. If VCE less than VCC by 2, thermal runaway problem should be overcome, sir. Okay, there the corresponding Q point should be selected in the active region portion, and there you can have a chance to avoid the thermal runaway you can call. So keeping that collector voltage should be less than VCC by 2. Now, thermal runaway apparent, the self-destruction of a BZT due to excessive heating effect, sir, that mainly due to what, sir? Minority current. Confirm? Which transistor configuration of a BZT act as constant current source in active region? So among all the three configurations are common base, common emitter and common collector. If you compare, sir, common base transistor can act as a constant current source in its active region. See this one now, sir, for common base circuit, this comes in common base, sir. So this is the common base circuit you can call, just I indicate small thing. So this is the output, sir. Collector base you call, this is emitter you say, this is VEB, sir, emitter to base voltage you call, this is collector to base voltage, sir, VCB call, here output current IC you say, input current you call IE. So if I draw that output characteristics of common base circuit, sir, that can be drawn between output collector voltage VCB and output collector current IC, sir, keeping input current IE constant. Keeping input current what? IE constant. The characteristic graph should become like this, sir. This is the graph you find out. So this is the common base characteristics. Suppose if you expand the graph to the other side, sir, that become like this. This is the expansion of the graph. Sorry. So if you expand the graph towards the other side, sir, so this one now. This is minus VCB call. Sir, this is the saturation region of a common base circuit you say. This is the active region where input is forward bias, output is reverse bias, sir. This should be some cutoff I can call. Suppose I can make this one for input is 0 milliampere, sir, very close to horizontal axis. This is called cutoff we call. So this is plus VCB you say, where both input and output are reverse bias. Here both input and output are forward bias you can call, and this is an active region of common base circuit, sir. You observe now, in the case of common base region of active region, the characteristic curves of flat response. Flat response means there the corresponding collector current increasing alpha times of given IE. Suppose here I equal 2 milliampere constant, here I equal some 4 milliampere constant, like this I call. For a given IE, it can changing alpha times, sir, and you know that alpha close to 1, so that IC changing as IE times. Already IE constant, thereby IC also constant, having a flat response. So in the active region of this one, the common base circuit look like a what, sir, means ideal current source, constant current source, because where collector current increasing alpha times IE, already IE constant and alpha close to 1, so IC changing as IE times IE is constant, so that collector current remains constant. So in the active region of common base circuit, you find out what's our ideal current source. Got it now? What I told you? In active region of CB transistor, sir, IC increasing as alpha times given IE, sir, and as alpha close to 1, you know, then IC increasing as IE times, but IE already constant. IE is already constant, so that IC constant as IE constant and look like a constant current source, sir, and look like what? Constant current source, and look like what, sir? Constant current source you can call. Got it now, sir? Check out this. So in this region of active region, it have a flat response. The corresponding collector current increasing as alpha times of IE. So IE already constant, so that the corresponding current or collector current also look like be what, students? Constant you can call. So in this region, the corresponding BJT of common base circuit act as a constant current source. Nothing but what you can call, sir? Ideal current source you can call. Ideal current source. Understand these things? Check out the next question. Why NPN is preferred over PNP transistor? So in a BJT, why do you prefer NPN transistor as compared to PNP transistor? Recall. So if we compare NPN and PNP transistors, you remember that in NPN the current is mainly due to electrons, whereas in PNP the mainly current by holes. If you compare electrons and holes, the mobility of electrons is good than compared to holes. So that in a given body, electrons can move faster than compared to holes, such that current conductivity by electrons is faster than compared to holes. So NPN is commonly preferred as compared to PNP. In general, wherever the current carriers, that is electrons, that should be preferred. Not only this, in case of FET and MOSFET also, N channel body is preferred over a P channel body. The main reason is the current carriers are electrons and whose mobility is greater than holes, right? So the reason is means in NPN the current carriers are what? Electrons. In NPN the current is mainly by electrons, right? That has more mobility, you know. Whose mobility, already you know mobility indicate how much is the velocity considered by the carrier with the applied field, whose mobility is greater as compared to holes of whose mobility is greater as compared to what, sir? Holes of P and P, you say. So it indicated that electrons conductivity is faster than compared to holes, so that NPN is preferred. NPN is preferred, you can call. So NPN is preferred over PNP mainly because of the electrons as the carriers, so whose mobility is greater than the holes of the PNP transistor, you can call, such that the conductivity of NPN is faster than compared to PNP, you can call. Conductivity of NPN is faster than compared to PNP, right? So this is the reason why that NPN is preferred than compared to PNP transistor. Check out the next question now. Is NPN sinking or sourcing? See this one now. NPN outputs are, NPN is nothing but a sinking outputs it have. What is the sinking output means? It sink the output current from load to the output. It sink that output current from load to the output, right? Whereas PNP transistor is nothing but a sourcing output, you can call. PNP outputs a sourcing condition, you can call. There they can source the current from output to the load. From output to the load, you can call. Confirm? So what I told you, NPN has sinking outputs, not sourcing, you call. Why it is, sir? Means because in NPN the output current, right, that is nothing but to sink that output current from what, sir, means from load to the output, you can call, right? In NPN, because what I call NPN can sink the output current from what you can call, sir, means from load to the output terminal, you can call, from load to output terminal. From load to output. This is the way of connection of NPN. If you go, just 1 minute I can do. So this is the NPN condition, you see. Emitter it is, base, collector you call, you connect a load here, right? This is the, what you can call, sir, in NPN, this is the place where you take the output. So here the output is taken after load, you can call. In NPN the output is taken after load, so that output current flows from output to the load, you can call, right? So output current flows from what, sir, means from load to the output, you can call. Output current flows from load to the output, you can call. So in NPN, what do you say? Output is taken after load. Output is taken after load, you call, right? There you can able to sync that output current from output to what you can call, sir, load. So from output current from load to output, you can call. Take that current from output, or what, sir, means load to output. Now let us see this one. Now if I go for PNP, that is called as a sourcing output, you can call. PNP is a sourcing output. So this one now, PNP is a sourcing output, you call. Sourcing output. Why do you call as a sourcing output? Means because PNP transistor can source that output current from output to the load. From output towards, sir, means load, you can call. This is the case because, okay, it can source output current, what you can call, from output to load, you say. It can source output current from output to load. In the case of PNP transistor, this is the way of connection, you say. This is the emitter, you call. This is collector, base, emitter of PNP you can call. You connect to the load is here. So this is the output terminal you call. So here output is taken before load, here output is taken after load. Here the sourcing the current from output to load you can call, from output to load. There from load to output you can call. Got it now? So in PNP, confirm, in PNP output taken right before load you can call, output taken before load. Output taken before load, whereas in NPN output taken after load. Confirm my option? So NPN is a sinking output, PNP is a sourcing output. You can commonly say NPN is a sinking output, PNP is sourcing output. And so now check out the next question. Explain about the Q point, right? Quiescent point, operating point. So this is most needed in the case of a BZT. So this Q point can decide the place in the active region where it can act as an amplifier. Suppose if the transistor is properly operated in the active region by selecting Q point, you are getting a properly amplified signal. Suppose if the Q point is not selected properly in the active region, some part of either positive or negative cycle can be clipped off. Confirm my option? So Q point can define the place where the transistor can act as an amplifier. If this Q point is located perfectly in the active region or in the required place in the active region, the transistor can be able to amplify the signal properly for all portions of the input. Suppose if the Q point is not in the concerned place or correct place, then what you find out, sir, means some part of either positive cycle or negative cycle can be clipped off. So using Q point, one can decide whether the output is amplified equally for positive or negative half cycles or not. So how do you define the Q point? Means for defining the Q point, you must also draw the load line using DC model of a BZT. That to be called as a DC load line you call. Commonly, DC load line is a straight line with a negative slope. Commonly, DC load line is a straight line with a negative slope. Suppose now I can able to go for CE transistor. This is a common emitter transistor. Emitter, base, collector. Suppose NPN model you call. I operate this one in active region, keeping what, sir, means input forward bias and output is reverse bias you can call. And I can keep input forward bias through some biasing resistor RB. So this is input supply you can call, that is called a base supply named as VPB. Confirm? And output to be reverse bias you can call by means of one more supply commonly called collector supply, and that to be connected via output collector load called RC. So these are to be biasing resistors in the selection of Q point. The resistance value of these two important in the selection of Q point. So for now, this one can be reverse bias. Commonly you know that both N-type, both collector and emitter are N-type terminals you call. So commonly you can keep collector to be made positive than compared to emitter, you know. So by that you can easy to drift the electrons towards collector. Confirm now? So this is the case. Right. So output is reverse bias, input to be forward bias you can call. So BZ is a body of two-port network. So depending on that you have four variables you can call. What are that four variables are? Those are input current IB, output current IC, input terminal voltage VBE, output terminal voltage VCE you call. So the Q point selection to be done by the selection of output current and output voltage. So these are called as a Q point values. But BZ is a current control, you know. Any change in output current controlled by what? Input current. So that in the Q point selection originally require IC and VC, but IC is to be a function of IB. So you can also take that. And what is the function of VB in the DC biasing circuit? Means the purpose of VB is to cancel the barrier effect, so that by the applied VBE, the barrier effect will be cancelled. On applying AC signal, the corresponding transistor should conduct immediately from zero reference of the signal. You do not wait until the signal can cross the barrier potential, because barrier effect should be overcome by this applied VBE. So this VBE should be maintained to make the input of a transistor free from barrier effect. So on that, if I apply AC signal, that concerned AC signal go for boosting or amplification from its zero reference. Otherwise, it do not go immediately from zero reference. I think that you know this type of problem you may know in the case of class B power amplifier. In the case of class B power amplifier, no DC biasing is applied to the input of a transistor. So even you can apply AC signal, it do not conduct immediately. It takes some time until the applied signal voltage cross the barrier potential, and it can find out some distortion there, that to be called crossover distortion, that can find out very easily in the case of class B push-pull power amplifier, where that has two class B transistors. One is conducting for positive cycle, other one conducting for negative cycle. Because of zero DC biasing, none of the transistor is conducting until the applied signal voltage crossing plus or minus that barrier potential of what that one VBI call. So to overcome the barrier effect, VBE must be maintained. So every signal has some importance in the biasing, in this biasing conditions. So Q point selection done by what I told, IC and VC, those are called as a Q point values, right? And IC selection to be done based on the base current, you can call IB. So this is the DC load line you call. So from the characteristic graph, you find out that DC load line should be a straight line. DC load line should be a straight line, and whose end points are at one end point is at saturation, another end point is at cutoff, you can call. One end point is at saturation, other end point is at cutoff. This is called saturation current. This is called cutoff voltage. So DC load line is a straight line of negative slope, you can call, whose end points must be what that means. One is a saturation point, other one is cutoff point. So this is saturation current calculated from output bias. Saturation current should be calculated from output bias, you can call, and at cutoff region commonly you say that IC equal to 0. Keeping IC equal to 0, ICRC product 0, then VC equal to VCC. So cutoff voltage is nothing but same as supply voltage. And saturation current to be defined from output bias, taking that collector voltage as a saturated value. Ideally, saturation value of collector voltage is 0. Practically, if you go for that saturation voltage equal to either 0.1 or 0.2 volts. For germanium, it is 0.1. For silicon, 0.2 volt, you can call. Ideally, that saturation voltage is 0. If I go for ideal condition, the saturation voltage of VC equal to 0, then IC saturation equal to how much, sir? VCC by RC. So, from output model, you are calculating what's our saturation current and cutoff voltage. By that, you can draw that DC load line, which will look like a negative, which will look like a straight line of negative slope. After that, how do you define that Q point means? So after that, you can consider to draw what's our means, the output characteristics for different values of base current like this. So if I draw that output characteristics for different values of base current, I can expect the graph like this. So I can able to draw this output characteristics for different values of base current I given. Suppose here I can make a graph some IB1 constant, and you can make a graph for some IB2 constant like this. For different values of base current, I made a graph. Confirm? So from this, you can define that Q point selection. How to define the Q point means, Q point defined as the point of intersection of the output characteristic graph with the DC load line. So it is the point of intersection of the DC load line with output characteristic graph for a given base current constant. Q point is the point of intersection of the DC load line with output characteristic curve for a given base current IB. So for a given base current IB, this is the graph. It can intersect the load line here. So this is the Q point for it. And it look like be close to cutoff. Some Q1 is close to cutoff, we call. Suppose if I go for this is the graph made for IB2, right? So this graph can intersect the load line here. So this will be the Q point for it. So for IB3 graph, the Q point, this is the intersection point, that will be Q point. So Q point is the point of intersection of DC load line with output characteristic graph we call. Suppose if I say that Q point is near to cutoff, a part of negative cycle is clipped off. during amplification. If the Q point is near to saturation, a part of positive cycle is clipped off during amplification we call. Without clipping either part of positive or negative half cycle during amplification, you mustn't should do the condition is the selection of Q point should be done at the center of the load line. Right, and so now Q point should be selected at the center of the load line, at which you find out Vc equal to Vcc by 2. Vc equal to what? Vcc by 2. So for good amplification, you should select the Q point at the center of the load line. Otherwise, either part of positive cycle or negative cycle can get clipped off. Check up this. Sorry. Now I can able to examine either part of positive cycle or negative cycle can be clipped off if the Q point is not be selected at the required place. Now I can able to check out that. Suppose I say that if the Q point is near to saturation, like this, you see now. This is Vc, this is IC. Suppose I select the Q point here. So remember now, during the amplification of any AC signal, the amplification should be possible with respect to what sir means saturation and cutoff. Per current it is a saturation, sir. Per current it is cutoff. And any AC signal you applied across the input terminals that can go for amplification with the Q point as a point of reference. With this reference, the signal amplification should be done. So if the Q point is near to saturation, you find out that most of the positive cycle is clipped off like this. Suppose if you select the Q point near to cutoff, what happen you see now? This is some Vc, this is IC you call. Suppose if I select the Q point near to cutoff, what happen? I can show that one to you. Suppose this is the Q point selection you say. So just now I told that any amplification should be done with reference is what? Saturation and cutoff. Per current this is saturation cutoff. Per voltage this is cutoff, this is saturation you call. Sir, you remember now here the Q point selection should be done taking near the cutoff you call, so that any amplification should be done with the Q point as a point of reference you say. So the corresponding AC signal can able to amplify with the Q point as a point of reference. That amplification should be like this. So you can get that good amplification per positive cycle, and most of negative cycle is clipped off. Confirm? Sir, without clipping, how do you get a good amplification for both half cycles? Means he say that for that you select the Q point exactly at the center of the load line. Q point selection should be made at what, sir? Load line you call like this. This is IC saturation you call. So I select a base current in such a way that it can able to define the Q point at what, sir? Center of the load line you say, like this. This is the way. Now I keep the Q point exactly at the center I call by the selection of base current. So by that what you can find out, sir, for the given AC signal, the corresponding AC signal can able to go for amplification equally for both positive and negative half cycles. So we are getting a faithful amplifications both for positive and negative half cycles. So selection of Q point exactly at the center of the load line, indicating that you are getting a good amplification for both positive and negative half cycles of the AC input. What is the condition for this one, sir? You know that this is Vc cutoff you call. And just now I told that from the circuit, cutoff voltage is same as supply voltage. So selection of Q point is at the center. Then the corresponding voltage is VCQ you can call. That is a zero signal collector voltage. That's what you call zero signal collector voltage. That should be equal to VCC by 2. So for distortionless output or for good amplification, the Q point should be selected at the center of the load line, at which Vc equal to VCC by 2 you can call. So selection of Q point exactly at the center. After that you can apply AC signal. Then the corresponding AC signal can go for amplification without any loss of either positive cycle or negative cycle. You are getting a faithful amplification you say. So for good amplification, the Q point should be selected at the center of the load line, at which Vc equal to what? Vcc by 2 you can call. Check up now. What the thing I am saying? So this is my circuit, you know. This is my circuit. What I told you, you have to select the Q point at the center of the load line I call. For that Vc equal to what I said, Vcc by 2 I call. Suppose I say that some Vcc is 10 volt. Then this Vc must be equal to what? 5 volt. Right? Suppose I assume that this is the transistor of beta is 100. Then what is that IC, sir? IC equal to, according to the Ohm's law, VCC minus VCE by RC. VCC is 10, VCE 5. I assume that this RC some 1K I call. All these are the fixed I made. So VCC 10, VCE 5, 10 minus 5 by 1K, that become 5 milliamps. Got it? Now I go for IB. IB equal to what, sir? Means, sir, IB equal to IC by beta I call. IC equal to beta IB. Then IB equal to IC by beta. IC is 5 milliampere, beta is 100. 5 into 10 power minus 5 ampere. That is, IB look like what, sir? Some 50 microampere. So now I assume that suppose it is a silicon transistor. For that VB I identified is some 0.7. Suppose I can keep this base supply as some DC supply of 2 volt. Only one thing is unknown you can keep, that is RB. So for VCC 10 volt, I wanted to keep VCE 5 volt by that Q point at the center of the load line. So I assume that RC 1 kilo ohm, beta is 100, VB of silicon transistor I call 0.7 volt, and input base supply given 2 volt. Who is just unknown, sir? Means RB. So by finding RB, you can able to keep that value. Automatically your Q point exactly at the center of the load line you call. Sir, what is the formula for RB calculation? Means, you see this one now. Here RB should be calculated as VBB minus VBE by IB. Like this you calculate. So what are the value you calculated, that value can keep and operate that transistor. 100% you can able to get that Q point at the center of the load line. After that you can apply the signal of AC voltage across the input terminals. Then that signal go for boosting or amplification equally for both positive and negative half cycles. So that is about the Q point. Confirm now? So Q point is one of the person called as a quiescent point or operating point. The selection of this Q point indicate where the transistor operates in the active region for amplification. Suppose if the Q point selection is near to saturation, right, some part of positive cycle is clipped off. If the Q point is near to cutoff, some part of negative cycle is clipped off. If the Q point is exactly at the center, then you are getting equal amplifications for both positive and negative half cycles of AC input you can call. Understand these things? So this is the examples I call. So Q point selection at saturation, near to cutoff, at center. Confirm? So what I told you? The selection of Q point in active region right, the selection of the Q point in active region is important for good amplification. Confirm? So for locating or identifying the Q point is done by what, sir? Means drawing the DC load line. Okay, and is done by drawing what, sir? DC load line first. And remember students, so DC load line, what I told you, it is a straight line of negative slope I call. DC load line is a straight line of what? Negative slope I say. Right? What is the Q point I told you? Q point is the point of intersection of DC load line with output characteristic curve for a given base current you call. So for good amplification, you should select the Q point at what? Center of the load line. For good amplification, what do you call? Q point is at the center you require. Q point is to be at center of the load line you call. Q point should be what, sir? At the center of the load line you call. At center of load line, where VCE, collector to emitter voltage, equal to what? Of the supply voltage, VCC by 2. Where VC equal to what, sir? VCC by 2 you can call. Confirm now? Where VC equal to VCC by 2. Confirm? So this is about the Q point use. Next I check out what FET means. Now I can able to go for. Is a FET unipolar or bipolar you call? So FET means field effect transistor, sir. He asked that it is a unipolar or bipolar you call. Sir, FET is a body of unipolar device. FET is a field effective transistor, sir. It is a unipolar device, not a bipolar. What is a unipolar? Means where you are expecting the current conductivity by only one type of carriers, not by both type of carriers, right? So FET is almost free from minority carrier effect you can call. In N channel FET, current is purely by electrons. In P channel FET, current is mainly by holes you can call. And in the case of FET as compared to BJT, the current is mainly due to drift mechanism. So you know that drift current is a function of applied electric field you can call, so that the conductivity of field effective transistor is changing by the applied electric field. By that it is called as a field effective transistor. It is called as what? Field effective transistor. Confirm? So what I told you, it is a unipolar device. Not bipolar, sir. Unipolar device. That is current by only one type of carriers. Current is due to either electrons or holes. Not by both type of carriers you can call. Current is either by electrons or what you can call, sir, holes. It is a person free from minority carrier effect. So as compared to BJT, there you can expect current by both majority and minority carriers, and BJT is suffered from minority carrier effect, so it requires stability, you know. But FET is completely free from minority carrier effect. It is quite stable. It is what, sir? Quite stable you can call. And again you find out now, in the case of field effective transistor, which type of current mechanism you can use, sir? Drift current mechanism you can use. The main current flow is due to drift mechanism, and it is a function of applied electric field. By that it is called as a field effective transistor. Confirm now? So what I told, in FET, current flow is due to drift mechanism, sir. In BJT, the main current there, you know, that is due to diffusion mechanism. But in FET and MOSFET, the current is mainly due to drift mechanism, so that current can flow as a function of applied electric field. By that, this person to be called as a field effective transistor. It is called as what? Field effective transistor you call. Check out now. What are the advantages and drawbacks of FET over BJT you can call? What are the advantages and drawbacks of FET over BJT? Sir, if I go for BJT and FET conditions, remember now, as compared to BJT, FET is nothing but, just now I told you, free from minority carrier effect. That is most important in the case of FET. So BJT is suffered from minority carrier effect you can call. So based on that, even input not be changing due to this minority effect. There is unnecessary variations you find out in a BJT, such that BJT requires some stabilization conditions. So that type of stabilization conditions you don't require in FET. Why, sir? Means FET is completely free from minority carrier effect you can call. So FET is quite stable. BJT is not stable you can call. And as compared to BJT, in FET, internal noise voltage is less. So the internal noise or unwanted AC who generated within this active element, that should be less in the case of FET you can call. But in the case of BJT, this internal noise is more, right? And What is the other advantage of FET, sir? Means, so FET can able to having what, sir, means good response as compared to BJT. It can act as a good amplifier. It can act as a good amplifier and as well as a fast switching device as compared to BJT. As compared to BJT, switching response is somewhat faster in the case of field effective transistor. So the only one drawback you may expect as compared to BJT is what means, as compared to BJT, FET maintaining a low gain value, because in the case of FET that you can examine later, the gain depending on one of the parameter called transconductance. So in the case of FET, the transconductance value is less, so that the FET body maintaining low gain values, so its gain bandwidth product is poor. That is one of the drawback of FET, and as well as FET is expensive than compared to BJT. So this look like be somewhat drawbacks of the FET, but FET is a good amplifier and as well as it is a fast switching device as compared to BJT. The main important advantages of FET are what, sir? So free from minority carrier effect and it is quite stable, and as compared to BJT, FET input resistance is very high. So commonly any active device you require for amplification need high input resistance, so FET need to be have high input resistance you call. Got it now? What advantages I call? Advantages, sir? Free from minority carrier effect I call. So minority carrier effect is not there, ideally zero, practically negligible, so that it is quite stable and don't need any further stability as you discuss in BJT, right? And is quite stable, right? Quite stable you can call. Next one, what, sir, means fast switching response as compared to BJT. Fast switching response as compared to BJT you can call. So as compared to BJT, so switching response is fast. Next, internal noise voltage is less, I told. Internal noise voltage is less. So it is a good amplifier even as compared to BJT, but only one drawback I told that. What that one means? So the gain is poor, such that gain bandwidth is poor because it have a very low transconductance value. Confirm now? So that's a drawback I call. What I said? Poor gain due to its low transconductance value call. So one of the parameters is transconductance. So that is poor for a FET. MOSFET also same. So poor gain due to its low transconductance as compared to BJT. As compared to BJT you can call. And one more is as compared to BJT, FET input impedance is high. Right? FET input impedance is what's are high. So these are the advantages and the drawbacks of FET over BJT you call. Right? Compare the terminals of FET with that of BJT terminals. See, so now in the case of FET, the terminals you find out is what, sir, means source, right? One more is a drain, other one is a gate. So these are the three terminals you may find out. Whereas in BJT, the three terminals you find out is what you can call, sir, emitter, right, base and collector. So these are the terminals you may find out in BJT. So BJT is available as NPN and PNP. FET is also available as N channel and P channel. If you ask that what are the comparison of the terminals you can call. If I go for functioning of these terminals, so there is a similarities of BJT and FET terminals you can call. In the case of BJT, any carrier can flow from emitter to collector via base. Like that, in the case of FET, any carrier, whether it is N channel or P channel, any carrier can always move from source to drain via gate. So source is the terminal where the carriers are enter the channel. Here the carriers can enter the body at emitter. You know that here the carriers who enter the channel at source can exit at a drain. The carriers can enter the channel at source and can exit at a drain. Here the carriers can enter the body at emitter and come out of the body at a collector. And you know that in the case of BZT, middle terminal is a base terminal of opposite impurity. In NPN, emitter and collector are N-type, base is a P-type. In NPN, emitter and collector are what, sir? N-type, base is a P-type you can call. So base must be opposite impurity than compared to emitter and collector. In the case of transistor, BZT, emitter and collector are same type of impurity, base must be opposite. In the same way, here also, gate, source and drain are same type of impurity, right? And gate is quite opposite impurity of source and drain. Suppose if I go for N-channel body, there source and drain are N-type and gate must be P-type. If you go for P-channel body, there source and drain are P-type, gate must be N-type you can call. So here base must be opposite impurity than compared to emitter and collector. Here gate should be opposite impurity than compared to what, sir, means source and drain. And here the input junction here is concerned between what, sir, means emitter and base. In the case of BZT, input junction is between what? Emitter and base. Here output junction is between what, sir? Collector and base. Base is common for input and output junction area. Suppose if you go for InFET, who is the input junction, sir? Input junction is between gate and source. Input junction is between gate and source. Output junction is between what, sir, means gate and drain. Output junction is between gate and drain, and input junction is between gate and source you can call. And now let us see this one now. As sir, here the channel width is controlled by what, sir, means gate. So gate is a person that is called as a controlled switch that can control the width of the channel. So channel width is very important for current conductivity you can call. So here channel width is controlled by gate voltage you can say. And one more thing, you say that if we compare the BZT and effective terminals, in the case of FET, source and drain are interchangeable. Source and drain are interchangeable, but in BZT, emitter and collector do not be interchangeable. In BZT, the emitter and collector do not be interchangeable. That interchangeable condition is applicable only for FET and MOSFET, not for BZT you can call. So in the case of FET and MOSFET, source and drain are interchangeable, but in BZT, emitter and collector are not interchangeable you can call. What is the meaning of interchangeable condition, sir? Other than middle terminal of gate, in FET and MOSFET, you can accept one of the extreme terminal as a source, then automatically the other one can act as a drain. No restriction, this is a source, that is a drain. Among the three terminals, the middle terminal must be a gate. Among the two opposite or extreme terminals, one can be taken as a source, automatically the other one can act as a drain. That's the case, but that condition is not applicable in the case of BZT you say. So similarities are, the function of source is same as emitter, the function of drain is same as collector, the function of gate is same as base. Other than this, what I told you, so in the case of FET, source and drain are interchangeable, but in BZT, emitter and collector do not be interchangeable. Confirm now? So that's not applicable for BZT. Here input junction is emitter, between emitter and base, output junction is between collector and base. Here input junction is between gate and source, output junction is between gate and drain. Got it now? So in the case of BZT, base must be opposite impurity than compared to emitter and collector. Emitter and collector must be same type of impurity. In the case of FET, gate must be opposite impurity than compared to source and drain. Not only here, MOSFET also same. And again, source and drain are of the same type of impurity. Source and drain to be of same type of impurity call. If you go for N-channel body where source and drain are N-type, gate must be P-type. If you go for P-channel body, source and drain are P-type and gate must be N-type we call. Understand this? Is FET voltage or current controlled? Explain a call. So FET is a voltage control device or a current control device he call, and how it is. Now we can able to explain he asking, sir. Now I can able to examine what it is. It is a voltage controlled or current controlled. Now I can able to discuss that one now. So you know that BJT is a current control device. In the case of BJT, any change in output current controlled by input current you call. In the case of BJT, any change in output current controlled by input current. But in the case of FET, the output current controlled by input gate voltage, such that FET is a voltage control device. FET is what? Voltage control device. Whereas BJT is a current control device you call. Suppose now I can able to go for explanation of this. Now I take some N-channel FET. This is some N-channel FET you can call. Right, sir? It is N-type silicon body and it should be a lightly doped one you call. It must be a lightly doped. What is the necessity to have a lightly doped you can examine? Why the channel body is lightly doped here means the condition is that, so while you can able to consider the barrier mostly occupy the channel so that the channel width can be controlled by the occupants of the barrier. For that purpose, the N-type material should be lightly doped. Now I take a body of N-channel FET, right? That must be lightly doped, making to say that, alright, the channel width could be controlled by the occupants of the barrier due to its light doping. So look like a BJT, this FET have two p-n junctions and that can be done by diffusing two p plus materials at the center on both sides like this. This is one p-type material of highly doped. This is another p-type material of highly doped. Two highly doped p-type material you are using, I told. Two highly doped p-type material you are using, sir. Right? One is, right, this is one of that one. Another one it is. Sir, each one can form a junction called P plus N junction. Each one form a junction called P plus N junction. The space between them is called as a channel. So the width of this channel is very important, sir, for current conductivity. The width of that channel is very important, sir, for current conductivity can call. And three terminals, you know, those are source, sir, through which carriers can enter the channel, drain, sir, through which the carriers can left the channel. Confirm? And these two are internally connected, sir. These two internally connected p-type material to be called a gate. The two internally connected p-type materials are called what, sir? Gate you can call. So now he asked that FET is a voltage or current control I call. So this is the FET structure you say. And now I told already in the case of FET, the current is due to drift mechanism, making that you need to drift the carriers from source to drain. How do you do this one, sir? That to be done for N-channel FET body, keeping drain must be positive with respect to source like this. So this is the drain supply, sir, that must be made positive with respect to source and the corresponding terminal voltage you named as VDS. This is the case. So if it is a p-channel body, sir, where source kept positive with respect to drain. In an N-channel body, drain should be positive with respect to source. In p-channel body, source should be positive with respect to drain you can call. Right? So this is the case. So it look like some reverse bias effects are near the drain as compared to source. It can causing a reverse bias effect near the drain as compared to source. So what is the barrier effect which can be found with the drain voltage, sir, that can expand near to drain and tapers or fall down while you come to the source? What is that corresponding barrier effect, sir, which can exist very close to drain, because the barrier effect that is reverse bias effect to drain. While you come to the channel body near that channel type, sir, that is near to source, that barrier effect come to reducing because source is not at reverse bias effect as compared to drain. And you see this one now, sir, for ordinary drain voltage, this one not causing any effect on the channel because it is not an exact reverse bias. Right? For ordinary drain voltage, no influence by this drain voltage on the channel. If you go for higher values of the drain voltage, sir, at that moment it can causing a small effect on the channel. It causing a small effect on the channel. Got it now? So now what is this one, sir? For current conductivity, FET must be operated in depletion mode. So FET to be operated in what, sir? FET is operated in depletion mode only, sir. Operated in depletion only mode you call. You do not operate in enhancement mode, sir. Depletion means what, sir? Reverse bias gate voltage. Reverse bias gate voltage, sir. You do not operate the forward bias gate voltage, sir. Check up now. See this one now. This is the case. This is the reverse bias gate voltage. Gate P type negative voltage, source N type positive. This is the applied gate voltage we call. And you see this one now. This corresponding voltage is called VGS. And what is the current you can define? That is called IZ. That is equal to 0. Why, sir? Means FET do not allow any minority current, just now I told, so that it is a purely reverse bias junction, so that minority current not allowed, sir, so that IC equal to 0. And you see this one now, as compared to the drain voltage, sir, this VGS exactly act as a reverse bias on each PN junction of the FET. So for each PN junction, this VGS causing an exact reverse bias effect, you can call. So according to the PN junction phenomenon, you know that with applied reverse bias voltage, the barrier can expand, sir. The barrier can expand, and you learn that barrier should be expanding near to what, near expanding more in a lightly doped area. Right? Who is lightly doped area, sir? Channel. For that purpose, this channel body can be kept lightly doped. We can control the width of the channel by keeping what, sir, means lightly doping. Suppose if I don't apply any gate voltage, sir, if I don't apply any gate voltage, the channel is almost free, you can call. Why, sir? What is that one? You can commonly define this drain voltage as a fix. So channel width is mainly controlled by the gate voltage, sir. Commonly can keep this one as a variable. So can keep the drain voltage as a fixed one, sir. And commonly you say that gate voltage should be variable because channel width is mainly controlled by the gate voltage. Suppose if I keep VGS equal to 0, sir, the channel width is almost free. So what is the drain voltage you keep? Here barrier is formed, sir, but that barrier is expanding towards the drain and it tapers as you move towards the channel like this. So this barrier look like be what, sir? Wedge type, you say. It is unsymmetric formation with respect to the drain voltage. So this is the barrier effect with respect to drain voltage, sir. Barrier effect with respect to drain voltage, you say. That should be very close to drain and it tapers as you move towards what I told, source of the channel body. So channel is almost free, because I apply ordinary drain voltage that do not causing any effect on the channel, keeping VGS equal to 0 volts, sir. So what do you find out, sir? Channel is free. So depending on this applied drain voltage, there is some repulsive forces acting on the electrons. So there is a tendency of maximum electrons can flow. So the electrons are flowing like this. The current is maximum, we call that to be called ID, sir. And you find out here at VGS equal to 0, at VGS equal to 0 volt, channel is free, you can call, and ID should be maximum. ID should be maximum, sir, called as short circuited gate to source junction drain current, you can call. Short circuit, sir, VGS 0 means gate junction is shorted. Short circuited gate to source junction drain current, you say, are simply called saturation drain current, IDSS, sir. Saturation drain current, IDSS, you call. So even the input voltage 0, it is a person that allows the current. Based on that, FET is called as a normally on device. Confirm now? It is also commonly asked one, sir. FET is what means normally on or normally off, means it is a normally on device. Normally on means allows the current even if the input voltage 0. FET is a normally on device allowing the current even the applied input bias voltage 0. Confirm? So now we can able to examine by increasing the reverse bias gate voltage what happened there with applied increase, with increase of reverse bias gate voltage, sir. The barrier can be formed across each junction like this. So this is the barrier effect across each junction with respect to VGS, sir. This is with respect to VGS, you say. With respect to VGS, sir. Barrier effect with respect to VGS. So with respect to VGS, that's a barrier effect you can call. Got it now, students? So even for ordinary gate voltage, the barrier should be effective across each junction. So it can effectively control the channel width. So here uncovered ions are placed, so that effective channel width reduces. Thereby the tendency here, it is a fixed one. Repulsive force is same, but number of electrons jumping is less, drifting is less. Thereby the drain current come below IDSS, such that you can confirm the output drain current varies as a function of input gate voltage. The output drain current can be varied as a function of input gate voltage, such that it is a voltage control device. And if we continuously increase the gate voltage, channel width go on decreasing, ID become decreases. And at a particular gate voltage called as a cutoff gate voltage, the channel width is 0, where ID equal to 0, such that it acts as a what sir means off switch. So at cutoff point where VGS equal to VGS off, ID equal to 0, act as a off switch you can call. Got it now, students? So what I told you, so as the reverse bias VGS, as the applied VGS increases, the drain current decreases, you say. So output drain current is controlled by input voltage. By that, FET is called as a voltage control device. Confirm? So applied reverse bias VGS increases, channel width decreases by the expansion of the barrier. Confirm? Then ID decrease below IDSS. ID decreasing below IDSS we call at cutoff gate voltage. Confirm? That you named as VGS of channel width is 0 by the completion of the barrier of both sides. Channel width is 0 where ID equal to 0 act as off switch. So this cutoff gate voltage is also called as a pinch off voltage, right? So you see this one now. Also this cutoff gate voltage VGS off is also called as a pinch off voltage. It is the pinch off gate voltage at which the drain current is 0 you call pinch off voltage, right? So output drain current is controlled by what, sir? Input gate voltage. So FET is a voltage controlled. You confirm. FET is voltage controlled as ID, output drain current ID, depend on input VGS. Done for now? So drain current depend on what, sir? Input VGS. By that it is called as a voltage control device, students. Remember? And you observe now, students, why do you operate only in depletion mode, sir? Why don't you operate this one? Sorry. Why don't you operate this one in enhancement mode? You can call, sir, it is a person to be operated only in depletion mode, I call. Why don't you operate this person in the enhancement mode? Means, sir, if I apply enhancement mode means forward bias gate voltage, sir. If I apply forward bias gate voltage, no meaning of the channel width variation. Channel width is as it is, sir, because in forward bias, no meaning of barrier effect you can call. Barrier effect comes to reducing effect only there. So, but what is my condition, sir? Instead of transferring the electrons towards the drain, they are circulating between gate and source. This is the case. If I apply forward bias gate voltage, none of the electron can reach the drain, sir, so that electrons are circulating between gate and source. Nobody can move towards the drain, so that the path do not complete by the flow of electrons. Without completing the path by the flow of carriers, the conductivity is not possible. The conductivity is not possible. And being the input junction is reverse bias of depletion mode, gate terminal do not draw any current, sir, indicating that so only input voltage is there. So the body having a drain current that should be same as source current. No gate current you can call, such that in FET and MOSFET, drain current should be same as what? Source current you can call. So confirm now, FET is a body of voltage control device. Here current is mainly due to drift mechanism. At VGS equal to 0 volt, channel width is nothing but free, right? Because of barrier effect is less, you can call channel is free, sir. More number of carriers are drifting, drain current is maximum. Sir, this is a person called normally on device because it allows the current even if input voltage 0. Even the input voltage 0, sir, it is a person that can allows the current you can call. Sir, as the reverse bias voltage of VGS increasing in depletion mode, channel width goes to be reducing by the occupants of the barrier on both sides, such that the drain current come below IDSS I call. At cutoff gate voltage, the drain current becomes 0, sir. That cutoff gate voltage is also called as a pinch off voltage. Confirm on this? Okay, check out the next one. Explain how drain current ID varies in linear and saturation regions. How drain current varies in linear and saturation region you can call, sir. Now I can able to show that one to you like this. So from output characteristic graph, I can show that one to you, sir. So this is the output characteristic graph of it. Output characteristics or drain characteristics also we call. So if I draw that output or drain characteristics, sir, this will be the graph you can expect for a FET. So this is the drain voltage, sir. This would be the drain current. Keeping gate voltage is constant, sir. What's all I told that channel width is mainly controlled by gate voltage, that you keep as a constant, sir. Suppose I'm a person, I can keep gate voltage 0, sir. Just now I told the diagram to you, sir. Now I can keep that gate voltage is constant, that to be 0 volt. Now channel is almost free. Just now, whenever the gate voltage 0, sir, channel is almost free, you can call. Now the drain current can be varying with respect to what, sir, means. With respect to what, sir, means. So drain voltage you can call. I start to increase the drain voltage from 0 volt. If I increase the drain voltage from 0 volt, sir, channel is free, increasing of the drain potential, making that the repulsive force on the carriers also increasing linearly, such that you find out that under low voltage values of VDS, the drain current increasing with linear movement of flow of carriers like this. So this is the small voltage region, sir, where you can expect that the current varies linearly with applied voltage. Why, sir? In this linear region, the drain voltage is small, so that it do not causing any barrier effect on the channel, sir. Channel is free, confirm now, so that with increasing of drain voltage, the force on the carriers is increasing linearly, so that movement increases linearly, the current increases linearly. This is the linear region. That to be happen only for what, sir? Small voltage regions we call. Says for now. This is the case. So in the small voltage region, the drain current can vary linearly with applied to drain voltage. Right, and this could be happen only for small values of drain voltage, sir, where no barrier effect on the channel by the drain voltage, sir, because applied voltage is very small, I told, and already gate voltage kept constant of 0, so that channel is free. So with the applied drain voltage of low voltage values, so drain current increasing linearly with linear movement of carriers. Confirm? Sir, once I reach a particular point, that point I call as a what, sir? Pinch off point you can call. This is a particular point. That point is called as a pinch off point, sir, where the voltage is called as a pinch off voltage you can call, where the voltage is called what, sir? Pinch off voltage you say. This is the particular point. There the voltage is called as a pinch off voltage. It is called a pinch off drain voltage, sir. It is the minimum drain voltage you can call, where maximum possible number of carriers can left the channel for the given gate voltage constant. For the given gate voltage constant, the maximum number of carriers can able to make a journey from source to drain, such that the current may attains its maximum. So for VGS equal to 0 case, sir, this current look like be what, sir? IDSS, saturated drain current. The current may attain its maximum, sir. This is the particular voltage of drain, that is the minimum drain voltage, where almost all the carriers, maximum number of carriers can left the channel you can call from source to drain, and causing a maximum drain current for a given gate voltage constant depending on the channel width. After that, what do you find out, sir? Even the drain voltage you are increasing, no further change in drain current, because what is the maximum possibility of carriers I told that to be defined at a pinch off only, after which even a change the voltage, the same number of carriers are only moving, same steady number of carriers are only moving from source to drain, such that the current look like be constant like this. This is the case. The current remains to be same, sir. After that, the current remains to be same you can call. Even you are increasing the drain voltage, no further increasing drain current you can call. Remember now? This is the case. Sorry. Confirm? So this is the particular reason you can find out, sir, where the drain current increasing like this. So if I go for some higher voltage of drain, sir, higher voltage of drain, what happen you can call, sir, means there avalanche breakdown can take place. This is only theoretical, sir, practically not possible. This is called as avalanche breakdown region you call. In that breakdown region, so voltage is almost constant, but current increasing rapidly. So it could be happen for high values of drain voltage. High values of drain voltage you can call. For ideal case, sir, for practical case, this is not commonly considered, right? So this is the graph that I can able to make for what? VGS equal to 0 volt. Sir, you can also repeat this graph for different constant values of VGS like this. Suppose one more graph I can make, sir, some for VGS equal to some -1 volt you can call. See this one now? Like this. This is one more graph I can make like this, sir. And so now you can able to go for, sir, higher values of drain voltage. There the avalanche breakdown appears like this. This is made for VGS equal to -1 volt constant. And one more thing you remember now, sir, if I increasing that reverse bias gate voltage, the pinch off comes to earlier. So first case pinch off is here, second case pinch off is here. So increasing of gate voltage, the pinch off voltage slightly become lower. Pinch off voltage slightly become lower, you can call. So it is the process. If you do this one continuously at cutoff gate voltage, what you can find out, sir? I told that the current become almost zero. This is VGS off, where channel width is 0, so right, indicating that no current, act as a off switch. This is the place where it acts as a off switch, sir. He asked that, explain how the drain current varies in linear and saturation region. Who is the linear region, sir? This portion is called as a linear region, you call. So this one is called as a linear region, sir, or a triode region also we call. It is a linear region or a triode region you can call, or ohmic region, where the output drain current varies linearly with the drain voltage. Same type of characteristic graph you can also find out in MOSFET, right? So here you can observe that in this linear region, this drain current varies linearly with the drain voltage, act as a linear resistor or ohmic resistor, and here drain current is a function of both VGS and VDS. In linear region, drain current is a function of both gate voltage and what? Drain voltage you can call. Confirm? Suppose just after pinch off you can go, this is called as a pinch off region, sir. It is called as a pinch off region. You can say, sir, this pinch off region same as the saturation mode of a BJT, because where the current do not respond, even the voltage changing. And in the saturation region, the characteristic graph almost have a flat response, where FET look like an ideal current source. FET look like an ideal current source, as well as it can act as a voltage amplifier. Right? So this is the pinch off region that is called as a saturation mode of a BZ you can call, where the current remain almost constant, even the drain voltage is changing and look like an ideal current source, act as a voltage amplifier also. And this is what you can call, sir, this portion is avalanche breakdown. That to be happen for high values of drain voltage only theoretical conditions, sir. So in the pinch off region or saturation region, if you expect that, what the thing you may find out, sir, means in the case of pinch off or saturation region, you find out that drain current is found to be depend on only gate voltage and independent of drain voltage. It is depend on VGS. VGS of reverse bias increasing, drain current come down. But with respect to drain voltage, drain current is constant. So in linear region, it is a function of both VGS and VDS. In pinch off or saturation region, it is a function of only VGS you can call. Only VGS. That's the drain current you may define. And so now, what are the thing I am saying? Check up this. So these linear and saturation regions are differentiated by pinch off point you can call. Both are differentiated by what, sir? Pinch off point. That can differentiate both linear and saturation. Confirm? Linear region exist. MOSFET also same, sir, for small value of VDS. Confirm? Where ID is a function of both VGS and VDS, sir. ID is a function of both VGS and VDS, and in this region FET can act as a linear resistor, sir, and one of the application of FET you may find out in the linear region, that to be called as a voltage variable resistor. Confirm? In linear region, right, FET used as a linear resistor, nothing but it can be used as voltage variable resistor, sir. VVR device, voltage variable resistor. That you can check out next. So what I find out, sir, means the pinch off occurs at a particular drain voltage, sir, at which the drain current become maximum and constant. So pinch off occurs at a particular drain voltage, sir, at which the drain current become maximum and constant, I can call. Pinch off occurs at a particular VDS called what, sir? Pinch off voltage, called pinch off voltage VP, where ID become constant, sir. Drain current become constant, you say. Confirm? So before pinch off it is linear, sir. After pinch off it is in saturation region. So saturation region means it is similar to the saturation mode of a BZT, sir. Recall, it is nothing but what you can call saturation mode of a BZT, you say. See this one now. Pinch off region is same as what I told, saturation mode of BZT, sir, right, where ID function of VGS only, ID function of VGS, sir, gate voltage only, call gate only, sir, and act as ideal current source, because current is independent of voltage. Act as ideal current source, sir, ideal current source in that area, and used as an amplifier, voltage amplifier, sir, and used as voltage amplifier in that area, you call. Confirm? So what the question is asking? So how the drain current varies in linear and saturation regions? In linear region, the drain current varies linearly with the drain voltage, where the drain current is a function of both VGS and VDS. In saturation region, nothing but same as pinch off region, you call, where drain current is only a function of VGS, right? With respect to VDS, it remains constant, look like what, sir, means ideal current source. That's the case, sir. Okay. Next one, now check out, sir. Why FET is called as a square law device? Why FET is called as what, sir? Square law device. So now we can able to examine this one now from the transfer characteristic graph of FET, sir. So now I can able to examine this, how this is, sir, means from the transfer characteristic of a FET. Transfer characteristic of FET indicate how the FET look like as a voltage control device, sir. How the FET look like what, sir? Voltage control device, you call. See this one now, this is the transfer characteristic graph of FET, you can call. So if I draw the transfer characteristic graph of FET, sir, suppose for n channel FET you do, you know that there the gate voltage should be negative. Just now you discussed that circuit, sir. Gate voltage negative, because gate is a P type there. Reverse bias voltage of depletion mode you can apply. Gate voltage negative for n channel FET you can call. So this is the drain current, you say. This is for n channel FET, sir, I drawn. Sir, you know that with respect to gate voltage, at gate voltage 0 you can call the drain current look like be maximum. This is called IDSS. The drain current look like be maximum, sir, that equal to what, sir, means IDSS you can call saturated drain current. So because of the channel is completely free there, suppose if I go for what, sir, means the gate voltage increases, the drain current come to be decreases, you can call. As the gate voltage increases, sir, the drain current decreasing. According to the practical version, sir, this drain current decreasing at the square law rate, that can be indicated by what, sir, means parabolic nature, like this. And this drain current becomes 0 at particular gate voltage, that I can call VGS off. And this VGS off can also be called as a pinch off gate voltage. So there are two type of pinch off voltage, sir. In terms of gate voltage at which the drain current is 0. If I consider the pinch off in terms of drain voltage, sir, it is the drain voltage at which the drain current become maximum and constant. So pinch off voltage is the same as cut off gate voltage, we can call. So the pinch off voltage is nothing but cut off gate voltage here, at which the drain current 0. So you observe now here drain current decreasing at the square law rate of applied VGS, sir. By that the FET is called as a square law device. FET is called as what? Square law device. Confirm now what I saying? ID decreasing at the square law rate of applied VGS. So drain current decreasing at the square law rate of applied VGS, and hence called square law device. And called as a square law device, sir. And called as what? Square law device, you say. Sorry. So this is a person called as a square law device. So we can also verify mathematically, sir, using what sir means Schottky equation. So Schottky equation should be commonly applicable in saturation mode of effect, sir. Saturation mode of effect you can call. See, so now, sir, how to define this? So saturation mode, sir, from Schottky equation, this is the thing you may call. From Schottky equation. From Schottky equation, you can call, what is the formula for ID, sir? ID is a function of VGS. ID equal to IDSS into 1 minus VGS by VP whole square, where VP is nothing but a pinch off voltage, nothing but called cutoff gate voltage, sir. This VP is nothing but what? VGS off you can call. So it is nothing but VGS off, sir. So IDSS is nothing but maximum drain current you can call, indicating that drain current decreasing at the square law rate of VGS. Drain current decreasing at the square law rate of VGS, sir. So by that, the FET is commonly called as a square law device. FET is commonly called as what, sir? Square law device. Not only FET, sir, MOSFET is also same. FET and MOSFET are called square law elements you can call, where the drain current decreasing at the square law rate of the applied gate voltage. Confirm now. So from Schottky equation in saturation mode, you can estimate the equation for drain current like this, right? ID equal to IDSS into 1 minus VGS by VP whole square ampere. This formula is very useful whenever you can use the FET as an amplifier. Okay. What are the parameters of FET you can call? Sir, FET have 3 parameters. Same thing you can also expect for MOSFET also, sir. One is what, sir, means output drain resistance. That is nothing but AC drain resistance from output characteristic graph you can define, sir. So what are the parameters means? One of the parameter you can call AC or output drain resistance, sir. AC or output drain resistance you call. This is one of the parameter you may define. So RD, sir, you can indicate as a RD. This is change in drain voltage with respect to change in drain current, sir, keeping what, sir, means VGS equal to constant. Keeping gate voltage constant, you define this, and this drain resistance, so commonly calculated from output characteristic graph of MOSFET, sir. So this is how much this means. For FET, it is around 0.1 mega ohm to 1 mega ohm, sir. And for FET, input resistance should be, already you know that gate current 0. Ideally, resistance of the gate is nothing but infinity you can call. Practically, input resistance of FET is nothing but how much, sir? 100 mega ohms, very high. Ideally, what you can call, sir, infinite resistance, but practically small minority gate current flows, it is negligible one. Based on that, input resistance of FET is about 100 mega ohms you can call. So output resistance to be defined from output characteristic graph, taking as a slope from what, sir, means, that is nothing but how much you can call, 0.1 mega ohm to 1 mega ohm you can call, right? If you go for saturation region or active region of a FET, there the curves have a flat response, just you can call, indicating that even the voltage changing, current do not be changing. So for ideal case, RD tends to infinity, right? So because of flat response in the active region, that is called as a pinch off or saturation mode of a FET you call, drain RD tends to infinity you can call, because change of current is 0, right? So one more parameter you may call transconductance, that is defined from transfer graph. Transconductance or mutual conductance also you can call. Transconductance denoted by GM, that is defined from transfer characteristic graph. Just now you know this is indicated as change in output current with respect to change in input voltage, delta ID by delta VGS you call. So it is defined as delta ID by delta VGS, keeping VDS equal to constant. So whose unit is ampere per volt or mho, or you can also use SI unit called Siemens. Okay, or SI unit of Siemens can also use. So main drawback of FET, I told you just now, it has poor gain. I call that poor gain is mainly due to its low transconductance. So this is very, very poor for a FET. How much means it should be around 1 millisiemens to 20 millisiemens you can call. For a FET, this is very, very poor. This is how much means, sir, around 1 millisiemens to 20 millisiemens you can call. Based on that, the voltage gain of a FET amplifier is very, very less as compared to BJT amplifiers, because the gain mainly depend on this transconductance value. How do you say that one means? That I show to you by one more parameter, that to be called what, sir, means, right? Amplification factor. One more thing I show to you. Amplification factor, this is a voltage gain factor you call. It is mainly depend on GM you say. This is one more parameter of this amplification factor mu, that you can call delta VDS by delta VGS you can call, keeping ID equal to constant. So you can rewrite this delta VDS by delta ID into delta ID by delta VGS you can write. So you already know that delta VDS by delta ID equal to drain resistance and delta ID by delta VGS equal to GM, transconductance. So the amplification factor mainly depend on the transconductance value of a FET. So that is poor you can call, so that it can have low gain factors. So these are the three parameters of a field effective transistor. Same thing you may also consider in MOSFET. Same thing you may also consider in what, sir? MOSFET. Okay. So now I can able to examine what is meant by VVR device. Just now I told that from characteristic graph. So in the linear region, FET can act as a resistor, commonly called as a voltage variable resistor I call, where I told that drain current is a function of both VGS and VDS. So one of the derived formula for that you see now. See this for now. In linear region, you know, where ID is a function of what? Both VGS and VDS. ID function of what, sir? Both VGS and VDS, sir. Gate voltage and drain voltage. And is this one, sir. This is the formula you are using. ID equal to 2 IDSS by VP. VP stands for pinch off voltage, you know, into 1 minus VGS by VP into VDS, sir. This is the formula you call. This is the formula for drain current in the linear region, where ID is a function of both VGS and VDS. With respect to VDS, it is increasing linearly. With respect to VGS, as VGS increasing, ID decreases, you call. This is the case. So now I need that resistance. So dou ID by dou VDS, now I can call delta ID by delta VDS type, dou ID by dou VDS. So 2 IDSS by VP is constant, you call, confirm, into 1 minus VGS by VP you call. Right, sir? With respect to VDS you are doing. So this is the case. So now I want the drain resistance I call. Check up now what the thing it is. So now I want that drain resistance RD, body resistance. That is dou VDS by dou ID call. So taking as a reciprocal of this, 1 by 2 IDSS by VP into 1 minus VGS by VP call. Right? Suppose now I can able to go for at VGS equal to 0 volt. At VGS equal to 0 volt, you know, ID maximum, IDSS you call. Then what is the drain resistance? RD tends to minimum, that I call R0. RD tends to minimum, that I can call R0. If I substitute now, what is R0, sir? So VGS equal to 0 you can keep. So 1 minus 0 by anything becomes 0. So that what you can get, sir, means it become as what, sir? VP by 2 IDSS you can call. Can I rewrite this equation like this? Vp by 2 IDSS into 1 minus VGS by Vp, you know. So already if I keep that one is a minimum, what is the value of R0 means? See this one now, and is like this, R0 equal to Vp by 2 IDSS equal. Vp by 2 IDSS, because VGS 0 you keep. Then what the thing you find out? So this is the expression for drain resistance. So what you find out, sir? RD equal to, now I can substitute this one here. See this one now? If I substitute Vp by 2 IDSS equal to R0, what the thing you find out, sir? R0 by 1 minus VGS by Vp. Confirm? RD equal to R0 by 1 minus VGS by Vp. So what the thing you can expect means, as VGS increases, what you can call, sir, VGS equal to 0, RD equal to R0 minimum. As VGS increases, it is a sub-reverse bias VGS you can call. So denominator comes to decreasing. So RD goes to be increases. Confirm? So what the thing you find out here? As VGS increases, RD increases above R0. So the body resistance increasing with respect to voltage and act as a VVR device, voltage variable resistor, and act as voltage variable resistor. So with this one now, it is a person to be used in what, sir, means automatic gain control circuit. So VVR device is the most useful one in communication systems in the generation of FM. So in the generation of FM, so we can able to use FET as a VVR device for the generation of FM signal, frequency modulated carrier. And not only that, this VVR device should be find out one more application, right? Automatic gain control circuit. Control the gain of a circuit automatically. Whenever the gain lead crossing the limit, automatically it can adjust the gain. So based on the resistance. So FET as a VVR device find the applications in FM generation, and as well as what you can call automatic gain control circuit, AGC bias, that is automatic gain control circuit you can call. Check out next. In FET, barrier expand mostly towards which side? Explain. Just now I told that if I go for FET, suppose if I go for N channel FET, I told this is the N channel FET I call, where I told that this is a channel of N type material of silicon, which one is a lightly doped I call, which is of what? Lightly doped I said to you, and on that you can define two PN junctions of opposite type of impurity, right? This is a highly doped P type material you are keep on opposite sides at the center. So each P type with this N-type body form a junction you call. This is called channel. And the tunnels are made, one from bottom called source, this is called drain, and these two P type are internally connected, that will be called gate I call. And you know that FET is commonly operated in the depletion mode, just now I told you, where drain is, so gate is kept at reverse bias potential with respect to source, this one, right? This is VGS. And to drift the carriers easily from source to drain, in N-channel body current carriers are electrons. For easy drifting of carriers, you keep the drain to be positive with respect to source, right? This is the drain voltage VDS. Now I told that with respect to gate voltage, right, it is exact reverse bias of each PN junction. The barrier effect should be symmetric of each junction like this. So with respect to gate voltage, the barrier should be formed across the channel area only. That not be expanding towards gate side, that to be expanding only to the channel. Why do not expanding towards gate side, sir? Because gate is highly doped material. So barrier do not be expanding towards gate. So no chance for the expansion of the barrier towards gate, because gate is highly doped one. So other than that gate, you can compare now drain and source where it can expanding. Now for that, now I can able to go for this. So with respect to drain voltage, you know, so that is not exact reverse bias, which can keep drain to be at reverse bias with respect to source. So with that one now, you can find out the barrier should be expanding mostly towards what, sir? Like this. expanding towards the drain, and while it come towards the source, it can tapers. So it is expanding towards the drain, and while it can comes towards, this can get tapers. Just a minute. So while it can move towards drain, it is expanding, you can call like this, and while you move towards the source, that can get tapers like this. So among the three terminals, the barrier expansion should be mostly towards the drain. So barrier not be expanding towards the gate because it is highly doped one, and as compared to source, the drain is look like a reverse bias, so that the expansion of the barrier is mostly towards the drain, either in MOSFET or FET. So the barrier is expanding mostly towards the drain. That should be the answer. Confirm. So this is the conditions you call. Barrier expands mostly towards the drain, sir, as drain is at reverse bias with respect to source. Confirm. No expansion of the barrier towards gate. Barrier do not expand towards gate as it is highly doped, sir. As it is highly doped person. So other than gate, remaining 2% are this, but as compared to source, drain is a reverse bias one, so that the barrier expansion is mostly towards drain. Got it now? Next one I go. What is MOSFET? How it differs from FET? Okay. What is MOSFET and how it differs from FET you can call. Check up now. This is the FET, sir. Suppose N channel FET I call. This is a FET. Suppose this is a N channel FET I call. Right, sir? This is gate, this is source, this is a drain, this will be a channel. Right, sir? In the case of N-channel FET, you know that electrons are moving from source to drain, sir. Electrons are moving from source to drain. The current can move from drain to source. Current flow always opposite to the channel. So the arrowhead on the gate terminal indicate the conventional current flow direction, sir. That is towards the channel like this. So this is the symbol for FET of N channel you call. So just in terms of symbol, you find out what is the symbol for MOSFET, sir. Right, what is the symbol for MOSFET? I can go. If I go for MOSFET, sir, this is the symbol you can call. This is gate, this is source, this is a drain, this will be the channel. So this is the MOSFET. Sir, if I compare FET and MOSFET as compared to FET, gate is connected to the channel, but in MOSFET, so gate is insulated from the channel. Gate is insulated, separated from the channel. By what it is separated from the channel, sir? In between channel and gate electrode, who is there, sir? Oxidation layer is there, silicon dioxide, this one. So as compared to FET, where gate is directly connected to the channel, in the case of MOSFET, gate is insulated from the channel by means of insulating layer of SiO2. By that, MOSFET is called as the insulated gate field effect transistor. And because of this insulation, you can find out that the input resistance of MOSFET is very high. As compared to FET, sir, MOSFET is nothing but smaller size. As compared to BZT, FET is a small size. Again, as compared to FET, MOSFET size again be small, you can call. And that too, because of this insulating layer by SiO2, the MOSFET input resistance is very high. So you know that FET input resistance is about 100 mega ohms I call. Even as compared to FET, the MOSFET input resistance is very high, about 10 power 10 to 10 power 15 ohms. So that is the main importance of this. So MOSFET input resistance is very high. So around 10 power 10 to 10 power 15 ohms, sir. And one more thing you remember now, whenever the MOSFET used in switching electronics, all this, so it completely avoid the use of resistors in its design. Best example, CMOS circuit, complementary metal oxide semiconductor circuit, sir, as compared to FET or BJT, whenever you can call, sir, the MOSFET completely avoid the use of resistors in its corresponding switching designs. Best example I call CMOS. Why it can avoid the resistor, sir? He himself said that myself is a highly resistive. That's the importance of the MOSFET. Okay, so MOSFET is commonly called as a insulated gate field effect transistor. And once again, FET to be operated only in depletion mode, sir, that is with reverse bias gate voltage. But MOSFET can operate in both the depletion mode and enhancement mode, sir. Depletion mode stands for reverse bias gate voltage. Enhancement mode stands for forward bias gate voltage, you can call. So it is a person can able to operate in both the depletion and enhancement modes. And this conducting, see this one now, sir, here the conducting channel and a gate electrode separated by SiO2 that look like a capacitor. So this structure, particularly this structure, if we call, that look like a capacitor, you can call, and whose body capacitance can be changed with the gate voltage. By that, the MOSFET can also be used in the applications as a voltage variable capacitor, and that named as a mass capacitor. With this structure, MOSFET considered as one of the person called mass capacitor, which can be used as a voltage variable capacitor. This is one more condition of this. And not only this, so having a capacitive nature, it can have a charge storage property in this oxide region and used in the design of memory. Best example, you know, static RAM. Confirm now? And as compared to FET, MOSFET output drain resistance is less, just it is order of kilo ohms. You know that in the case of FET, the output drain resistance order of some mega ohm, I told, 0.1 to 1 mega ohm I call, but in the case of MOSFET, the output drain resistance is order of kilo ohms. So as compared to FET, input resistance is high, output resistance is low, you call. So these are the some differences between FET and MOSFET, you say. Confirm what I told you? Sorry. So now, in FET, gate is connected to channel, right, sir? In MOSFET, gate is insulated, sir. Insulated means separated by SiO2, sir, oxidation coating from channel, called as ISFET, insulated gate field effect transistor. Called as what? ISFET, insulated gate field effect transistor. Confirm? Input resistance of MOSFET is high. How much I told? As compared to BJT, it is, sir, as compared to FET, it is high. That is 10 power 10 to 10 power 15 ohms due to the presence of this insulating layer, right? So, due to insulating layer, right, the channel and gate electrode separated by insulating layer of SiO2, that MOSFET can having some capacitive nature, sir, right? Due to insulating layer, confirm, MOSFET act as mass capacitor, MOSFET capacitor, sir, and used as a voltage variable capacitor by changing the gate voltage. Used as voltage variable capacitor. It also has some charge storage property. Based on that, you can able to use in the addition of memory, you can call. So in the case of FET, gate is connected to the channel. In the case of MOSFET, gate is disconnected from the channel. FET operated in depletion only mode, sir. MOSFET operated in depletion as well as enhancement modes. Depletion and enhancement modes. Understand this, students? Okay. Check out the next question. Why polysilicon gate is preferred over aluminum gate, you can call. So in the case of MOSFET, you know that already gate is separated from conducting channel by insulating layer of SiO2. So what in the beginning conditions that the gate is made of aluminum. Nowadays, this instead of aluminum gate, now you can able to use some polysilicon gate. So what is this polysilicon gate means? So the polysilicon gate is a polycrystalline metal of silicon, you can call. Polysilicon is a polycrystalline of silicon. So as compared to aluminum gate, polysilicon gate is preferred. What is the main reason means? The polysilicon electrical behavior is very close to silicon. The polysilicon electrical behavior is very close to silicon, you can call. And one more thing is, if I going to be use aluminum gate, you do not operate at high temperature, it can melt easily. Whereas polysilicon gate do not melt even at high temperature, and it can be useful even at high temperature also. And one more thing, in the enhancement MOSFET, you don't have a conducting channel. You have to induce the channel with applied gate voltage, that to be called threshold voltage, at which the channel is established in enhancement MOSFET. If I consider that aluminum gate, the required threshold voltage to build up the channel to be look like to be high, around 3 volt or 4 volt like this. Whereas if I make that gate with polysilicon, the threshold voltage probably low value that should be less than or equal to 1 volt. So these are the main reasons to prefer polysilicon gate instead of aluminum gate, you can call. And you remember now, as compared to aluminum gate, the polysilicon body having high resistivity. For that purpose, commonly you may prefer this polysilicon gate of what, sir, means highly doped either P plus or N plus material to reduce its resistivity. Confirm now? So what is the thing I say? Polysilicon gate is preferred, okay, because what I told, electrical behavior of polysilicon is close to silicon. Electrical behavior of polysilicon is close to silicon, you say. Next, aluminum metal should melt at high temperature, right? So aluminum can melt at high temperature, you call, and do not operate, right? It do not operate. Whereas polysilicon can easily operate, you call, can easily operate at high temperature without melting. At high temperature without melting condition. So this is one more reason I call. And one more thing what I told means, so in the case of enhancement MOSFET, you know, in the case of enhancement MOSFET, what the thing you find out, sir? The threshold voltage you require to build up the channel, because it has no conducting channel. With aluminum gate, the required threshold voltage look like to be high, whereas with the polysilicon gate that should be low, right? With aluminum gate, the threshold voltage gate voltage you call VT, by which you can generate the channel there. Threshold gate voltage required is high. So the required threshold voltage look like to be high for getting conducting channel. And it will look like lower, that is commonly less than 1 volt you can call. It look like lower, that is less than 1 volt, less than or equal to 1 volt probably with polysilicon. Right? So these are the advantages of polysilicon over aluminum gate. By that commonly you can replace aluminum gate with what's a polysilicon material. And commonly because of the polysilicon have a high resistivity as compared to aluminum one, such that polysilicon of highly doped N plus or P plus material should be used for gate condition. Right? Check out the next one. Why NMOS is preferred over PMOS? Right? Either depletion MOSFET or enhancement MOSFET of two types are there. One is NMOS, other one is PMOS. In the case of NMOS, the current carriers are 100% electrons. In the case of PMOS, the current carriers are 100% holes you call. So if I compare electrons and holes, already you know that electrons have more mobility than compared to holes. So that which is mostly preferred for current conductivity, faster conductivity means NMOS, because the current carriers are electrons. So if I compare NMOS and PMOS, sir, which can have good more high packing density means NMOS, because of the current carriers are electrons you can call. So first one is NMOS have a high packing density than compared to PMOS. Right? So if I compare NMOS and PMOS of same dimensions, right, as compared to PMOS, right, NMOS of same dimensions have more conductivity. Have more conductivity you can call. And this NMOS is commonly preferred, what you can call, sir, means for fast conductivity conditions because of the current carriers are electrons. Right? So if I compare NMOS and PMOS, who can maintain high resistivity than compared to other one means PMOS have high resistivity than compared to NMOS. If I compare NMOS and PMOS of same dimensions, so you may maintain the high resistance from PMOS. So PMOS is commonly used in the IC designs for resistor applications. Confirm? So the main advantage of NMOS is NMOS has, so in NMOS what sir, current carriers are electrons only you can call. NMOS has high packing density. Confirm? Next, if we compare NMOS and PMOS of same dimensions, NMOS and PMOS of same dimensions, what I told sir means NMOS body having a more conductivity because of the current carriers are electrons. Right? NMOS has more conductivity as compared to PMOS of same dimensions. And resistivity of NMOS is less. Resistivity of NMOS is what you can call, sir, less. And PMOS is commonly used as a resistor in IC designs you can call. Okay. Check out the next one of this. Distinguish depletion and enhancement MOSFETs. You already know that two type of MOSFETs are there, depletion MOSFET and enhancement MOSFET. So if I go for a D MOSFET and E MOSFET, what is the differences you find out means, in the case of D MOSFET, according to the construction, the channel should be built up. You don't create the channel should be present according to the construction, that is a physical channel to be present, you can call like a JFET. If you go for enhancement MOSFET, the physical channel do not be present. There you can able to induce the channel with applied certain gate voltage. Right? In the case of enhancement MOSFET, channel do not present. If I go for a depletion MOSFET, channel should be present. And if I go for a depletion MOSFET, it is designed to operate both in depletion mode and enhancement modes. In both modes, the depletion mode MOSFET can operate. Depletion mode as well as enhancement mode, both modes it can operate, you can call. By that it is called as a dual mode MOSFET you can call. Whereas enhancement MOSFET is designed to operate only in the enhancement mode, not in depletion mode. That's the case. And depletion mode MOSFET commonly called as a normally on device like a JFET. And one more thing, the operation of depletion MOSFET in depletion mode is the same as the JFET. And in addition to this, the depletion MOSFET also have enhancement mode we call, whereas JFET do not operate in the enhancement mode. So depletion MOSFET look like to be act as a normally on device where you can expect the current conductivity, even the applied input gate voltage is 0. If I go for enhancement MOSFET, there it is don't get the conductivity at applied gate voltage 0 because of no channel, and it is look like a normally off device. So depletion MOSFET is a normally on, whereas enhancement MOSFET is nothing but only a normally off device you can call. So according to the structure, if you go for depletion MOSFET and enhancement MOSFET, depletion MOSFET has conducting channel, and that too is not present in the case of enhancement MOSFET. Suppose now I can able to check out, this is the depletion MOSFET. See this one now. Suppose now I can able to go for some NMOS. I show first NMOS. So now let us see this one now. So any MOSFET construction to be done on a substrate. Substrate is the place where the construction of a device is to be done. Substrate is the area where the construction of a device is to be done. And in the case of MOSFET, the substrate must be opposite material. NMOS have a P-type substrate, PMOS have N-type substrate you can call. Suppose now I can able to go for the construction of NMOS of a depletion MOSFET. Here it can have a P-type substrate of lightly doped. This is a P-type substrate. This is a substrate body. On that, the construction of corresponding MOSFET to be done. So this is of lightly doped you can call. It is a lightly doped one, so that you can easily override the effect of it. So we are creating now compensated semiconductor. Already know that what is the compensated semiconductor, sir. If a given pure semiconductor is doped simultaneously with both donor and acceptor impurities, then that concerned semiconductor look like to act as a compensated semiconductor. So now let us see this one now, sir. I can able to use a substrate of P-type of lightly doped one to override its effect. Sir, how do you get here source and drain? Means by diffusing, sir, by locating a highly doped N-type semiconductors on both sides. Now one type of N-type semiconductor I diffuse here of highly doped, and one more N-type material I diffuse here of highly doped. So each highly doped N-type semiconductor now can able to place on each side of that semiconductor of P-type substrate, sir. This can act as a some source, this can act as a some drain. And this is the terminal that I taken here, that is called body terminal, sir. This is commonly act as a second gate terminal. This is commonly act as a second gate terminal you call. Confirm? So after source and drain diffusion over, what the thing you can call, sir? Entire surface area is overlaid with oxidation. What is the purpose of oxidation in IC technology? Means the oxidation SiO2, sir, it can able to act as a masking against the diffusion of impurities. As long as the oxidation is there, it's not possible to you to allocate or to allow any impurity into that body. It acts as a masking. If you want to insert any impurity, so you have to remove the oxidation coating in the specified place. How to remove that oxidation coating in the specified place, sir? By means of that photolithographic process. Using photolithographic process, you can remove the oxidation. So after source and drain diffusion over, the entire surface area is overlaid with what? SiO2 you can call, such that the channel body is insulated by SiO2. So this SiO2 can act as a masking against the diffusion of impurities in IC fabrications. So after that, you are indicating a polysilicon gate. This is the polysilicon gate. So this is NMOS. Commonly you are using some P plus polysilicon. It may no restriction. Originally may use either P plus or N plus. Commonly gate is of opposite type of channel condition. So now I can use some P plus polysilicon. So it is a composite semiconductor of body I call. So this one now, if I go for its cross-sectional view, this is originally a P-type semiconductor you call. Right, substrate body. From that I taken body terminal I call. Right. So this body is overlaid with what, sir? Means so this body is nothing but doped with what, sir? Means two N plus materials on top and bottom, so that this P-type effect to be negligible. So the body look like to be act as a N-type channel, and diffusion of two highly doped n-type materials on both sides of the body converted as a n-type channel and reducing the effect of p-type substrate. And now you are taking the terminals, one is the source, right? Other one is what? Drain. Source and drain look like be connected to the body. Whatever the gate, you know, gate should be insulated by SiO2 like this. See this one now, occur the construction, it is a person that have a channel. Channel should be present here. So this is the gate material of polysilicon. This is a polysilicon of gate. So according to the construction, in the case of depletion MOSFET, the channel should be present. So this body terminal taken from substrate, that look like we act as a second gate terminal you can call. So if I go for enhancement MOSFET, the construction is almost the same. So the construction is almost the same. The difference is that the channel should not be present. So if I go for enhancement MOSFET, what are the thing you can check up now? Now I can able to go for E MOSFET, enhancement MOSFET suppose. This is enhancement only MOSFET you say. In the case of enhancement only MOSFET, as compared to depletion MOSFET, the channel should not be present. The channel should not be present, you can call. Let us see this one now. What is this? Suppose in this one I can go for NMOS. So the construction seems to be same like a depletion MOSFET. What is that one? Now also I can take a lightly doped p-type substrate here. This is a p-type substrate of lightly doped. Confirm? So from that you taken a terminal called body terminal. That can act as a second gate terminal, same one. But in the case of your enhancement MOSFET, before source and drain diffusion, you say that entire surface area is overlaid with oxidation. I don't keep any source and drain diffusion. So first of all, the entire surface is overlaid with oxidation coating you call. So that none of the impurity allowed into that place. After that over, what the thing I can do means, I can remove the oxidation coating in the specified area, that is only at the edges I remove. So at the edge part I remove that one now, see this one now. Only at the edges I remove that. Instead of removing everything, I remove at edges only, sorry. So leaving that middle area as it is of that oxidation coating. Here the oxidation coating is as it is, sir. Oxidation coating is as it is you call. This is as it is. After completion of oxidation coating over, I can remove the oxidation at the edge part where you have a chance to introduce the impurity. Now I can able to locate the impurity of here some N plus. I can able to allocate the impurity of some N-type metal of highly doped one to act as a source. From that I take a connection called source. Here also, sir, this is open area. In this one I can able to introduce one more highly doped n-type material, sir, to act as a drain. So source and drain now can be generated. And remember now, this impurity do not penetrate into this one now because the entire middle area is nothing but containing oxidation coating. So none of the impurity can come into this side. So that the channel should not be present. So the diffusion of source and drain should be perfect in such a way that the effect of substrate is throughout in the middle region. The effect of substrate is throughout in the middle region because the entire middle region having oxidation condition. Confirm now, once the source and drain diffusion is over, again you can overlay with the entire surface with the oxidation, sir. This is the case. After that, you are introducing a polysilicon gate over that. A polysilicon gate should be introduced. So as compared to the depletion MOSFET, in the case of enhancement MOSFET, the source and drain are diffused such that the effect of substrate is throughout in the middle region like this. So the effect of substrate is throughout in the middle region, sir. This is N-type, this is N-type. So no path is made from source to drain. No path is made from source to drain a call. Sir, this is the source, this is the drain. Channel should not be present, sir. And you can able to keep the gate to be insulated by SiO2 like this. So this is polysilicon of P plus. Suppose I use, this is the gate. So as compared to the depletion MOSFET, in the case of enhancement MOSFET, channel should not be present physically. That you can able to create with applied gate voltage, and that to be possible in enhancement mode. By that it is called as enhancement only MOSFET. In depletion MOSFET, according to the structure, the channel should be present. Confirm now? And again, I say that one more difference is what, sir? Depletion MOSFET can operate in both modes, so depletion mode and enhancement mode. Whereas enhancement MOSFET can operate only in enhancement mode. And the depletion mode MOSFET operation under depletion mode is the same as JFET. Means it can have a drain current of saturation IDSS at VGS equal to 0, and as the gate voltage of reverse bias increasing, the drain current decreases. And not only that, the depletion MOSFET, if I operate in the enhancement mode, the drain current increasing with increase of gate voltage. So it can operate in both modes. But enhancement MOSFET is operated only in enhancement mode. And at VGS equal to 0, in the case of enhancement MOSFET, drain current 0, that can act as a normally off device. Normally off device. And so now, this is the thing you call. So if you compare that, what I told, D MOSFET has a channel, physical channel, right? Whereas E MOSFET, enhancement only MOSFET, has no channel. Channel should be induced there. Confirm? D MOSFET is a dual mode MOSFET you call. Is a dual mode MOSFET operating, what I told, both depletion. Depletion means reverse bias gate voltage, sir. Depletion means what? Reverse bias gate voltage we call. And enhancement. Enhancement means forward bias. Enhancement means what, sir? Forward bias. So it can operate both modes, sir. Okay. Now, whereas E MOSFET, enhancement MOSFET, do not operate in depletion mode, sir, because in depletion mode it do not find the channel. It can find the channel only in enhancement mode at a particular gate voltage called threshold gate voltage. By that it can operate only in enhancement mode. Whereas E MOSFET can operate, what, sir? In enhancement mode only. Can operate in enhancement mode only, sir. Confirm? And one more thing what I told, sir, depletion mode MOSFET in depletion mode is the same as JFET, sir. Depletion mode MOSFET operation in depletion mode same as JFET that you discussed already. D MOSFET in depletion mode is the same as JFET. That is nothing but its working principle same as JFET, right? And act as normally on device. It is a normally on device, sir, because look like a JFET, it have a drain current conductivity, right? Even at VGS equal to 0. Whereas E MOSFET, enhancement MOSFET you call, is a normally off device, sir, where you don't expect any drain current at VGS equal to 0. Normally off. So D MOSFET is a normally on device, sir. E MOSFET is a normally off device commonly called. So this is the main classifications you may find out. Okay. Check out the next one. Why D MOSFET is not preferred, right, as compared to enhancement MOSFET, E MOSFET. The main problem you find out that, suppose if I go for D MOSFET, sir, this is the case. This is the D MOSFET I call. Just now you discuss. it has a substrate of p type of light, right? That is nothing but lightly considered, because the complete space is occupied with the n-type channel of composite condition, you say. So this is a channel body, sir. So originally it is a p-type substrate. On diffusion of two highly doped n-type materials, the body converted as a n-type channel, neglecting the effect of p-type, sir. This is the body terminal we call. Commonly, this body terminal can act as a second gated terminal, sir, and this body effect to overcome by shorting that body terminal with the source. Suppose this is a n-mass I can call, sir. This is of n-mass 1. So this is a n-mass condition, sir. Right? So now let us see this one now. Here we are going to say that the gate is insulated by polysilicon. Sir, gate is a polysilicon material, you know, that is insulated by SiO2, sir. So this is a gate of polysilicon material we call. So this is the structure of n-mass where body terminal is shorted with the source. Let us see this one now. What is the problem in the case of depletion MOSFET, sir? Per conductivity condition, here the current carriers are electrons, sir. I wanted to allow these electrons to move from source to drain. How to make these electrons to drift from source to drain means already know that by making drain to be positive with respect to source. In n-mass, drain must be positive with respect to source, sir. Same thing in JFET also. Whereas in PMOS, source is positive with respect to drain, sir. In NMOS, drain should be positive with respect to source, and this corresponding voltage I call VDS. And just now you know this depletion MOSFET can operate in both depletion mode and enhancement mode, sir. Sir, depletion mode means reverse bias gate voltage we call. See this one now, that to be indicated by this applied bias of gate supply. This one, VCC. So if VCC equal to negative, sir, it is a depletion mode, that is reverse bias gate voltage, sir. Operate in depletion mode you can call. Confirm now? If applied VCC negative, sir, that is reverse bias gate voltage, sir. Reverse bias VCS, and it is in depletion mode, sir. And it is in depletion mode you call. And look like a JFET there. Where you find out, sir? Where you find out ID equal to IDSS, saturated drain current, at VCS equal to 0 volts, sir. At VCS equal to 0, channel is free, sir, maximum electrons drifting, so that drain current becomes maximum. And VCS ID decreasing, sir, ID come below IDSS as VCS increases, sir, and becomes 0 at cutoff gate voltage, right? At VCS equal to VCS of ID becomes 0, sir. See this one now. So this is the drain current that is flowing here. So gate current never be allowed because gate is insulated, sir. Gate look like open, you know. So gate current do not allowed there. You remember now, to turn off depletion MOSFET, I require, right, two power supplies. One to operate drain supply per NMOS, suppose I go. So to drift the electrons, I require drain to be positive with respect to source. So that require positive supply. To turn off the body, I require the gate supply must be opposite polarity, because you say that this body is become off, that is drain current 0 at VCS equal to VCS of, that is a reverse bias gate voltage of negative value I apply. So polarity of the input and output supply must be different. Opposite polarity supplies you require, so that it's not replace them with a common supply. So in the case of depletion MOSFET, to turn off the device, you must and should require two supplies of opposite polarity. So why, sir? To turn off, you must and should operate in depletion mode. Undo that or get off gate voltage you can call. Undo that what, sir? Cut off gate voltage. See this one now, sir. This one happen in depletion mode. For NMOS, that gate voltage is negative. But here, to drift the electrons, I require drain supply is a positive. So you must and should require two supplies, one for input, other one for output. So first to drawback. And one more thing is, sir, What is the required gate voltage to turn off that one? That should look like be more as compared to the applied drain voltage, as compared to that of applied drain voltage. So main thing is it require mainly two supplies to turn off, sir. So otherwise it's not be turn off, you can call. So based on that, depletion MOSFET is not be preferred in IC, sir, and commonly it is used as a resistor in IC designs. So the general application of the depletion MOSFET is what, sir? Resistor, you can call. Who is most popular in CMOS technology or VLSI conditions, sir? That is E-MOSFET, enhancement MOSFET only can preferred. Depletion MOSFET not be preferred, mainly because of requiring two power supplies of opposite polarity. Right? That's the main drawback of this. Don't you know? What I told? The main drawback is that it requires two supplies of what, sir? Opposite polarity. Opposite polarity to turn off, sir. Opposite polarity to turn off. Okay. Suppose if Vc is equal to positive, sir, that is forward bias gate voltage, sir, where you can expect ID increasing above IDSS, sir, above saturation drain current with VCS increase. And in this, it do not turn off, sir. So turn off possible only in depletion mode, sir. It do not turn off here. So to turn off the body, muscle should operate only in depletion mode. That's the problem. That depletion mode means muscle should require two supplies of opposite polarity, and that too it can turn off at a particular gate voltage I call cutoff gate voltage, sir. That value must be greater as compared to the applied drain voltage you can call. Such that depletion MOSFET commonly preferred to use as a resistor in IC designs. Who is most popular to use, sir? That is enhancement MOSFET. Enhancement MOSFET. Confirm now? So depletion MOSFET is not preferred. Why, sir? Means the main reason is it requires two supplies of opposite polarity because it is a normally on device, you know. So to turn off this one, I require two supplies of opposite polarity. That's be somewhat difficult one. Okay. Why channel do not present in the enhancement MOSFET? Why channel do not present in the enhancement MOSFET? Just now you learn that in the case of enhancement MOSFET, right, the diffusion of source and drain is such that the channel should not be present there. The channel should not be present there. The diffusion of source and drain is such that the effect of substrate is throughout in the middle region, such that channel should not be present in the case of enhancement MOSFET. See this one now already, you know. You discussed that cross-sectional view of enhancement MOSFET, sir. So originally it is a P-type body of substrate, right? This is called as a body terminal, sir. Here I told that the diffusion of source and drain is such that the effect of substrate is throughout in the middle region. The effect of substrate is throughout in the middle region I call, right? Such that what the thing you can call, sir? Channel should not be present. Channel should not be present, sir. Channel should not be present. Confirm? So if you want to build up the channel, so you can override the effect of this substrate. So how do you override that effect of substrate, sir? That to be done by the creation of inversion layer. That to be done by the creation of what, sir? Inversion layer you can call. So as compared to the depletion MOSFET, in the case of enhancement MOSFET, sir, channel should not be present. Confirm? This is what, sir? Polysilicon you say. This is of, sir, what, sir, means gate material of polysilicon. So this is silicon dioxide, sir, sorry. It is SiO2 of masking, sir. This is a polysilicon of gate. Confirm? So in the case of enhancement MOSFET, sir, channel is not present. Suppose it is a enhancement of NMOS, sir. This is the case. Gate, right, source, drain. So channel look like a broken line, sir. This is the symbol for NMOS you call. In the case of NMOS, the channel look like a broken line because it has no conducting path. Confirm now? What I told you? Diffusion of source and drain such that the effect of substrate is throughout in the middle region. Confirm? Is throughout in the middle region, you say. And thereby channel is not present. So that channel you can create by override the effect of what, sir? Substrate. That to be done by the generation of inversion layers, sir. That to be done by the creation of what? Inversion layer. That you can check out there. Next one. What is the function of inversion layer? Say this one now. What is the function of inversion layer? Here he asking that I can able to examine now. So same MOSFET I taken. Suppose it is of N mass, you know just now. Say this one now, sir. So entire middle region of a P-type substrate effect you call. Now this is of highly doped N-type, act as a source and drains are there. So here also source and drain are interchangeable, sir, like effect, you know. So this is the body terminal, sir. Commonly this body terminal act as a second gate terminal you call, that is shorted with the source to avoid that body effect, sir. Now look like a JFET or depletion MOSFET, what I can call. Here also to drift the electrons, sir. In the case of N mass body, suppose this is N mass body, sir. To drift the electrons, you keep that to drain to be positive with respect to source. Drain to be made positive with respect to source, sir. If it is a P mass, source to be made positive with respect to drain, sir. So this is N mass, drain kept positive with respect to source, we call. And you know that here this is a, what you can call, oxidation coating, sir. Over that polysilicon of gate is there. So this one now, sir. I told that it is a person that can operate only in enhancement mode, not in depletion mode. So this is the gate voltage we call, sir. This is the gate voltage. Suppose if you apply this one is a depletion mode of reverse bias gate voltage, see this one now. Here you can define the conductivity principle by means of the charging of this body, sir. So this is called as a channel interface, sir. Channel interface can act as a one conducting plate. Other one is nothing but this polysilicon gate act as another conducting plate, sir. We can define the conductivity of MOSFET by means of the charging mode of this capacitor, you say. Suppose if I operate in depletion mode, sir, so this plate can get negatively charged, sir. Then according to that charging condition, this one become positive charge. So if you wanted to override the effect of substrate, means we must also grow up opposite charge, sir. By growing opposite charge in that area, we can override the effect of that fellow. But here you are growing the similar charge at the interface. So instead of reducing its effect, we are going to be increasing the effect of that substrate, such that in the depletion mode, you never overcome the effect of the substrate, so that no chance for the channel build up. So how it is considered, sir? Only in the enhancement mode it is possible. Only in enhancement mode only it is possible, sir. Not in depletion mode, you call. So now I can able to go for enhancement mode. This is that. So this is the forward bias, sir. In the depletion mode, no chance for the channel. Now I can able to go for forward bias gate voltage called enhancement mode, sir. So start from 0. Suppose if the applied gate voltage 0, sir, no charge is built up. So the effect of substrate is throughout in the middle region, such that none of the carrier can move from source to drain. Drain current is 0. Act as a what, sir, means normally off device. Now if I increasing that forward bias gate voltage just above 0 volt, sir, see so now what happened? So this terminal can become positive charge. Then automatically can grow up what, sir? Here negative charge. The negative charge should be grow up at the interface, sir. The growth of the negative charge at the interface, right, causing what, sir, means inversion layer you call. So the inversion layer is the region of opposite charge, sir, which can grow up at the channel interface you can call, which can grow up at the channel interface by the charging of this capacitor by the applied forward bias. This one. As the negative charges grow up, you can call here, right? So that is called as the inversion layer. What is this inversion layer, sir? It is the phenomenon of generation of opposite charge to override or reduce the effect of the substrate. So inversion layer is the phenomenon of generation of opposite charge, right, at the interface to reduce the effect of substrate. So at a particular forward bias gate voltage, that is called as threshold gate voltage, sir. In this inversion layer, the channel should be built up. Once the channel is built up, sir, the carriers can able to drift from source to drain like this. Until that no carrier can move, sir. So in the case of enhancement MOSFET, we can able to build up the channel by the creation of inversion layer. And in this inversion layer, at a particular forward bias gate voltage called threshold gate voltage, channel look like to be present. Then the carriers can able to drift from source to drain and causing the drain current ID. Here gate is open, sir. You never expect any gate current. So the drain current flows for the applied gate voltage greater than or equal to threshold, sir. For the applied gate voltage less than threshold, sir, no channel, no current can flow, act as a off switch. Once the applied gate voltage crossing the threshold voltage, sir, where the drain current flow and is increasing with increase of VGS and act as a on switch. Confirm now? So what is this inversion layer I call, sir? Check up this. So what I told, inversion layer is the phenomenon of generation of what's sir, opposite charge or same charge? Generation of opposite charge at interface, right, to reduce the effect of substrate, to reduce the effect of what, sir? Substrate. That is called as the inversion layer. By that you can able to build up the channel. That channel should be induced, sir, not be permanent. Suppose if I withdraw the gate voltage, again the channel is called, what is that channel interference, what you can call charge build up, get collapsed, sir. What is the charge you build up at the interface that can get collapsed, and thereby again the effect of substrate comes throughout in the middle region, sir. Again the effect of substrate comes throughout in the middle region. So the channel that can be generated is a induced channel, never be permanent channel. Confirm? Check up next. So what is the threshold gate voltage VT called, sir? Just now I told that, sir, once you can create the inversion layer at a particular forward bias gate voltage, the channel should be built up, sir. At a particular forward bias gate voltage, the channel should be built up. That to be called as a what, sir? Means a threshold gate voltage. That to be called as threshold gate voltage you can call. So yes or now? So here I told that, so sorry. So yes for now, in this case, at a particular forward bias gate voltage, right, if increasing the forward bias gate voltage at a particular forward bias gate voltage, what I told, sir, means so the channel look like to be built up. Once the channel is built up, sir, the carriers can able to tend to move. So what is the forward bias gate voltage at which the channel is built up? That to be called as a threshold gate voltage, sir. Right, for the applied gate voltage less than threshold, no channel, no current flow, act as a off switch. Once the applied gate voltage cross that threshold voltage, sir, channel should be present, thereby the drain current can flow and the body have a conductivity. Right, so and this threshold gate voltage is what, sir, means look like positive for N mass, sir, and look like negative for P mass. Confirm now? What I told you? It is the forward bias gate voltage, sir, at which channel is induced by inversion layer, sir. Channel is induced by the inversion layer. So what is the forward bias gate voltage at which the channel is induced by the inversion layer? That to be called as a threshold gate voltage, sir. Sir, this is positive for N mass, negative for P mass, sir. So that commonly you taken as a modulus. Threshold voltage commonly taken as a modulus, sir. And you remember now, the value of threshold voltage is a function of three things, sir. Source to body voltage, gate oxide thickness, and doping concentration of substrate, sir. Na or Nd. So this is source to body voltage, sir. Source to body voltage we call VSB. This is SiO2 thickness, sir. Silicon dioxide thickness. Right. This is what, sir? Doping of substrate. Doping of substrate material, sir, by which that MOSFET you made. Substrate is the area where the construction to be done, I call. Na is the doping for what, sir, means P type of NMOS. So Nd is the doping concentration of what, sir, means N type of PMOS you can call. Sir, if any of this one increasing, the threshold voltage goes to be increases. If any of this one increases, sir, the threshold voltage look like be increasing. Confirm now? Says for now what I told? Vt increases if VSB increases, right, or T increases, or Na or Nd, anyone increase, sir, or all increase, what you can call. So always you require threshold voltage should be minimum, sir. By that the channel should be built up at earlier stage, so the conductivity become fast, right? So that switching response become fast. Sir, now Vt could be kept a minimum, sir. Vt must be required minimum by keeping VSB equal to 0. Source to body voltage 0, sir. By that commonly you say that source and body terminals are shorted. Source and body terminal what, sir? Shorted I can call. That I told you in the previous case of figure you see now. So source to body is shorted, sir. By that you can avoid that one, right? So commonly you can keep VSB equal to what, sir? 0 volt. Right, and commonly you say that, right, this one should be what, sir, means lightly doped or not, sir? Lightly doped substrate you can use. The doping concentration of substrate should be less, you can able to use. And not only, sir, gate oxide thickness should be minimum. The oxidation coating should be taken as a thickness is very minimum, sir, right? Keeping VSB equal to 0 and thickness T is minimum, sir. Minimum thickness you can use, and decreasing the, right, now you can able to take a lightly doped substrate and consider a lightly doped substrate, sir. Substrate should be lightly doped, already you know this. So keeping all these things, threshold voltage will be minimum we call. Threshold gate voltage look like be what, sir? Minimum. And one more thing you remember, sir, this threshold voltage commonly independent of what, sir, means threshold voltage is independent of type of polysilicon, sir. Vt is independent of type of polysilicon of P plus or N plus material. So even you change that P plus to N plus or N plus to P plus, sir, no change in the threshold voltage. Threshold voltage mainly depending on those factors I told. These are the factors, sir. So if you consider that polysilicon of P plus to N plus or N plus to P plus, no change in the threshold voltage you can call. Got it now? Sir, pinch off occurs at what value of drain voltage you can call? Says for now, sir, pinch off. What is this pinch off means? You know that once you can able to enter a pinch off condition, thereafter there is no further change in the drain current, even the drain voltage you consider to be changing. So pinch off occurs, right, with at a particular drain voltage, sir, at a particular drain voltage at which the voltage between gate and drain is equal to threshold voltage, is equal to what, sir? Threshold voltage. With respect to VDS, right, the pinch off occurs at a particular drain voltage at which what you can call, sir, the voltage between gate and drain equal to threshold voltage you call. Confirm now? Says for now what I say? Pinch off occurs at a particular drain voltage at which the voltage between, confirm, voltage between gate and drain is equal to threshold voltage, sir. This is the statement you call. So practically I verified this one. So that is what you can call, sir, at pinch off, what you can call Vc minus Vd equal to Vt call, or with respect to source commonly you can call Vgs minus Vds equal to Vt. Vgs minus Vds equal to what, sir? Vt you can call. Correct now, sir? Or Vds equal to what you say, sir? Vds equal to Vgs minus Vt. So this voltage is called as a pinch off voltage. So this pinch off voltage is a key person, sir, that can differentiate the linear and saturation conditions you call. Sir, before this pinch off, the MOSFET right in linear region you say. See this one now? For VDS less than VP, sir, for VDS less than VP you can call, where VDS is small, it is in linear mode. Confirm? For VDS greater than or equal to VP, it is in saturation mode, sir. Act as a constant current source like a FET. Pinch off or saturation mode. At VDS equal to VP, it is switching from one mode to the other mode, sir. At VDS equal to VP, it is switching from one state to the other state. For less than VP, it is linear. For greater than VP, it is in saturation. At equal to VP, it is a switching condition from one state to the other state. Confirm now? So what is body effect you call? Just now you learned that, sir, body terminal taken from the substrate, that look like to be act as a second gate to terminal. The body terminal taken from substrate, sir, that look like to be act as a second gate to terminal I told. Sir, now let us consider if this terminal is open, it can affect the channel conductivity, sir. It can affect the channel conductivity, and particularly in enhancement MOSFET, right, the threshold voltage goes to be increases. The threshold voltage goes to be increases, you can call. Sir, the variation in the threshold voltage, so with respect to this source to body voltage is called as a body effect, you can call. The variation in the threshold voltage with respect to this source to body voltage is called as a body effect, you can call. Sir, how do you overcome this body effect, sir? This body effect can be overcome by making the source to body voltage equal to 0. Source to body voltage is equal to 0, sir. How do you do this one? Means in the case of NMOS, this body terminal connected to either source or ground, sir, because in NMOS, source is commonly connected to ground. Whereas in PMOS, sir, the body effect can be overcome by connecting the body terminal to either source or to the drain supply, because in the case of PMOS, source is connected to the drain supply, sir. Confirm now? So the body terminal taken from what's been substrate, which look like as a second gate to terminal I call. Confirm now? And which look like to be affect to the channel conductivity, sir, if it is open. So particularly in the enhancement MOSFET, sir, with this source to body voltage, with this body effect, what you can call, sir, threshold voltage increases, so that the channel should be built up at a later time. So it can causing effect on the threshold voltage. What are the changes or what are the variation in the threshold voltage with this source to body voltage is called as a body effect I call. How do you overcome this one, sir? Keeping VSB equal to 0. Confirm? Body terminal taken from substrate, sir, right, that can act as what, sir? Second gate to terminal I call. that can act as a second gate terminal, sir. Gate terminal. Right? What I can call, sir, it can affect the channel conductivity if it is open. It affect the channel conductivity, sir. It affect the channel conductivity if it is open, sir. Right? So not only this one now, sir, particularly in the enhancement MOSFET, with this body effect, you can call to say that the threshold voltage increases. The changes in the threshold voltage you find out. So the changes in threshold voltage with respect to source to body voltage is called body effect, sir. Is called body effect call. Is called what I say? Body effect. Right? And it is overcome by making VSB equal to 0 volt, sir. How to keep VSB equal to 0 volt means that is shorted with the source or ground in NMOS, or shorted with the source or connected to drain supply in PMOS. Confirm? So whenever VSB equal to 0, what you told, sir, means threshold voltage look like be minimum, sir. At VSB equal to 0 volt, confirm. So you see this one now, threshold voltage VT equal to VT naught, minimum, sir. VT equal to VT naught you can call, that is minimum. If VSB not equal to 0, then the required threshold voltage comes to be greater than VT naught, increasing, sir. This is the minimum threshold voltage you can call. So that value goes to be increasing if VSB not equal to 0. So if the channel is, sir, threshold voltage required more, sir, means switching response becomes slow. That's a problem. Okay. How drain current varies in linear and saturation region of enhancement MOSFET, sir. Suppose now I can do this one now for NMOS condition, sir. This is the case for NMOS enhancement MOSFET, sir. This is the drain voltage. This is the drain current, sir. If I draw that one for a particular VGS, sir, you know that channel should be built up at VGS equal to VT onwards only. Before that channel should not present, sir. So that now I can draw the graph for VGS equal to VT constant onwards like this. This is for VGS equal to VT, sir. If I repeat this graph for one more VGS value, sir, like this. Suppose this is for VGS equal to some VT plus 1 volt, like this. So just now I told to you, sir, pinch off occurs at a particular drain voltage at which VDS equal to VGS minus VT you can call. This is the pinch off condition, sir. Confirm? Just to know. So now I can able to check out the pinch off condition, sir. See this one now? So pinch off occurs at a particular drain voltage like this. So this is the pinch off condition, you say. So this is the pinch off state, sir. Pinch off condition you can call. This is called VP. So before this pinch off, see this one now, sir, that is particularly smaller values of drain voltage. So this is called a linear region where drain current varies linearly with the drain voltage, where the MOSFET can act as a resistor, voltage variable resistor. Right? Sir, after pinch off, it is nothing but what you can call, sir, drain current is independent of what, sir, means drain voltage. It is called as a pinch off or saturation, sir. It is nothing but what? Pinch off or saturation you call. So here you observe now, sir, here the drain current is varies as a function of both VGS and VDS. Here drain current is function of only VGS, sir. With respect to VDS, it is a constant. With respect to VDS, it is look like what, sir? Constant you can call. Now, what is that one now, sir? I can show that one by the mathematical formula for that. Suppose I discuss this one for NMOS condition, sir. Check up this. How this current varies both in linear mode and saturation mode I call. Suppose in linear mode I call, sir. In linear mode, ID function of what, sir? VGS and VDS. Right? And here, what is the condition you see now? The applied drive, what is this one, sir? VGS less than what you can call, sir? VDS less than VGS minus VT you can call. Before pinch off it is. Here VDS less than VGS minus VT for NMOS. And what is the formula of drain current if I find out, sir? Here the formula of drain current to be like this. ID equal to some K dash into VGS minus VT into VDS minus of VDS square. So this is the formula for drain current, sir. So VGS is the gate voltage at which you define. VDS is the drain voltage you can call. VT is the threshold voltage at which the channel is built up. K dash is called as a transconductance value, sir. Where K dash is a transconductance parameter you can call. So this is a transconductance parameter, sir. So for NMOS, it is depending on what, sir? Mobility of electrons and oxidation capacitance, sir. COX stands for oxidation capacitance. Epsilon OX by T call, right? W is nothing but channel width, sir. L is nothing but channel length you can call. So on all these things it is depending, sir, whose unit is ampere per volt square. So where mu stands for mobility of electrons, W stands for channel width you can call, L stands for channel length, sir, COX stands for oxidation capacitance, and all these factors it is depending, right? And you remember now drain current directly proportional to what, sir, means W by L. W by L is called as a aspect ratio, sir, channel width to channel length ratio. So this is the expression for drain current in linear mode, where ID function of what, sir? Both VGS and VDS you can call. Suppose if I go for in saturation mode, sir, if I go for the same drain current in saturation mode like this. If I go in saturation mode, you say that ID function of VGS, sir, with respect to VDS it is constant. Look like ideal current source you call. Where you see this one now, applied drain voltage should be greater than or equal to VGS minus VT, sir, for NMOS. Confirm? So what is the formula of drain current you can call? K into VGS minus VT whole square ampere. Right? For given gate voltage, this is the formula you can calculate. What is that K, sir? Where K is nothing but again be a transconductance parameter. K equal to some K dash by 2, sir. K equal to what, sir? K dash by 2 you can call. So that equal to what, sir, means mu n COX W by L. So here small thing, sir. It's not 2L. Just 1 minute. So K dash equal to what I can call, sir? Mu n COX W by L only, sir, it is. Sorry. So mu n COX W by L you can call. Whereas K dash if you go, so if I go for K dash, sir, it becomes as a mu n COX W by 2L you can call. Ampere per volt square, sir. Where mu n stands for mobility of electrons, W stands for channel width, L stands for channel length, COX stands for oxidation capacitance. So in the saturation mode, the drain current is a function of VGS, sir. There it look like an ideal current source, sir, as well act as an amplifier. Confirm now? So before pinch off, it is in linear region, sir, where the drain voltage is small you can call, where drain current is a function of both VGS and VDS you can say. And this is the transconductance parameter for NMOS, sir. So mu n COX W by L. W stands for channel width, L stands for channel length. Now, COX stands for oxidation capacitance or mass capacitance you can call. So that can be defined per unit area. Okay, check out the next one. What is channel length modulation, sir? What is channel length modulation? See this one now. Suppose now I take NMOS, sir. Sorry. Now I take suppose NMOS. See this one now. I take NMOS body, sir. This is NMOS body I taken. Right, sir? So it have a P-type substrate, confirm, on which you are introduced to diffuse highly doped N plus materials to act as source and to drain, sir. Source and to drain you call. Confirm. Entire surface is overlaid with oxidation coating you call. This is the oxidation coating, sir. SiO2, whose thickness is a T call. T is the thickness of SiO2, sir. Right. After that, polysilicon gate, provided. This is a polysilicon of gate, sir. Confirm. So this is the body tunnel you call. You know that body tunnel is shorted with what, sir, means source commonly you say, right? It is shorted with the source, sir. So it is shorted with what, sir? Source. Now I can written for NMOS. It is shorted with the source. So that VSB equal to 0 you call. Sir, commonly you say that drain is kept at positive potential with respect to source for drifting of carrier, sir. This is the case. This is the drain supply, and the corresponding is a drain voltage, sir, VDS. Confirm. And in between gate and source, we are connecting what, sir, means supply of forward bias gate voltage, sir, with respect gate as a positive potential. By that, we can able to build up the channel. So the corresponding voltage is called what, sir, means gate voltage VGS. Confirm. So gate voltage VGS you can call, students. Understood on this? So this is the gate voltage, sir, between gate and the source terminals. See this for now. Here, drain look like to be at reverse bias potential with respect to source, because drain you are applying a what, sir, means positive potential. So this is the channel, sir. This will be the channel. So what is that channel length? I can show that one to you. This is called channel length, sir, L. This is called channel width, sir, W. So original length is L, sir. Original length is L from source to drain. Now I can apply as ordinary PN junction reverse bias principle, sir. So you know that whenever the reverse bias gate voltage increases, what happens, sir, means the barrier can expand. Where it is expand, sir? In a lightly doped area. Who is at reverse bias, sir? Drain is look like at reverse bias potential with respect to source. Because drain connected to positive potential, sir, it look like at reverse bias with respect to source. So with this one now, with this drain voltage, the barrier is going to be added. There should be added barrier effect with respect to source. And that barrier look like be increasing near drain and it tapers as you move towards source, or like this. This is the barrier. So this barrier is created across drain like this. Confirm? So this is the barrier that is created in the p-type region, sir, that can have negative ions, right? So this is the barrier effect by the added negative ions there near drain. Added barrier effect, confirm, by negative ions, because it is a p-type metal, sir, near a drain. Sir, by that what the thing you find out, sir? What is the original width? You can call L. So now look, by the added negative ions there, the width of the channel reduces, sir. By this added barrier effect, the effective channel length reduces, sir. How it decreases means I show that one to you. So original channel length is L, sir. So this is the barrier effect you can call. So that can I assume that delta L, sir, it is. It is a delta L I call. Then effective channel length becomes what, sir? L minus delta L. Sorry. So effective channel length becomes what, sir? This is the effective channel length that becomes as L minus delta L. So by this added barrier effect, there is a small deviation in the length, sir, channel length. Delta L is not much higher, sir, very small. Anyhow, there is a change in the channel length with applied drain voltage that to be called as a channel length modulation. The variation in the channel length with the applied drain voltage is called channel length modulation, you can call. What are the importance of this one, sir? The effective channel length somewhat decreasing. Sir, as the channel length decreasing means the transit time, journey time for the carriers to move from source to drain decreases. So transit time decreases means in a given time some number of carriers more, number of carriers reaching the other end increases, drain current increases, the transconductance goes to be increases. So that is the case of this one, sir. So with effect of channel length modulation, he said that there is a somewhat change in the drain current with the drain voltage also. And one more thing, sir, this channel length modulation effect should be considered only in saturation mode where drain voltage look like be good. Suppose if I go for linear mode, sir, drain voltage is very less, you know already, such that barrier effect is not be considered. So here barrier effect is mainly considered with respect to the drain voltage, sir. So for ordinary drain voltage, you don't find out this barrier effect, such that this channel length modulation condition considered only in saturation mode. Confirm? What is the thing I told? So what I told, sir, with applied drain voltage, confirm, there is reverse bias effect, sir, at drain as compared to source. Confirm? Then there is a added barrier effect, sir. Added, that is the depletion region effect you call. Added barrier effect near drain. Confirm? So that effective channel length decreases, sir. Effective channel length decreases from L to L minus delta L call. So what I told, sir, changes in channel length, with respect to drain voltage is called channel length modulation, sir. Is called channel length modulation, you call, denoted by lambda. So that is called as a channel length modulation denoted by lambda, sir. Okay, sir. Now let us consider this channel length modulation is effective only in saturation mode, sir, where VDS would be considerable. If you go for linear mode, sir, channel length modulation is ignored, right? Lambda effect, sir, that is channel length modulation effect you call, is taken in saturation mode, sir. Originally you say that in saturation mode drain current is a function of only VGS. With this lambda effect there is a little bit change in drain current with respect to drain voltage also. That I show by the graph, sir. See this one now. Originally in the saturation mode you say that the drain current increasing with respect to drain voltage, sir, with respect to gate voltage only. But if you take that channel length modulation, sir, there is a little bit increase in drain current with respect to what, sir, means drain voltage also. See this one now. This is without lambda effect, sir. This is without lambda effect, I call. Now I can go for same of that one with the lambda effect now. Same that one I can take, sir, with the lambda effect. See this one now. No changes in the linear modes are almost same. While I can go for saturation mode little bit increase, sir, like this. This is with lambda effect, sir. So lambda effect is considered only in saturation mode, sir. In linear mode is not considered because applied VDS is less. No barrier effect you can call, such that no change in the channel length. Sir, with respect to lambda effect, what is the expression for drain current means like this? With the lambda effect, confirm in saturation mode, this is the formula, sir. ID equal to, see this one now, K into VGS minus VT whole square per n mass I consider, sir. Derived formula I am writing 1 plus lambda into VDS. This is the formula where lambda stands for what, sir? Channel length modulation you call. So you already know that this is the ID saturation, sir. Saturation drain current without lambda effect you can call. So if I take that lambda effect, there is a small change in that drain current. So this is the case. What is that lambda, sir? Lambda stands for channel length modulation, and you remember that, sir, lambda to be indicated as reciprocal of early voltage. Like this you can also call 1 by Vs, sir, whose unit is volt inverse. Whose unit is what, sir? Volt inverse you can call. So this is the channel length modulation effect you can say. But this is considered in saturation mode. With respect to that, you may find out there is a small change in drain current with respect to what, sir? Drain voltage also. But sir, commonly if you specify only can take, otherwise commonly it is ignored. Okay. Check up. What is flat band voltage VFB, sir? What is the flat band voltage VFB? Sir, you know that in the case of MOSFET, right between the channel interface and what, sir, means gate electrode, there is a oxidation coating is there. See this one now, in our construction, just I indicate small diagram. This is the channel interface, sir. This will be the channel interface. Confirm. This is the oxidation, sir. So this is the oxidation you can call. Right, sir? Here it is a polysilicon of gate, sir. So you see this one now, sir, it look like a capacitor you call. So how to carry the charge carriers from one surface to the other surface means that's very, very difficult, sir, because this oxidation coating do not allow any carrier into it. This is the oxidation, sir. So how to transfer the carrier from one to the other one means that to be done with help of flat band diagram, sir. That to be done with help of flat band diagram we can call. See this one now, I show that one by the flat band diagram. Same thing. This is what, sir? Oxidation coating. SiO2. On one side what is there, sir? Polysilicon gate is there. This is the polysilicon gate, sir. Commonly polysilicon material is nothing but look like what, sir, means it is a what, sir, means composite body, look like act as a what, sir, means metal. This is a polysilicon gate, sir, look like act as a metal. And whose Fermi level, sir? This is the Fermi level of it. This is the Fermi level of that one, sir. This is the vacuum. I go for this is vacuum, sir, free space. That's be the vacuum I call. Sir, other side what, sir, means channel interface. Suppose NMOS, sir. So now I can go for NMOS, sir. For NMOS, channel interface is a P-type semiconductor you can call. That is a P-type substrate, sir. So this is a P-type substrate. P-type semiconductor you call. For P-type semiconductor, sir, you know that this is what you can call, sir, conduction band. Sorry, this is what, sir, valence band, you know. This is what? Valence band, sir. This is what, you know, conduction band. This is the vacuum I call. Sir, for P-type semiconductor, you know that Fermi level lies near the top of valence band. So in between these two things, sir, who is there? Oxidation coating is there. In between these two things, who is there, sir? Oxidation coating is there. I wanted to carry the carriers from one end surface to the other one, that too from gate to the channel interface. If, sir, originally I told that SiO2 do not allow, then how do you carry that one? Means, first of all, I can carry the carriers from Fermi level to the vacuum, from vacuum to this one Fermi level. So that to be how much voltage you require, sir, defined by the flat band voltage. So see this one now, first of all, I can able to carry the carrier, suppose electrons here, from Fermi level of the polysilicon to what, sir? Vacuum. So how much is the work done that you require, sir? That is called as a work done, a work function for metal, like this. It is a work function for metal you can call. Sir, work function of a metal indicate how much is the energy you require to carry the electron from Fermi level of the polysilicon crystal to the vacuum. After that, now I can able to go for, sir, this is the vacuum where the carrier is there. Now I can able to carry that carrier from that vacuum to the Fermi level of that p-type semiconductor, which is just above the valency band, like this. I carry this one now. Sir, how much energy you require to carry this electron from vacuum to the Fermi level of this p-type semiconductor, sir? That is called as, what, sir, means Fermi function. That is called as a work function for semiconductor, sir. That will be called as a work function for what? Semiconductor you call E pi S. Right? So what is the flat band voltage, sir? It is the work function difference between metal and semiconductor. It is the work function difference between what, sir? Metal and semiconductor you call. It is the work function difference between metal and semiconductor if none of the charge is stored in either oxide region or at channel interface. So the flat band voltage is the work function difference between metal and semiconductor if no charge is stored either in oxide region or at channel interface. So that is nothing but E pi m minus E pi s, sir. That is called as a flat band voltage, you say. So using which you can carry the carriers from one area to the another area. Check up now what I told you. Flat band voltage VAB is the work function difference. Confirm? Work function difference, sir, between metal and semiconductor. Metal and semiconductor if no charge is stored. No charge is stored either in oxide region, sir, either in oxide region or at channel interface, sir. Confirm? This is the case. So how do you indicate that one now? Just now you told that energy, that is flat band diagram, sir. From that flat band diagram, so now I can able to indicate this one now. So from that flat band diagram, I indicate that one now, sir. See this one now. From flat band diagram, just now I told you. From flat band diagram, sir, you written like this: VAB equal to, that is flat band voltage, sir, pi ms you can call. So that is pi m minus pi s volt. So what is this pi m, sir? That is a work function for metal using which you can carry the electron from Fermi level of the metal to the vacuum. What is the pi s, sir? Fermi level for what is the, sir? Pi s stands for work function for semiconductor, sir, that represent the voltage required to carry the electron from vacuum to the Fermi level of the semiconductor. This one. All this is considered if no charge is stored, sir. If already some charge is stored, if there is a small change. If already some charge stored, sir, on the oxide region or at interface, right, then VAB can be modified like this, sir. VAB equal to pi ms minus QSS by COX. What is this QSS, sir? It is a charge density, so charge for unit area. QSS is surface charge density, sir, amount of charge stored per unit area. COX is the mass capacitance, sir, capacitance per unit area. So if it's already some charge is stored, then the required flat band voltage decreases. So originally is pi ms. So now that come to decreasing if already some charge is stored in the oxide region. Confirm now? So that can be modified as pi ms minus QSS by COX you call. QSS is what? Surface charge density. COX is what you can call, sir? Mass capacitance you call. Got it now? Sir, operation of mass capacitor you call. Sir, mass capacitor, you already know that, sir. Separation of conducting channel and gate electrode by SiO2 look like a capacitor whose capacitance can be changing with applied gate voltage, sir, such that the MOSFET can be used as a voltage variable capacitor. MOSFET can be used as a what, sir? Voltage variable capacitor. And this mass capacitor is of two types, sir. One is NMOS capacitor, other one is a PMOS capacitor you can call. If you go for NMOS capacitor, sir, NMOS capacitor having a P-type substrate. NMOS capacitor is what, sir? P-type substrate. Whereas PMOS capacitor have N-type substrate you say. Sir, this mass capacitor having 3 operating modes. This mass capacitor have how many operating modes, sir? 3 operating modes you can call. What are the 3 operating modes, sir? One is accumulation mode. Other one is depletion mode. Other one is inversion mode. Confirm? It have 3 operating modes, sir: accumulation, depletion and inversion. Suppose I show that NMOS capacitor. This is NMOS capacitor, sir, having a P-type substrate. This is a P-type substrate, sir. So you know that entire surface is overlaid with what, sir? Oxidation coating. This oxidation thickness is very thin, you know. This is that, sir, T. This is SiO2. So this is a polysilicon, sir, of P plus or N plus, whatever you can call. Alright, this can act as a gate, you know. This is the body terminal you call. So we can apply the voltage here, sir, that is this. So this is NMOS capacitor, sir, that NMOS capacitor having a P-type substrate you call. Whereas a PMOS capacitor, if you go N-type substrate you can use. This is NMOS capacitor, sir. That is what, sir? NMOS capacitor you call. Now I can able to go for accumulation mode, sir. See this for now. In the accumulation mode, what, sir, means Vc equal to 0 volt or negative voltage, sir, you can apply. If I apply gate voltage in 0 or negative, sir, what you can apply? Suppose it is negative voltage you call. Sir, in the P-type substrate, who is there? Holes are the carriers that are accumulated here. The holes are attracted by this, what, sir, means surface charge of this interface, sir. So by that the holes of the P-type substrate moves towards the interface, sir. This is the channel interface you can call, moves towards there and accumulated there. They are unable to go to the other side because in between that oxidation is there. So this is called as accumulation mode. Sir, accumulation of holes, so holes are the free carriers that do not causing any barrier effect, such that in the case of accumulation mode, the capacitance is considered by only oxide region, sir. In this region, capacitance is considered by oxidation region. Capacitance by SiO2 only, sir, and that look like be maximum, sir. C equal to COX, sir, that equal to epsilon OX by T, where epsilon OX is the permittivity of oxidation, sir, T is the gate oxide, sir. So both are constant, sir. So it is maximum and constant. So what is that accumulation of holes at the interface do not causing any barrier effect. So that is the first one of that. That is called as a what, sir, means accumulation mode. Now I can able to go for, sir, a depletion mode, you say. If you go for a depletion mode, sir, applied gate voltage is small positive, sir, Vc equal to positive, sir, and it should be less than Vt you can call. It is a small positive value but less than threshold voltage. If I apply small positive voltage here, what you can call, sir, this become positive charge. So this one become negative, sir. With that one, what are the holes who are accumulated in the previous case? That holes are depleted from the surface, sir. Depleted from the surface. So the depletion of these holes from the surface, what you can call, sir, occurred the junction principle, sir. Occurred the junction principle. So this leaving of holes at the interface, creating negative ions. Creating what, sir? Negative ions like this. Sorry. Creating negative ions at the interface. So holes are depleted, sir, like this. Depleted from the interface and leaving negative ions. So this negative ions causing some width, sir, that I call D. So now here the capacitance is considered by both oxide region and barrier effect you can call. Here capacitance is by what, sir? Oxide and barrier. Capacitance is by what, sir? SiO2 and added barrier, sir. Both can present. So here the total capacitance is what, sir? C equal to COX CT by COX plus CD, sir. So COX plus COX into CD by, sorry, COX into CD by COX plus CD you can call, where COX is the oxidation capacitance, sir, that is maximum constant you call. CD is nothing but the added barrier capacitance, sir, where D stands for width of the barrier you call. Where D stands for what, sir? Width of the barrier. Confirm now? Where CD equal to barrier capacitance, sir, epsilon Si by D. Where epsilon Si is the permittivity of this p-type substrate of silicon, sir. This is barrier capacitance, sir. That is barrier capacitance. So this become minimum, sir. Decreases to minimum. So this is nothing but what, sir, means you can call depletion mode, sir. Other than this, we can also find out one more mode that is called what, sir? Inversion mode. Inversion mode is nothing but what, sir? Vc equal to greater than Vt, sir. Greater than or equal to Vt. More positive there. More positive condition, sir. In this mode, what you find out, sir, means there is a breakage of covalent bonds in the p-type substrate because the applied gate voltage is what you can call, sir? More positive you can call. Applied gate voltage is more positive, sir. So that on the p-type substrate, the covalent bonds are broken. On p-type substrate, the covalent bonds are broken. The breakage of covalent bonds can able to give what, sir, means electron hole pairs. The breakage of covalent bonds gives what, sir? Electron hole pairs you can call. Among that, the holes are moving down and electrons are moving up. Sir, on moving of electrons towards the upper side, what are these negative ions I told in the previous case of depletion mode? That area occupied by these electrons. Sir, once the free carriers are occupied in the place of ions, ions effect is not be considered. So that added barrier effect come to decreases. So what is the barrier effect by the depletion mode you can call that can able to reducing by the generation of this inversion layer by the opposite carriers of electrons. So here, why do you call this inversion layer, sir? At the interface, you are going to be considering the generation of opposite polarity carriers to cancel the added barrier. So that is called as the inversion layer. So based on that, here again the capacitance comes to be what, sir, means increasing and become maximum by what, sir, means that capacitance again equal to what, sir, means oxidation capacitance only. So in the inversion mode, the capacitance again be increases, sir, because what are the electrons who come to this towards the interface, so that can come to reducing the effect of the barrier, such that the barrier effect decreases, resultant capacitance increases, and again what you say, sir, means the capacitance comes to the maximum. That is called as a strong inversion, where again the capacitance is considered by what, sir? Only oxidation capacitance, only the oxidation capacitance. Like that you find out 3 operating modes. This is the case. If I draw the graph for NMOS, sir, sorry. If I draw the graph for NMOS, sir, this is the case. This is plus Vc. This is minus Vc. Right, sir? So all this is an accumulation mode. Okay, capacitance is maximum, sir. Now in depletion mode, capacitance become decreases, sir. Right? This is the threshold voltage. This is called weak inversion again. Again, above threshold, sir, you find out that inversion mode, sir, where the barrier capacitance effect decreases because of the inversion generation of electron, sir, opposite polarity electrons at the interface to reduce the added barrier, sir, to reduce the effect of added barrier. So again it increases. Go for strong inversion like this. So this is accumulation, you say. This area is accumulation, sir. All this is per n mass I draw. This is depletion, sir. Right, all this is inversion, sir. Right, sir. Here capacitance is by oxide and barrier. COX CD by COX plus CD. Here capacitance is by only oxidation, sir. Again here it is by oxidation. It is called strong inversion, you say. Strong inversion. Here capacitance decreases to minimum. Again, because of the reduction in the barrier effect by the inversion layer, that is growth of opposite polarity carriers at the interface to reduce the barrier, the capacitance increases and becomes maximum. That's called strong inversion. This is called weak inversion, sir. So at threshold you have a weak inversion, you say. Here the weak inversion is there. Confirm, sir? So at threshold point weak inversion is there, that comes to increasing and becomes maximum. Confirm. Next one I check out. Sorry. Explain the basic principle of CMOS inverter recall. Explain the basic principle of CMOS, sir. CMOS stands for complementary metal oxide semiconductor. CMOS stands for what, sir? Complementary metal oxide semiconductor, you can call. That's called as a CMOS. Sir, CMOS is considered by the combination of one NMOS and PMOS of enhancement MOSFET. Already you know that depletion MOSFET not be preferred. Which one should be preferred, sir? Which one to be mostly used, sir? Enhancement MOSFET to be used. It is a combination of one NMOS and one PMOS. That should be called CMOS. This CMOS is most popular to use in VLSI designs. Why do you, sir? Means the main important thing is, sir, as compared to NMOS, CMOS should be mostly preferred. The main thing is nothing but it have a good packing density, high noise margin, very low power dissipation, sir. So it having a very low power dissipation among all the logic family circuits, you know, and what you can call, sir, high noise margin you can call, and a good packing density you can call, and it completely avoid the use of resistor in its design. So even as compared to NMOS, CMOS must be preferred, sir, because of good packing density. CMOS should be preferred. CMOS is the combination of what, sir? One NMOS and PMOS. And in the case of CMOS design, sir, you remember that, right? NMOS should, say, PMOS should be always be connected at top. PMOS should be connected at top, sir. NMOS should be connected at bottom. The meaning of that one, sir, NMOS is always be connected to ground. PMOS is always be connected to supply. So it is the combination of NMOS and PMOS, sir. Both are integrated to be like this. So NMOS should be always in the ground position, sir, bottom position. PMOS should be top position, sir, drain supply. Sir, why do you connect the PMOS towards the supply? Means because PMOS is strong to allow logic 1 and weak to allow logic 0. Right? PMOS is strong to allow logic 1, sir, and very poor or very weak to allow logic 0. So that PMOS always be connected at top. Whereas NMOS, if you go, sir, NMOS is very strong to allow logic 0 and very poor or weak to allow logic 0. So that NMOS is always be placed at the ground. So, and once again, sir, a common input must be applied to both NMOS and PMOS. This is the structure. A common input must be applied to both NMOS and PMOS, sir. And once again, the output should be taken across NMOS only. Output to be taken across what, sir? NMOS. And so now, so a CMOS is a complementary metal oxide semiconductor, I call. It is a combination of one NMOS and one PMOS, sir. And that too, those are enhancement MOSFET type, not depletion MOSFET, sir. Okay. So what I told here means This CMOS is preferred even as compared to NMOS. Why, sir? Because of its good packing density, very low power dissipation, sir, having high noise margin. And you know that, sir, the entire CMOS circuit not using any resistor in its design, sir. Completely avoid the use of resistor in its design. It is the most popular to use in VLSI circuits. It is most popular to use in VLSI circuits, sir. You observe now, even the drain supply is there, that is directly connected without any resistor. And according to the CMOS design, you see this one now, PMOS is always be kept at the top side, that is connected to drain supply, sir, because it is strong to allow logic 1, and it is not allowing logic 0, sir. It is very poor to allow logic 0, so it can allow logic 1 without any destruction. Whereas NMOS is always kept at the bottom, sir, that is connected to ground, because NMOS is strong to allow logic 0. It can allow logic 0 without any destruction. According to the CMOS design, a common input should be applied to both NMOS and PMOS. And output must be taken across NMOS only, sir. So that is the design of it. See, for now, what are the design of this one, sir? This is a PMOS. So simple I use. A bubble head indicate PMOS, sir. In the case of PMOS, source is taken with respect to drain. This is the PMOS, sir. This is NMOS I call. In the case of NMOS, drain with respect to source you take. This is NMOS. This is PMOS, sir. So both should be connected in series case like this. Drain to drain connected, but source to source not connected, sir. This is source connected to ground of NMOS. This is source connected to drain supply like this. And this to be connected to the common input. Output always be taken across NMOS, sir. This is the case. So this is the CMOS inverter design. This is the design of CMOS inverter, sir. And why do you call as an inverter? You can able to check up now. If I go for the transfer characteristics of this one now, sir. See this one now. So if I draw the transfer characteristics of this inverter, sir. Sorry. If I draw the transfer characteristics of this CMOS inverter, the graph may come like this. This is your input, sir. This is your output, you can call. Confirm. The graph come like this. So this is the logically threshold region, that is VDD by 2, sir. That is logically threshold region, that is called VDD by 2, you can call, below which input is lesser, so that output is maximum VDD. Got it now? For Vi less than VDD by 2, input is low, sir, output is high. For Vi greater than VDD by 2, sir, input is high, output is 0, sir. So output is a complement of input, you can call, look like a inverter. Look like what, sir? Inverter, you say. So the CMOS inverter circuits are like this. If you go for practical design, sir, in a case of practical like this. This is the practical case. This is the ideal condition I told, sir. Ideal response, you, sir. If I go for practical, sir, this is the case. So the graph may come like this. This is the graph you may get. Just 1 minute. So this is the case, sir. You may find out like this. This is the transfer characteristics of CMOS inverter, you can call. Now we can able to divide into different modes there. So based on that PMOS, linear, saturation, all these conditions you may find out. If you go for practical condition, this is the case, sir. So what are the regions you find out now? This is the thing you can call. This is VTN, sir, threshold voltage of NMOS. Confirm? This is what you can call, sir. So this is nothing but what you can, sir, VDD by 2 I call. Just 1 minute. Sorry. this one now, I can indicate that one. This is VTN, sir. Threshold voltage of NMOS you can call. VTN, sir, I suppose. Now I written like this, threshold voltage of NMOS. If you go for this one, sir, this is what you can call, sir, means VTN you can call. This is nothing but what you can call, sir, threshold voltage of PMOS you can call. So VDD by 2, now I can able to go this. This is VDD by 2, sir. Sorry. Exactly half point, now I can come back. This is the VDD by 2, sir. Sorry, 1 minute, I can do that again. So if you go for transfer characteristic, a practical case like this, sir, you may get that one is a practical case like this. Right, sir? So check up now what are the conditions there I can show to you. VTN you can call. VDD by 2, sir. Right, that is VDD by 2, sir. This is VDD minus modulus of VTP, sir. This is threshold voltage for PMOS, sir. This is called VDD. So different conditions are there. So if you go for this one, sir, what if that NMOS and PMOS here? Here NMOS is cut off, sir. NMOS is cut off, PMOS is linear, you say, according to the condition. If you go for this one, sir, okay, NMOS is saturation, sir. NMOS is saturation, PMOS linear, sir. If you particularly take this one now, both NMOS and PMOS are in saturation, sir. NMOS and PMOS are in saturation at VA equal to VDD by 2. NMOS and PMOS are in saturation, sir. Now in between this greater than VDD by 2 and less than VDD minus VTP you can call. In this area if you go, sir, where PMOS is saturation, sir, NMOS is linear. If you go for particularly this area, sir, where NMOS is linear and PMOS is cut off, sir. PMOS is cut off. PMOS should be cut off. This is the case. If you go for the practical case, this is the conditions you call. First area in between 0 to VTN, NMOS is cut off, PMOS is what, sir, means linear. In between VTN and VDD by 2, sir, so greater than VTN and less than VDD by 2, NMOS saturation, PMOS linear, sir. Exactly VDD by 2, that is called as a logically threshold region. Both are in saturation region you call. If you go for, sir, greater than VDD by 2 and less than VDD minus VTP, sir, VTP stands for threshold voltage of PMOS. Why do you take modulus, sir? Because for PMOS threshold voltage is negative, so negative sign not considered, sir. By that I taken modulus. So VDD minus modulus of VTP, sir, where PMOS saturation, NMOS is in linear. Okay. So final regions are greater than VDD minus modulus of VTP and less than or equal to VDD, sir. There NMOS is linear, PMOS is cut off. PMOS is cut off. So this is the transfer characteristic of CMOS inverter. So ideal response, practical response you may call. Sir, CMOS is nothing but most popular to use in VLSI designs. VLSI designs you can call. Understand this? What I told you? CMOS is the combination of NMOS and PMOS, sir. Confirm? Combination of NMOS and PMOS, sir. It has what I told, high packing density, right, high noise margin, sir, and very low power dissipation, sir. Very low power dissipation. What I told, sir, it completely avoid the use of resistor in its design. Completely avoid the use of resistors in design. Confirm? It is very popular to use in VLSI circuits, sir. It is popular to use in VLSI designs. Confirm? It is popular to use in what, sir? VLSI design. This is about CMOS inverter. Okay. Hi. In this EDC marathon class, you discussed what means the carrier transport phenomenon of silicon. That is nothing but semiconductors you discussed, as well as PN junction theory part you learn. Right. Based on that, special diodes you discuss, some Zener diode, Varactor diode, like this tunnel diode. So this is special diodes, and optoelectronic devices you discussed. Those are LED, photodiode, solar cell. These things you discussed. Next, you examined that BJT configurations you discussed, and what are the main comparisons of common base, common emitter, common collector. And based on that, you learned already load line analysis and selection of Q point. You checked out, and then finally you discussed that FET, MOSFET transistors, and MOSFET, enhancement MOSFET you discussed, and how it is useful in VLSI circuits. Based on that, you discussed mass capacitance, CMOS. These are the topics you covered in this EDC marathon class. I hope that this EDC marathon class should be very useful to you for all your interviews related to this electronics sector, right? So whenever you can able to go for any interviews concept of ISRO or any other one. So for all marathon, for all interview programs, this EDC marathon class 100% helpful to you, right? All the best. Thank you.